Hello my dear PUC champions, welcome to PUC Karnataka YouTube channel. Now this is a very special live for all of you, and here we are going to discuss all the important questions chapter wise for all of your PU2 chapters. Right now this is a recorded live, it is not actually live, so if you want to communicate with me, you can post your comments in the chat. I will be replying back that through chat only. I will not be available to reply to your chats through after watching the chat. Right, so now what you will get in this lecture, very important, all the important questions including numericals, including questions from your question banks, MCQs, 2-3 marker and 5 marker chapter wise, starting from electric charges and field, and then we'll go chronologically according to your chapter orientation in NCERT. Right, so let us start with today's session. First chapter is obviously electric charges and fields, and then we will go on with the next lectures. Right, so do watch it. If you are not comfortable watching straight 12 hours, then what you can do, you can watch first 6 hours, then you can come back and again watch the remaining 6 hours. But this one video will prepare you for 70 out of 70 in your final exam. And if you want to download the PDF, you know what you have to do. You have to go into the WhatsApp channel, and also if you are watching our channel for the first time, I request you to subscribe, because more of such videos are coming in our channel. First, I am going to discuss about the blueprint. Now in the new blueprint, they have not given the separation between whether the question that is going to come, will it be a MCQ question or will it be a fill in the blanks question. So for the safer side, we are going to discuss everything. So one mark question will come. This may be an MCQ, that is 99% chance, because all the 3 model question papers giving you MCQ from this chapter. Now short answer type questions will be, there will be a 1-2 marker question from this chapter, there will be 1-3 marker question from this chapter, and there will be a long answer type question from this chapter. Now this long answer type can be a derivation, can be a numerical question, it can have both. Okay, last year's final board paper 5 mark numerical question came from this chapter, but this year there is a chance that 50% chance that this year there will be a derivation from this chapter and numerical question will come from the second chapter. Okay, so you have to prepare for everything. Okay, and those who somehow misses the first paper and want to improve in the second paper, then they have no other option, they have to prepare everything, 5 mark derivation, 5 mark numerical as well. Okay, now let's look into the questions that we are going to discuss. We are going to discuss 15 MCQs, we will be also discussing 5 fill in the blanks, we will be discussing short answer type questions 5, we will be discussing short answer type 3 marker question 5, we will be discussing 4 very important derivations from this chapter, and also we are going to discuss 6 numericals from this chapter. Okay, so if you watch this entire chapter will be covered through this one lecture. Now let's continue with the first question. The electric flux over a closed surface enclosing a charged particle is minus q by 6 epsilon naught. The charge of the particle is, so total charge enclosed, total electric flux is basically, we know that electric flux is given by charge enclosed divided by epsilon naught, and that value here, now let me write this like this so that there is no confusion. So charge enclosed divided by epsilon naught. So suppose there is a Gaussian surface and the charge which is enclosed inside it is QEN, then QEN by epsilon naught is the electric flux, and that is given by minus q by 6 epsilon naught. So if you compare these two, you get Q enclosed is equals to minus q by 6. So Q enclosed is minus q by 6, it is not any other value, so it will be minus q by 6. Option C is correct. Next question, the value of basic unit of charge is, so the basic unit of charge is 1 electron, charge of an electron, that is 1.6 into 10 to the power of minus 19. Now if you see the options, they have cleverly given 1.9 into 10 to the power of minus 16, so they just change the 6 and 9. So be careful, answer it, it's easy question. Now next, the SI unit of electric flux is, electric flux is given by electric field into area into cos theta, right? Now unit of electric field is Newton per coulomb and area is meter square, and cos theta is a dimensionless quantity, so Newton per coulomb meter square is the SI unit. So if you see the option C is again correct answer for this question. Now let's move on to the questions. If a body contains N1 protons and N2 electrons, then the net charge of the body is. So very interesting question. This is from your this year's model question paper. So body contains N1 number of protons and N2 number of electrons. Now you might say, sir, which one is bigger, which one is smaller is not given. How can I calculate the net charge? No need. We know that charge of a proton is always positive. So what is the total charge of the protons? Total charge of the protons is number of protons times the charge of a proton. Now charge of a proton interestingly is same as charge of an electron, only thing is they are positive. Okay, amount is same, only thing is proton is positive, electron is negative. So this is the total amount of charge of a proton. Now charges are additive in nature. So what is the total charge of electrons? Total charge of N2 number of electrons. Total charge of N2 number of electron is N2 into minus E. Why minus E? Because this is electrons. So electrons are negative in nature. So basically this question is being answered through the property of electric charge, that charges are additive in nature. So if you take N1 number of protons into number of electrons, just multiply charges, individual charges, and add them. Also you have to take care of the sign of the charges. So if it is proton, then it will be positive. If it is electron, sign will be negative. So N1E minus N2E or N1 minus N2 into E. So this is the total charge of the body. So N1 minus N2 into E. Now if N1 is bigger, then charge will be positive. If N1 is smaller, then charge will be negative. As simple as that. We do not need to know which one is bigger, which one is smaller to calculate the net charge. Okay, so this is the formula, this is the way you should solve this kind of question. This is a little tricky question, can be considered as a HOTS question. Now next, electric field due to an electric dipole at a distance small r on the axis of the dipole is. So electric field due to an electric dipole on the axis of a dipole is inversely proportional to 1 upon r cube, not 1 upon r square. So it is inversely proportional to r cube, inversely proportional to r cube. Okay, if you remember, electric field due to a dipole on its axis is given by 1 by 4 pi epsilon naught 2p by r cube. So electric field on the axis is inversely proportional to r cube. Now next question. The electrostatic force between a pair of unlike and like charges respectively. Again, this is from your latest model question paper. The electrostatic force between a pair of unlike and like charges. So what is between unlike charges? Unlike charges always attract each other and like charges always repel each other. So first is attractive, so unlike is attractive and like is repulsive. Okay, so attractive comma repulsive is the correct answer, just to test your patience, just to test your whether you are able to read properly and answer this question or not. Okay, now next question. Gauss's law is true for any surface, only open surface, only closed surface, only spherical surface. Now 90% of you will blindly mark any surface and that is not true. Gauss's law is true for only closed surface, only closed surface, and that closed surface can be anything. Okay, even if you consider a plate, okay, a plate that where you eat your lunch and dinner, that place is also a surface, but in that case that surface Gauss's law is not applicable. This is an open surface. A bowl, okay, if you are considering a bowl where you drink your soup or tea, so that is also can be considered a surface, but they are all open surfaces. As long as it's a closed surface, the shape of the surface does not matter, but closeness do matter. Okay, so be careful. Again, easy question, but again that can trick your mind. So it is only true for only closed surface. Next question, the SI unit of electric charge is coulomb meter, coulomb per meter, coulomb. So SI unit of electric charge is coulomb. The total electric flux through a closed surface in air is equal to 1 by epsilon naught times the total charge enclosed by that surface. This is the statement of Gauss's law of electrostatics. So Gauss's law of electrostatics is the correct answer. So option C is correct. Next question, the SI unit of surface charge density. This is one of your previous year questions. I think 2024 this question came. The SI unit of surface charge density is coulomb per meter square. Coulomb per meter square. Okay, not coulomb per meter cube, not coulomb per meter, but it is coulomb per meter square. SI unit of surface charge density. Line charge density coulomb per meter and volume charge density coulomb per meter cube. SI unit of electric field Newton per coulomb or volt per meter. There are two units of SI electric field. One is coulomb, Newton per coulomb, and second one is volt per meter. Both are SI units. Next, what is the nature of Gaussian surface involved in Gauss's law of electrostatic? Magnetic, scalar, vector, electrical. So the nature of Gaussian surface involved in the Gauss's law of electrostatic is a vector. Okay, that's why we take E dot dA. Okay, E dot A. So if you remember, flux is always E dot A. That means the surface has to be a vector quantity. E cos theta, it is a dot product. So surface has to be a vector quantity. If it is not a vector quantity, then Gauss's law will not be applicable. Okay. Now next question, the angle between the dipole moment and electric field at any point on the equatorial plane is. So the direction between dipole moment is always pointed from negative to positive, and the electric field along the equatorial plane, this is very special, it is directed exactly opposite to that. So dipole moment is from negative to positive, electric field is from positive to negative. So the angle between these two lines when you draw from a single line will give you 180 degrees. So correct answer is 180 degrees. For axial case, the angle is 0 degree. The dipole moment and electric field are in the same direction. So in that case, angle will be 0 degree. Now let's see question number 15. The torque acting on an electric dipole placed in an uniform electric field is maximum if the angle between the electric field and the dipole moment is 0, 60, 90 or 180. Now we know that torque acting on an electric dipole is given by tau equals to Pe sine theta. Now sine 0 is 0, sine 60 is root 3 by 2, sine 90 is 1, sine 180 is again 0. So that means the torque acting on this dipole will be maximum when sine theta value is maximum. Sine theta value is maximum when theta is equals to 90 degrees. So the torque acting on this dipole will be maximum when the angle is 90 degrees. Next question. Now we are solving 5 fill in the blanks. One of the basic properties of electric charge is dash a pair of equal and opposite charges q and minus q separated by a distance 2a is an dipole. The electrostatic force between two charges is maximum in dash. Electric field inside a charged spherical conductor is 0. Two electric field lines will dash cross. So sometimes what happens, some of the fill in the blanks we can directly tell by reading it, okay, without even reading the options. Some of the fill in the blanks, we do need options to answer. So first of all, you pick up the questions where you can directly answer the fill in the blanks. Okay, for example, I know this is this will be a dipole. Okay, this will be a 0 and this will never cross. Okay, so these three are easily answerable. For remaining things, we need to check the fill in options. So if you see the properties of charge, so never, dipole, quantization, vacuum, 0, always. So among these, only quantization is the property of charge. So first option must be quantization. Second option, we have seen that a pair of opposite charges, equal and opposite charges, separated by a small distance. So that must be dipole. You cross verify it once. Even if you are sure, you have to cross verify it once if the option is mentioned or not. Next, the electrostatic force between two charges is maximum in never, vacuum, 0, always. So from these options, remaining options, only vacuum is making some sense. We know that force between two charges is given by 1 by 4 pi epsilon naught q1 q2 by r square. So if you put them inside a dielectric, the force reduce. That means the force is maximum in vacuum, right? There is no medium or free space, right? So the option could be vacuum, option could be free space. So you have to check it once and confirm it. So the correct answer for this is vacuum. Electric field inside a charged spherical conductor is always 0. Okay, so this is obviously known answer. So we will see whether 0 is given or this is given. Either Z E arrow given or this symbol is given, so you have to be careful and mark it correctly. Two electric field lines will never cross, so never is the obviously the answer, not always. Okay, two electric field lines never cross each other, so correct answer is never. Okay, so this is how you should tackle fill in the blanks. I have tried. Fill in the blanks are the most easy part, but still student make small mistakes in fill in the blanks. And remember, if you make one mistake in fill in the blanks, there is a chance that two mistakes will be automatically happen. Okay, the options are given generally such a way that there may be some cases confusion between two options. So if you make one option wrong, then there is automatic wrong answer can be happen to the another question. Okay, so be careful for fill in the blanks, because if you make one mistake, there is a chance, high chance, that there will be two mistakes happening without you are realizing it. Okay, now let's move on to our next segment, 2 marker questions. State and explain Gauss's law in electrostatics. The most important question from this chapter. Gauss's law states that the total electric flux passing through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. And his explanation is phi equals to q by epsilon naught. This is the flux through the surface, or E dot ds equals to q by epsilon naught. Q is total charge enclosed by surfaces. So here you have to draw a surface, name it S, and charge inside the surface you have to show it Q. Okay, so this is the total charge enclosed by the surface. Next question. Write Coulomb's law in vector form, explain the terms, state and explain Coulomb's law. Now this question can be asked as a 3 marker, also it can be asked as a 2 marker question. Okay, so here we are discussing it as a 2 marker question, but same question can be asked as a 3 marker question. Statement: Coulomb's law states that the electrostatic force between 2 point charges is directly proportional to the product of magnitude of the 2 charges and inversely proportional to square of the distance between them. Coulomb's law in vector form is F equals to 1 by 4 pi epsilon naught q1 q2 by r square r cap. Now in this case you have to show what is the r cap vector. Okay, so you can take this as your r cap and you have to mention this is minus r cap. Now obviously based on which f12 or f21 it can vary. Okay, this is the overall statement of Coulomb's law. And also you have to mention the terms. q1 q2 point charges, epsilon naught is permittivity of free space, r is distance between q1 and q2, r cap is the unit vector. Okay, now next, sketch the electric field lines for force due to a point charge if Q is less than 0, Q is greater than 0, or due to a dipole. Okay, so this question is a mix of your last year's model paper question and this year's model paper question. Okay, this year's model paper question, they have asked you to draw a due to a point charge, positive point charge and a dipole. Last year it was a negative charge, a positive charge, and dipole was not there. So if Q is less than 0, that means it is a negative charge. For a negative charge, all the field lines will converge at a point. So this is the, as you can see, this is negative charge, all the field lines are converging. For a positive charge, all the field lines are going away along the straight line. So you have to use a scale to draw this diagram. And for dipole that they have added, it's slightly tricky. So this will be a straight line, but remaining lines you have to draw using your hands, because even if you are using compass or scale, that will not be perfect, because there is no such, they are not circular, by the way. So these lines will not be circular. And you have to draw using your hands. Practice once or twice, it will be easy. Field lines will exit from positive and they will close at negative. Some field lines will go towards far away, and again it will come back to negative, but the connection you need not show. So 2 lines you show up, 2 lines you show down, and 2 lines you show going in this side, 2 lines you show going upside. Similarly, 2 lines coming from this side, 2 lines coming from this side. That's it. Okay, this is the electric field due to a dipole. Now next, define electric flux through an area element, mention its SI unit. This is a new question from your latest model paper. So definition of electric flux: the electric flux through an area element is the product of the dielectric field and the area vector, and it's represented the number of electric field lines passing normally through that area. Okay, so if you remember the diagram that is given in your textbook, this is how they have given it, right? Electric field lines, and some cases the field is not perpendicular, so in that case the theta angle was given. Okay, so phi is equal to E dot A, and it was given that this is the A vector, and the angle is given by this. Okay, so E dot A is EA cos theta. SI unit of electric flux is Newton meter square per coulomb. Okay, Newton meter square per coulomb, Newton per coulomb meter square is also acceptable. Okay, so you have to remember the second line is slightly extra. You can mention it, you cannot, you may skip it, but you have to remember that electric flux through an area element is the product of electric field and the area vector, dot product or scalar product. Okay, it is the dot product, mention dot product. Okay, dot product or scalar product of the electric field and the area vector, and it represents the number of electric field lines passing normally through the area. Mathematically portion you can write, you can skip, not important, but SI unit as part of the question you have to answer it. Next, define electric field at a point. What is meant by source charge? Again, this is a question from your latest blueprint. Not blueprint, sorry, it is taken from your latest model paper. The electric field at a point is the net force experienced per unit positive test charge placed at that point in an electric field. Again, mathematically E is equal to F by Q. So force experienced by a test charge divided by its own value of the charge is the electric field at that particular point. Okay, and what is the source charge? The source charge is the charge that produces the electric field in the surrounding space. In other words, it is the original charge responsible for creating the electric field experienced by other test charges. So when I am saying that electric field, we do not mention any charge who creates it. So source charge is the original charge that creates that electric field. Okay, so suppose I say this is a source charge. Source charge means it will have its own electric field. Okay, and if you put a test charge over here, it will experience a force. Okay, from that force we can calculate the electric field at that point. Okay, so a test charge, if the same question is asked and they add what is a test charge, Test charge is a charge that do not produce any electric field of their own. Okay, test charge means it's an imaginary charge that do not produce any electric field of their own. Now let's move on to the 3 marker category. Derive the expression for torque on an electric dipole placed in an uniform electric field. Very important and classic question. Even this question is, even though this is a very old question, and still it is included in your this year's blueprint as well. So here we have 2 charges. Say this is plus, this is minus, plus Q, minus Q, and we are trying to find what is the torque acting on this dipole. Okay, dipole is basically 2 charges separated by a small distance, say 2a, and when you place in an uniform electric field, it will not experience any net force, only net torque it will experience. Now suppose the electric field is E, electric field is E, charge is Q. So what will be the force on this charge? Force on this charge is given by Q into E, and it will be in this direction. Now this is a negative charge. Negative charge experiences a force in the opposite direction again, but magnitude will be same. Magnitude wise the force will be same, but the direction of the forces will be different. Now to equal and opposite forces, 2 equal and opposite forces acting on an object at different points creates torque. Okay, if this is happening on the same point, then they would have cancelled each other. There is no net force, there is no net torque as well, but because they are acting on 2 different positions along the same object, okay, it will create a torque. Torque means an effect of rotation. For example, you are pushing a door to open the door. So the door, when you are pushing the door, there is a torque acting on the door because the hinges produces an opposite force, hinges that on which the door is fixed, right? Now how to calculate the torque? Let me refresh your memories. Suppose this angle is theta. This is the angle between the electric field and the dipole moment. Dipole moment is from negative to positive. So dipole moment is along this direction and electric field is in this direction. So this angle is the direction between electric field and dipole moment. Now how to calculate torque? For that we have to find, first of all, our duty is to find the direct distance between these 2 forces. So one force was acting along this, one force was acting along this. So what is the direct distance between them? We have to find that first. How to find the distance between them? We will extend this line and we will draw a perpendicular. Okay, so this will give us the distance between this force and this force, right? So now in this case the angle is known, so that's why it will be easier for us to calculate. So this angle is theta, that means this is an similar angle, so this angle will also be theta. Okay, and this side is 2a. 2a is the distance between the dipole, so that is also known. This is 2a, this is this angle is theta, and this is a 90 degree. Because this is a perpendicular, that means this is a 90 degree. So right angle triangle, hypotenuse is 2a. What is the value of the perpendicular? Okay, so perpendicular is given by this distance, say L. So the value of L is given by 2a sine theta. Okay, sine theta is equals to L by 2a. Some people have curly brown hair turned permanently black. Some people have, some means sine, people means perpendicular, have means hypotenuse. So here this is the angle, that means this is the perpendicular. Anything opposite to the angle is perpendicular. So perpendicular by hypotenuse is sine theta. So this perpendicular distance will be hypotenuse into sine theta. Okay, so L value is 2a sine theta. So we know the distance between the forces and we also know the magnitude of both forces. So torque is given by magnitude of any of the forces times the distance. Okay, this is the formula for torque. Torque is given by force into distance. Okay, but when forces occur in pair, then only torque acts. If there is only one single force, there will be no torque. Now force is given by Q into E, and L is given by 2A sine theta, or we can rearrange them as Q into 2A into E sine theta. Now Q into 2A is a fixed quantity for a given dipole, and that is known as dipole moment. So PE sine theta is the torque acting on the dipole. This is it, but after that we can write this same thing in vector notation as P cross E. Okay, P cross E is the vector notation. Now remember, sine theta always appears when there is a cross product. Okay, if it is a cos theta, then it would be a dot product. Also, you have to remember, torque is a vector quantity. Force and dipole moment, they are also a vector quantity. Electric field is also a vector quantity. Now next, write any three properties of electric charge. There are only three properties of electric charge. Now this question can be asked as a 2 marker as well. So additivity of charges. Charges are additive in nature. This is the first property. Quantization of charges. All charges are integer multiple of smallest charge. E is the charge of an electron. Conservation of charges. Total charge in an isolated system is always conserved. So isolated system, you have to mention isolated system. And also, if they ask you, add these lines. Many students add additivity of charges, quantization of charges, conservation of charges, but they do not explain what does it mean. At least add one line to explain what are the meaning of these things. Okay, now next, what is an electric dipole? Define electric dipole moment, give its direction. Okay, so dipole, two equal and opposite charges separated by a small distance is known as electric dipole. Dipole moment. Electric dipole moment is the product of magnitude of the charges and the distance between them. It's a vector quantity. The direction of dipole moment is from negative to positive charge. Write three properties of electric field lines. This is also very common, 2 properties, 3 properties, and even I have seen some colleges during their internal exam, they ask 5 properties. Okay, that is also possible. So electric field lines may start from positive charge and end at negative charge. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. Two electric field lines are never intersect each other. Electrostatic field lines do not form any closed loops. Electric field in free space decreases as we move in the direction of the electric field lines and vice versa. So if you are moving in the direction of electric field, the value of electric field slowly decreases. Okay, and remaining of the points are self-explanatory. If you need any more explanation on this, please mention in the comment section of this video. Now let's continue. Define linear charge density. Mention the expression for electric field at a point due to an infinite line charge and explain the terms. This derivation we will do anyway, but this question is asked in your latest model paper. The linear charge density denoted by lambda is the amount of electric charge per unit length of the charged line or charged wire. Okay, mathematically lambda equals to Q by L. Q is the total charge, L is the length of the wire. So this is how you can define it. Electric field due to an infinitely line charge is given by E equals to 1 by 4 pi epsilon naught 2 lambda by R. Here you have to explain the terms. It is mandatory whenever you are writing an equation, try to explain what are all the terms. E is electric field intensity. So E is the electric field intensity at a distance small r. Lambda is linear charge density. Small r is the distance of the point from the line charge, and epsilon naught is the permittivity of free space. Okay, so this is how you have to write your answer. Now let's move on to the 5 marker section, long answer type 5 marker derivation questions. Derive the expression for electric field at a point on the axis of an electric dipole. So we will be doing 4 derivations, and from these 4 derivations you are definitely going to get, if derivation is coming from this chapter, you are going to get the derivation. So first is electric dipole. So diagram is compulsory whenever if you are doing a derivation. If the diagram is required, you have to draw the diagram. So here, as you can see, 2 charges, minus charge, plus charge is there. The distance is 2a. Suppose this distance is a, this is also a. Okay, this is the midpoint. So if distance is 2a, then this will be a, this will be a. The actual distance from the point where we are measuring the electric field, point P, the distance say r. Okay, so we are trying to find electric field at this point P. Okay, we are trying to find electric field at this point P. First of all, for a given dipole, dipole moment is given by small p equals to q into 2a. So this is the dipole moment. Now first, how to calculate the electric field? So to calculate electric field, what we will do, we will find the electric field due to the positive charge and due to the negative charge individually, and we will try to understand what is the direction of these 2 electric fields, and then basically add them up to find the net electric field. So electric field due to this positive charge first. So what is the electric field due to the positive charge? Let me start here so that I can use this space. So electric field due to the positive charge first. So this is a positive charge, and we are trying to find the electric field over here. So we need this distance. So what is this distance? The total distance from the center of the dipole is small r, and this much distance is a. So this total distance is r, this is a. So that means this distance will be r minus a. Okay, so this will be r minus a. Okay, so E plus electric field, we know it is given by K Q by R square. In this case, R minus A whole square. So if you draw the diagram properly, it will save you time. Also, it will save you to understand the derivation as well. Okay, R minus A whole square. What will be the electric field due to the negative charge? So electric field due to the negative charge will be again K Q by, now in this case the distance we are measuring from this charge, so this distance will be, so this much distance is r, and if you add a value to it, you get the total distance. So this distance must be r plus a. So it will be kq by r plus a whole square. So the values of electric fields are known. Now next is the direction of electric field. So positive electric field is always outward. So positive electric field is always outward, and negative electric field is always towards, right, or inward. So negative electric field is always inward. Now what? So which one is bigger? So the electric fields are in opposite direction. So the net electric field basically will be, net electric field will be one minus another. Now how to find which one, which minus what? So for that we have to find the bigger one. Which one is bigger amongst these two? So electric, if you confuse in the equation, then you have to realize that this positive charge is closer to the point. That means E plus must be bigger, E minus must be smaller. So in this case what we will be doing, we will be doing E plus minus E minus. Now why we are doing negative? Because not because the charge is negative, because the direction of electric field is in the opposite direction. Okay, the direction of electric field is most important thing when you are trying to calculate the electric field. So E plus minus E minus, E plus value is given over here, K Q by R minus A whole square minus K Q by R plus A whole square. Now we have to simplify this. So KQ is common and we get R minus A whole square, R plus A whole square, this comes over here, R plus A whole square minus R minus A whole square. Okay, now what is R plus A into R minus A? That will be given by KQ. And one more mistake I made, not mistake I will say. So this Q is smaller in this question. So let me erase this and rewrite it once. Okay, so that there is no confusion. So this is small q, small q. Okay, so now let me put these values over here, and we realized KQ is common in both cases. So it will be 1 by R minus A whole square minus 1 upon R plus A whole square. Right? KQ is common. Now if you simplify this, you will get KQ. I always write capital Q, sorry for that. This is my habit. So KQ, it will be R square minus A square whole square. Okay, if you multiply these two terms, you will get A plus B, A minus B, that is A square minus B square, but there is a square common, so that is square, and in the top you will get R plus A square, A plus B whole square minus A minus B whole square, which is nothing but 4AB. So you will get KQ into 4RA divided by R square minus A square whole square. Now it's time for a small approximation. What approximation we will be doing? We will approximate that the distance R is bigger than the distance between the charges. Okay, and one more thing that we will be doing here is that K 2A into Q into R, there is also a 2 over here, divided by R square minus A square. So what thing we have done? We have break this 4 into 2 parts. Okay, 1, 2 we have taken inside the bracket, and 1, 2 is outside the bracket. Okay, just a way of writing, right? 2 into 2, 4, still 4. And we have taken the assumption that the value of R is very, very bigger than A. So using these two things, we can write the net electric field is given by K is 1 by 4 pi epsilon naught. Now we have to write the value of K. Now 2A into Q is what? 2A into Q is our dipole moment. So this quantity, whatever is inside the bracket, is our dipole moment, and there is a 2 extra on the outside. There is an R over here, and in the division part, this A is very small. So compared to R square, A square is much smaller. So we can ignore that, and we can write this as R square to the power square, that is R to the power of 4, or this can be written as 1 by 4 pi epsilon naught 2p divided by R cube. 1 R cancels, right? So this is the expression for electric field due to a dipole on its axis. So if you do this derivation, full 5 marks you will get. Now let's next derivation, derive the expression for electric field at a point on the equatorial plane of an electric dipole. Again, diagram is necessary. Here, as you can see, this is the dipole, this is positive, this is negative. Now in this case, the distance is always measured from the center of the dipole. So in this case, this distance is small r. So let's slightly change. Okay, and this angle is 90 degree. That means this is A, this is R, so this distance must be equals to R square plus A square, Pythagoras theorem. Similarly, this will also have the same value. Okay, both will have the same distance. Now let us consider this positive charge. So what will be the electric field due to this positive charge? Electric field due to the positive charge will be KQ by this distance square, that is R square plus A square. Square root, square, they cancel each other, so the only electric field is KQ by R square. What about the negative charge? Negative charge will also be KQ and divided by this distance square. This distance and this distance are same, so it will also be R square plus A square. Okay, so both distances are same, so we have put this electric field. Now if you see that both electric fields are magnitude wise same, what about the direction? So the positive electric field again is away from, positive electric field is always away from, and negative electric field is always towards. Okay, now in this case the electric fields are in complete different directions. Okay, so we cannot simply add or subtract, we have to add them vectorially. So for that, if we take components along this direction and along these two directions, then we will realize that the direction along y will cancel each other, only the direction along x will remain, and fortunately both angles will be same, because this is an isosceles triangle, because this is along the equatorial plane. So if this angle is theta, this angle will be theta, and this angle is theta, this angle is also theta. Okay, these angles are coming in a different ways, but both angles are fortunately same. Okay, so we again will try to find the net electric field. Now we realize that positive and negative both have the same magnitude, so we will say E plus equals to E minus equals to E say. And what is the value of E? E is same as this value. So this is E, this is also E. What is this component of E? The angle is theta, so adjacent component is cos theta, and this is also E, this angle is also theta, this will also be E cos theta. So E net in this particular case will be 2E cos theta. One E cos theta from the positive, one E cos theta from the negative, they gets added and we get 2E cos theta. Now we will put the values of E as well as cos theta. So 2E value is KQ by R square plus A square. Now what about cos theta? So let us consider this triangle. This triangle, this is the angle theta. Okay, cos theta means base by hypotenuse. Base by hypotenuse. So base is A, hypotenuse is square root of R square plus A square. Okay, so everything is done. Now again we have to just rearrange. K is common. Q into 2A. Okay, so this 2 multiplied with this A, so Q into 2A and R square plus A square into R square plus A square square root, so we get R square plus A square to the power 3 by 2. Now again we will use the same approximation, that is R is greater than A. So in that case the net electric field will be 1 by 4 pi epsilon naught. This Q into 2A is our dipole moment. You have to mention that in the derivation, because I have mentioned in the previous derivation. I am not mentioning it in this particular derivation, but you don't make that mistake and you have to mention that in the concurrent derivation as well. Okay, so this will be, and because we are ignoring this A, so it will be R square to the power of 3 by 2, so it will be R cube. Okay, so this is the net electric field due to a dipole on its axial plane. Now here you have to note that the dipole moment is from negative to positive. So this is the direction of dipole moment, but electric field is on the other side, right? So vectorially it can be written that net electric field is negative of 1 upon 4 pi epsilon naught P by R cube. Okay, this is one. Another way, also if you write it, the teacher will be impressed and they will give you full marks. Now next, derive an expression for electric field at a point due to an infinitely long, thin, uniformly charged straight wire using Gauss law. So we have a straight wire, infinitely long, charged, okay, say positive charge, and we are trying to find the electric field at some point P. So for that, first of all, suppose this is my P point, we have to construct an imaginary cylindrical Gaussian surface. Okay, an imaginary Gaussian surface of the distance. So suppose this distance is R, this will be R. The length of cylinder means it has to have a length, so length say L, and the charge density of the cylinder is lambda. Try to use a pencil and compass if possible to make this look better. Okay, now we will apply Gauss's law of electrostatics. So what is the Gauss's law? Gauss's law states that phi equals to Q enclosed by epsilon naught. Okay, again the definition of electrostatic flask says that if electric field, suppose here is given by E, and if we take a small surface area ds, then integration E dot ds is the flux, and if you take the integration throughout the surface along this entire curved surface of the cylinder, this is the total flux, and that is given by Q enclosed by epsilon naught. Okay, now you will realize why Gauss's law is very handy in case of symmetrical surfaces. So in case of symmetrical surface, what is the meaning of symmetrical surface? Symmetrical surface means if you stand along this axis and if you look around you, you will not find any difference because it's a cylinder. Cylinder is symmetrical along the axial line. Okay, so if you look anywhere from that line, you will see no difference. That's why it is symmetrical. So if you can find any symmetry, then electric field will also be symmetrical. Electric field will also have the same value along the surface of all points on the surface of the cylinder. There will be no electric field along this flat surface and the bottom flat surface, but electric field will always present along the curved surfaces. Okay, so because of that we can say electric field is constant, and we can take it outside magnitude of the electric field, and then we write whatever is inside, ds equals to Q enclosed. Now what is the charge enclosed inside the cylinder? Charge enclosed inside the cylinder is basically the charge density times the length. Okay, so charge enclosed is charge density, line charge density into length is the total charge divided by epsilon naught. Now what is the meaning of this closed ds? Closed ds means the total surface area of the curved surface. Now what is the total surface area of a cylinder? Surface area, curved surface area of a cylinder is given by 2 pi r L. R is the radius, L is the length. So 2 pi RL equals to lambda L by epsilon naught. Or we can write the electric field is given by L cancels 1 by lambda by 2 pi R epsilon naught, or we can write it in a fashion 1 by 4 pi epsilon naught 2 lambda by R. This is a fancy way of writing, nothing new. So lambda by 2 pi r epsilon naught, we have multiplied 2 in the denominator and numerator, so this becomes 4 pi epsilon naught 2 lambda by r. Okay. Now last derivation from this chapter, state Gauss's law in electrostatics. Now statement I am not stating, it is already given in 2 marker section. Derive an expression for the electric field at a point outside uniformly charged shell. So here we have a charged shell. Shell means, what is a shell? Shell means it's a cover. Okay, inside is hollow, very thin shell, like egg, covering of an egg. So if you break the cover of an egg, inside the egg is there, but if there is no egg inside, if you make a small hole and if you take out everything inside that egg, then whatever is left, that is considered to be a shell. We have a charged shell. The radius of the shell, say, is given by capital R, but we are trying to find electric field at some distance, small r, and we are using Gaussian law. Okay, so now say the total charge on the shell. There is an advantage of this derivation. If this derivation comes, it is the most easiest derivation. The charge, total charge, you can consider it to be capital Q. Total charge on the surface of the sphere can be considered capital Q. Now what you have to do, you have to construct a Gaussian surface of radius small r. So that is the only thing that you have to do. Construct a Gaussian surface of radius small r, then we can apply Gaussian law. Again, this is a sphere, this shell is a spherical shell, and this is also a sphere. That means this is a spherical symmetry. So for spherical symmetry, what we can say, electric field and each and every point on this surface must be same. So due to So in the last derivation also, if you you have to write that, okay, due to spherical symmetry, the electric field must be constant on the surface of the sphere. Right now, so as you can see, the derivation I have filled half of the board with writing. That means derivation is obviously not that big. So only thing that you have to do, phi equals to E dot ds equals to charge enclosed divided by epsilon naught. Charge enclosed is already mentioned. Now spherical symmetry, E is constant, so it will come out, close integral ds equals to q by epsilon naught. Now what is ds? ds is the surface area of this outer sphere. What is the surface area of a sphere? It is nothing but 4 pi r square, and that is equals to q by epsilon naught, and from here we get E equals to q1 by 4 pi epsilon naught q upon r. Okay, q upon r square, sorry. So this is the expression for electric field due to a Gaussian, due to a point charge. Okay, now let's move on to numerical questions, the most awaited section of this series. 2 point charges plus 4 nanocoulomb and plus 8 nanocoulomb are placed at the points A and B respectively, separated by a distance 0.2 meter in air. Find the magnitude of the resultant electric field at the midpoint O of the line joining A and B. What will be the magnitude of the resultant electric field at O if plus 4 nanocoulomb is replaced by another plus 8 nanocoulomb charge? So we will solve one by one. First let us draw the diagram. So here we have two charges. One is plus 4, let me change the color, plus 4 nanocoulomb, and this one is plus 8 nanocoulomb. Okay, points A and B. Now separated by a distance 0.2 meter. Okay, now what we are trying to do is find the magnitude of the resultant electric field at the midpoint O. So resultant electric field at the midpoint O we are trying to find. So how to do that? The distance of A is obviously 0.1, distance of B is also 0.1, right? Midpoint total distance is 2.2 meter, so it will be half of that. So distances are known. Now we have to find the electric fields due to this plus. This will be in this direction and this plus will be in this direction, but because this charge is bigger, so what we have to do eventually, E8 and E4 we have to subtract them. That's how you can calculate the net electric field. So what is the electric field due to the positive 8 charge? So it will be KQ1 by R square. K is 9 into 10 to the power of 9. Q1 is 8 nanocoulomb. 8 into 10 to the power of minus 9. Distance is 0.1. So 0.1 square. 9 minus 9 cancels and we get 72, and 100 comes from here, so 7200 Newton per coulomb. Okay, divided by 0.1 square means divided by 0.01, that means multiplied by 100. Okay, so if you have any confusion regarding this, just check it once on your own. Similarly, E4 can be calculated as 9 into 10 to the power of 9 into 4 into 10 to the power of minus 9 divided by 0.1 whole square, that is 3600 Newton per coulomb. So what is the net electric field? Net electric field, as I mentioned, both electric fields are in the opposite direction, so there will be a subtraction, and subtraction will happen from the bigger minus smaller, that is 3600 Newton per coulomb. Don't forget to write the unit. Okay, second part, there is a second part. What will be the magnitude of the resultant electric field at O if plus 4 nanocoulomb is replaced by another 8 nanocoulomb charge? So if both charges are 8 nanocoulomb, in that case this is E8, this will also be E8. So part B is if plus 4 nanocoulomb is replaced by another plus 8 nanocoulomb, then both electric fields will cancel each other, right? Equal and opposite electric fields cancel each other. Thus net E will be equals to 0. Okay, so net E will be equals to 0. Let's check the answer, 3600 and 0. Okay, now next question. 2 point charges 5 microcoulomb and minus 5 microcoulomb are located at A and B separated by 0.2 meter in vacuum. Again, also almost similar question. What is the electric field at the midpoint O of the line joining the two charges? Here only difference is charges are equal and one charge is positive, another charge is negative. Let's try this one as well. So this one is 5 microcoulomb now. This one is minus 5 microcoulomb. The distance is again 0.2, but again because we are calculating at the midpoint, so we will say this is point A, this is point B. So this is 0.1, this is also 0.1 because total distance is 0.2 meter. Okay, what is the electric field at the midpoint? Again, we will calculate the electric field due to the positive and negative. Both electric fields will be same. Magnitude wise, direction we have to check. K Q by R square. K is 9 into 10 to the power of 9. So say this is plus. Okay, plus 5 micro means 10 to the power of minus 6, and R square is 0.1 whole square. So 5 in the 45 10 to the power of 3 plus 5, so it will be 45 into 10 to the power of 3 plus 2 5. Okay, so 45 into 10 to the power of 5 is the electric field due to the plus 5. Similarly, electric field due to the negative 5 will also have the same magnitude. Now we have to check the direction. If they are in the opposite direction, they will cancel each other. So positive will be away from, negative will be towards. So in this particular case, both electric fields are in the same direction. That's why I say do not put the sign of the charges when calculating the electric field. That will give you a wrong idea. So first calculate the electric fields and then check the direction of the electric fields. Okay, so from this direction we can calculate the net electric field is given by 45 plus 45 into 10 to the power of 5, that is 90 into 10 to the power of 5, or 9 into 10 to the power of 6 Newton per Coulomb. So this is the net electric field. Okay, now what? Now is, if a negative test charge of magnitude 2 nanocoulomb is placed at O, what is the force experienced by the charge? So this, the midpoint is not P, midpoint is O. So if you place a negative test charge, test charge is negative, and that value is 2 nanocoulomb, what is the force experienced by the charge? So if you place a negative test charge over here, it will experience a force opposite to that of the electric field, that is towards A. So direction is confirmed. Because it's negative, it will be net electric field is in this direction. Negative charges always experiences a force in the opposite direction of the electric field, that is particularly in this direction. So part B, what is the net electric force? Force is given by Q into E. Test charge is 2 nanocoulomb, so 2 into 10 to the power of minus 9 and 9 into 10 to the power of 6, so it will be 18 into 10 to the power of minus 3 Newton. So this is the force experienced by the charge, and the direction is towards or along OB, along OA. Why along OA? Because net electric field is in this direction. So the negative charge will experience a force in the opposite direction. So 9 into 10 to the power of 6 Newton per Coulomb is the net electric field, and 18 into 10 to the power of minus 3 Newton is the resultant electric force. 3 charges each equal to plus 4 nanocoulomb are placed at 3 corners of a square of side 2 centimeter. Find the electric field at the 4th corner. Similar question came in your midterm paper. Okay, let's solve it. So we have a square and plus 4 nanocoulomb charges are placed at 3 corners. Say this one, say this one, and say this one. Nanocoulomb is common. Now we are trying to find the electric field at the 4th corner, that is this point. Now say each side is given here as 2 centimeter. I am assuming each side is A for now. We will put A is equal to 2 centimeter at some point of time. Now, so electric field, how to calculate electric field due to multiple charges? Electric field due to multiple charges is, you have to calculate the electric field due to the individual charges and then add them vectorially. So electric field due to this 4 is along this direction. Electric field due to this 4 is along this direction, and electric field along due to this 4 is along this direction. Now as you can see, because all the charges are same, okay, so this 4 and this 4 are in exactly 90 degrees angle, and their resultant will be along this direction, along the diagonal direction. Okay, this is only because these two charges are same. If they are not same, then it would be lot complicated than this one. Okay, so this is plus 4, this is plus 4, so this is the plus 4 due to this is the plus 4 due to this, and the first we will calculate the resultant between these two, and that is along the diagonal direction, and then we can add the electric field due to the corner one. Okay, what is this distance, by the way? This is A, then this will be A root 2, diagonal of a square. This is A, this is also A. Okay, and A equals to 2 centimeter or 2 into 10 to the power of minus 2 meter. Okay, so this one is given. Now first we will calculate the electric field due to this and this, both are same. Okay, both are same, and that we will say E1. So this is say 1, point number 1, point number 2, point number 3, point number 4. Okay, so electric field at 1 and electric field due to 3 are same, and that value is given by KQ by A square, or 9 into 10 to the power of minus 9. Q is 4 nanocoulomb, and A is 2 into 10 to the power of minus 2 whole square, or 10 to the power of minus 9 cancels, we get 9 into 4 divided by 4 into 10 to the power of minus 4. This 4 cancels, so 9 into 10 to the power of 4 is the these two electric fields. So this is E1, this is E2, this is E3, this is E1. Now magnitude wise both of them are same value. So what is the resultant of these two vectors? When two vectors have same magnitude, what is the resultant? Okay, and the angle between them is given as 90 degrees. So we know that resultant of two vectors A and B is given by A square plus B square plus 2AB cos theta. We have learned that in our PU1. So in this particular case both magnitudes are same, so A and B are same. So in that case A square plus B square, and this 2AB cos theta is 0. Why? Because the cos theta is 0. So cos theta 0 means 2AB is 0. So that means this is 0. Okay. Both are same values and angle is 90. So we get this as square root of 2A square, or A root 2. So when two equal vectors are at right angles, their resultant is A root 2. So when we add E1 and E2, E1 and E3, the net value of E13 is given by any one magnitude times root 2. Magnitudes are same, so that value is 9 root 2 into 10 to the power of 4. So this is the resultant of these two, and it is along the direction of E2. E2 and this quantity, they are in the same direction. Okay, so now the net electric field will be E13 plus E2. Okay, so E13 we have calculated. What about E2? Let me calculate E2 in this space. So E2 is given by KQ by A root 2 square. So everything is same, but there is only one root 2 square extra. That means only what we have to do, this KQ by A square is already known. KQ by A square is already known. That is 9 into 10 to the power of 4. But there is a extra root 2 square in division. Root 2 square means obviously 2. So that is 4.5. 5 into 10 to the power of 4. Okay, so just put that value plus 4.5 into 10 to the power of 4. So 9 root 2 plus 4 root 5 4.5 into 10 to the power of 4. So if you put the value of root 2 and use a simple calculator, you can calculate this electric field is given by 17.22 into 10 to the power of 4 Newton per coulomb. You have to use a calculator to get the final answer, and simple calculators are allowed in your PU board. Okay, now next, a conducting sphere of radius 10 cm has an unknown charge. If the electric field 20 cm from the center of the sphere is 1.5 into 10 to the power of 3 Newton per coulomb and points radially inward, what is the net charge on the sphere? So conducting sphere of radius 10 cm, you can recall the spherical shell derivation. So this was the radius, electric field we calculated. On the side, R is given by K charge on the sphere divided by R square. Now electric field inside the sphere is always 0, same as the spherical shell. Even though we have not derived it, electric field inside the spherical shell is also 0 because there is no charge. For a conducting sphere, all charges stay on the surface. That's why electric field inside the conductor is 0. Okay, so this is the formula that we are going to use. Okay, electric field is given, this distance is given, K we know, right? So E equals to K total charge on the sphere divided by R square. Now here you have to note that the electric field points radially inward. Radially inward means this must be the electric field must be negative. So this value you have to take minus. Okay, so radially inward means obviously the charge is negative, that's why it is negative. So we will use minus 1.5 into 10 to the power of 3. We will not use any negative sign in this unknown values. Okay, they will come automatically. K is 9 into 10 to the power of 9. Q is unknown. Distance is 20 centimeter. That is 20 into 10 to the power of minus 2 whole square. Now from here we have to calculate Q. Q equals to minus 1.5 into 10 to the power of 3 into cross multiply 400 into 10 to the power of minus 4. 20 square is 400 divided by 9 into 10 to the power of 9. Okay, so if you simplify this, you can calculate the net charge on the sphere, which will come out to be 6.67 nano coulomb minus 6.67 nano coulomb. Okay, the negative sign is missing over here, but there will be a negative sign. Okay, and if you miss that out, if you miss that negative sign, you will not get marks. They will deduct 1 mark. Okay, now next question. An uniformly charged spherical shell of radius 10 cm has a surface charge density of 16 microcoulomb per meter square. Find the electric field due to the shell at a distance of 20 cm from the center of the shell, 5 cm from the center of the shell. Now this question is from year 2025. Okay, there was a controversy happened with this question because in the question paper, instead of giving micro capital C meter minus 2, what they have given this as, there was a misprint happened, centimeter to the power minus 2. So this actually means to be microcoulomb per meter square. That is the unit of charge density. But many students thought, what is this unit? So they started with micro or centimeter square, and they mess up in the middle of the question, and they started crying. So board says, okay, if you solve it by assuming centimeter square or you assume it by microcoulomb per meter square, both solutions are correct, and they gave the marks. But many students thought I will not attempt it and I will get full marks, but that did not happen. Okay, so first, uniformly charged spherical shell of radius 10 centimeter. So radius is given as 10 centimeter. And they asked you at two different positions. First is for 20 centimeter, second is for 5 centimeter. What is given here is the surface charge density. Surface charge density given as 16 microcoulomb per meter square. That is 16 into 10 to the power of minus 6 coulomb per meter square. So this is the surface charge density which is given. Now, if surface charge density is given, how can we calculate the total charge? To calculate the total charge, what we have to do, we have to multiply the surface area of the sphere, that is 4 pi r square, and then we multiply the surface charge density. This is the total charge of the sphere. Okay. Now, we know that electric field outside a shell at a distance, say capital R, small r, is given by, electric field is given by 1 by 4 pi epsilon naught, okay, q by r square. Okay, so if you put this value over here, the total charge, you will get 1 by 4 pi epsilon naught into 4 pi r square sigma divided by r square. 4 pi cancels and you get this as sigma by epsilon naught r square by r square. This is another formula that you can remember, or you can come to this equation as I have arrived it. So sigma value is 16 into 10 to the power of minus 6. Epsilon naught is 8.85 into 10 to the power of minus 12. R square is 10 centimeter square. Now here unit does not matter. 10 square divided by 20 square, because centimeter square, they will cancel each other. 10 to the power of minus 2 both cancel. That's why centimeter is not super important. And if you solve it, this entire equation, you will get this as 4.5 into 10 to the power of 5 Newton per coulomb. Okay, so this is the electric field. And second option, this is first option, this is A. What about B? For B, the distance is 5 centimeter. So 5 centimeter is less than that of the radius of the sphere. So if it is less than that of the radius of the sphere, inside the sphere electric field will be 0. So inside the sphere electric field will be 0. So it will be 0. Okay. So last year's PYQ is also I have completed in this lecture. Now last question is from your model question paper. A positively charged spherical conductor of radius 0.1 meter produces an electric field of 1.8 into 10 to the power of 3 Newton per coulomb at a point P distant 0.2 meter from its center. Calculate the magnitude of the charge present in the spherical conductor. Okay, question is similar. Electric field is given, distance is given, and they asked you what is the charge on the conductor. Okay, so electric field is given by K Q by R square. Okay, so Q must be equals to E R square by K. Okay, E value is given 1.8 into 10 to the power of 3, and R value is given here as 2.2 meter. Just careful that this distance must be bigger than the radius. Radius hardly plays any role. For example, last question it did play a role to calculate the total charge. Otherwise, radius only you have to check whether it is outside or inside. okay, divided by K is 9 into 10 to the power of 9, okay, and you will get this as 8 nanocoulomb. Okay, so this will come out to be 8 nanocoulomb. Okay, now second part, also find the magnitude of the new charge produced on the same spherical conductor if 5 into 10 to the power of 10 extra electrons are removed from it. Okay, so here the direction of the electric field is not mentioned, so we can okay, positively charged is mentioned. Positively charged is mentioned, that means this is positively charged, so this must be plus. Okay, second, they are saying that you are removing electrons. Removing electrons means you are making it more positive. So if they say that you have to add electrons, then finally you have to subtract it. Okay, that means you are making it negative. In this case, you are removing electron means you are making it more positive. So by how much amount you are making it positive, that you have to calculate. So this is part A, this is part B. So we know that quantization principle, N into E. Number of electrons that you have removed is 5 into 10 to the power of 10, and we know that charge of an electron is 1.6 into 10 to the power of minus 19. So 1.6 into 5 is 8, and 10 to the power of 10, 10 to the power of minus 19, 10 to the power of minus 9. So this is also 8 nanocoulomb. So you make the sphere positive by another 8 nanocoulomb. So what is the net charge now? So net charge is whatever was the previous charge and how much positive you have made it. So 8 plus 8, that is 16 nanocoulomb. So the net charge of the sphere is now 16 nanocoulomb. So correct answer is 8 nanocoulomb for the first part, 16 nanocoulomb for the second part. This is from your model question paper that is there in this year. There is only one paper has a numerical question from this chapter, and we have solved it. Before I start with today's lecture, I just want to share the new blueprint from this chapter. So basically here they have mentioned 1 mark question. One of the questions will come from this chapter, and one question will come as short answer type, 2 marker. Short answer type 3 marker will be there as 1 question, and long answer type 1 question. Now as you know that in the blueprint they have not mentioned whether this 1 marker will be for MCQ or this will be for your fill in the blanks. Also the clarity of this long answer type, whether it will be a theory based question or a numerical based question, we have no such clarity. Okay, but we know that this chapter is important for MCQs, but we will also practice some fill in the blanks for reference, and long answer type questions will be practiced, both theoretical questions as well as numerical, because this chapter and electrostatic field chapter, they are like coming in a pair. So if theory question comes from the first chapter, numerical question comes from the second chapter, and vice versa. So how many questions we are going to discuss in this session? So we are going to discuss 15 MCQs as usual. We will also discuss 5 fill in the blanks. We will discuss 5 2 marker question, 4 3 marker question, 3 long answer type questions, and also we will be discussing 4 numerical questions as well. So without much delay, let us start with the MCQs first. 2 capacitors of capacitance C1 and C2, C1 not equals to C2, are connected in parallel to an external source of potential difference V. The equation which is not applicable for the given combination is. Symbols have their usual meaning, so let us understand what is the question is talking about. So here we have 2 capacitors C1 and C2. They are connected in parallel with the voltage source V. Okay, so this is how the connection goes. This is C1, this is C2, and this is V. Okay, now they are asking you that the equation which is not applicable. Not applicable means out of these 4 equations, 3 are applicable, so 3 are correct, only 1 is incorrect. That incorrect one you have to identify and answer. Okay, So first of all, if charge stored over here is Q1, here it is Q2, then the total charge in the circuit, whatever is stored Q is equals to Q1 plus Q2. Okay, so definitely this is a correct statement. Now what about V is equal to V1 plus V2? So we know that in parallel combination, if voltage you apply is V, then the same voltage is applied across this and same voltage is applied across the second capacitor as well. So V equals to V1 plus V2 is not correct. So this is our answer. This one is our answer, but we will check the other two options as well. C equals to C1 plus C2. So equivalent capacitance in parallel combination is given by C1 plus C2. So this is a correct statement. And as I mentioned, V1 is equals to V2. We know that in parallel combination, the voltage remains same. In fact, this is equals to the voltage of the battery. So this is also a correct statement. So only incorrect statement is option B. Now let's move on to the question number 2. The electric potential at a point due to a point charge varies with the distance from it as 1 upon r, 1 upon r square, 1 upon r cube, 1 upon r to the power of root r. So electric potential at a point due to a point charge. So electric potential due to a point charge is given by V is equal to KQ upon r, not r square, not r cube, but only 1 upon r. So correct answer is option A. Okay, this question I have taken it from your blueprint. In the blueprint, instead of r they have mentioned distance. So instead of distance I have taken it as r. Okay, that is the only change I have done myself. Otherwise the question is same. Now question number 3. The capacitance of a capacitor is 6 times 10 to the power of minus 6 farad. It is connected to a 200 volt cell. The energy released on discharging it fully will be. So how much energy is released when you discharge a capacitor? Capacitance is given by 6 into 10 to the power of minus 6 farad, and it is connected to a 200 volt battery. Right now, first of all, you have to understand that when you are discharging a capacitor, that means first of all you have to charge it. So when you charge the capacitor, how much energy it can hold? So that much energy will be released when you are discharging it. So how much energy can be stored in a capacitor is given by half CV square, because voltage is given, capacitance is given. So we will use this formula to calculate how much energy it can store. So half into capacitance is 6 into 10 to the power of minus 6 into 200 whole square. Now this question came in 2024 exam. Okay, so this is the PYQ. 3 into 10 to the power of minus 6 into 200 into 200. So how many zeros are there? 1, 2, 3, 4. 4 zeros are there, and 10 to the power of minus 6 is there. So we can write 3 into 4 into 10 to the power of minus 2. Okay, 4 zeros are reduced from this minus 6. Now we have 3 4s are 12 into 10 to the power of minus 2. So that is 0.12 joules. So the energy that is released here is 0.12 joules. Option A is correct answer. So this is a short, very short numerical came in your previous year question. Now, if n identical capacitors of capacitance C is connected in series, then the equivalent capacitance is. So here we have n capacitor, each of them have capacitance C, and you are connecting them in series. So what is the equivalent capacitance? We know that in series combination they add reciprocally, so equivalent capacitance in this case will be C by N. If it is connected in parallel, then the capacitance will be N into C. So correct answer is option C, C by N. Now let's move on to the next question. If charge in a capacitor is doubled, then the capacitance is. So we know that Q equals to CV. So you might think that if I double the charge, capacitance should be doubled. Actually no, capacitance is given by Q upon V, and if you increase Q, the voltage will increase, but the ratio of charge and voltage will remain constant. Capacitance is actually a proportionality constant, and that's why it is a constant. No matter if you change charge, if you increase voltage, the capacitance will remain same. To change capacitance, what you have to do? You have to go to its dimension, that is you have to change the distance between the plates, you have to increase its area, or you can add a dielectric medium between the plates. That's how you can change the capacitance, right? So the formula for changing the capacitance is K epsilon naught A by D. So if you change any one of them, the capacitance will change, but by changing charge or voltage, capacitance will not change. So correct answer is remain same, option C. Question number 6. At the surface of a charged conductor, electrostatic field must be. So at the surface of a charged conductor, we have a charged conductor. And what about the electrostatic field? So they are asking about electrostatic field, not electrostatic potential. So it will be either it will be 0, parallel to the surface at every point, infinity, normal to the surface at every point. We know that from the property of conductors that electric field on the surface of the conductor is not 0, but it is normal to the surface. So it is normal to the surface at every point. This is the correct answer, not 0. 0 is inside the conductor, electric field is 0, but on the surface it is not 0, and neither it is infinite. Okay, next question. The electric field inside the cavity of a charged conductor is 0. This is known as electrostatic shielding. So inside a charged conductor, if you have a cavity, cavity means the cavity that you might have in your teeth, okay, a gap, okay, a hollow space. So cavity means metal is there, okay, outside, but there is no metal inside. This is called a cavity. Okay, cavity means a hollow space where nothing is there. Now if you measure the electric field inside this cavity will be always 0, and that is called electrostatic shielding. Next question. Dash dielectric develops a net dipole moment in the presence of an external field. So which type of dielectric develops dipole moment in the presence of electric field? Presence of external electric field, both polar and non-polar develops dielectric moment. In case of polar, they already have a net dipole moment in molecular level, but in the material level, net dipole moment cancels each other, so net dipole moment will still be 0. But when you apply external electric field, not only the polar ones but non-polar ones both get electrically polarized. So both polar and non-polar will be the answer. Clear? Right? Both polar and non-polar dielectric develops net dipole moment in the presence of external electric field. Next question. What is the total charge on the parallel plate capacitor? So here they have given you a diagram and they asked you what is the total charge on the parallel plate capacitor. So in this case you can see that total charge of a capacitor is given by Q plus minus Q, that is equals to 0. Okay, charge of a capacitor is Q, but total charge always will be 0. Total charge in a capacitor will always be 0, but when we say the charge of a capacitor, we generally take the positive value. So total charge will be 0. Correct answer is option D. Next question. Potential due to a charge Q at its own location is. Potential due to a charge Q at its own location is 0, infinite, between 0 and infinity, minimum. So let's see. So potential due to a point charge is given by K, Q by R. Now at its own location, when the charge itself is located, okay, at its own location R equals to 0. Okay, at the location of the charge, the distance is 0. So if you put distance 0, then you get KQ upon 0, which is equals to definitely infinity. So at its own location, not only potential but electric field is also infinity. Due to a point charge, whenever you are considering a point charge, at the location of its at its location, the field and potential both becomes infinity. The capacitance of an air capacitor is C0. A dielectric medium of dielectric constant K is inserted between the plates. Then the new capacitance will be. So air capacitor, the capacitance is given by A epsilon naught by D. Now when you add a dielectric medium, the same capacitance becomes A epsilon naught by D, so it basically K times C0. So capacitance becomes K times, that's why we use dielectric medium. So correct answer is KC0, option D. Next question. the electric potential at the surface of a conducting charged spherical shell of radius 10 centimeter is 20 volt. The electric potential at the center of the shell is. So we have electric potential on the surface is given by 20 volt on the surface. So if the potential at the surface is 20 volt, then inside the shell will also be 20 volt. It will be constant. Okay, potential is constant inside a shell, inside a conductor. Electric field is 0, but potential is constant. So the answer will be 20 volt. Okay, next question. The values of electric field E and electric potential V at any point on the equatorial plane of an electric dipole are such that, so on the equatorial plane of a dipole, what is the electric field, what is the potential? So on the equatorial plane, electric potential you already know, it is given by E equals to equatorial plane equals to minus 1 by 4 pi epsilon naught P by R cube. Okay, so this is the equatorial plane, potential on the equatorial plane. Now what about electric potential? So electric potential normally at any position is given by 1 by 4 pi epsilon naught P cos theta by R square. This is the general expression, right? Now for equatorial plane, what is the angle theta? For equatorial plane, the angle theta is obviously 90 degrees. So what is the electric potential? So electric potential on the equatorial plane is definitely equals to 0. Okay, so that is a small mistake. This is potential we are talking about. So the symbol has to be that of potential. So this will be V. Okay, so V equipotential at the equatorial plane must be 0, and also it can be proven from the fact that one is positive charge, another one is negative charge. So net potential will cancel each other because distance is same, so it will be 0. So electric field is not 0, but potential is 0. So option C is correct. Electric field is not 0, potential is 0. So option C is correct. Next question. The angle between equipotential surface and the dielectric field is. So angle between equipotential surface and the electric field is. So if there is a equipotential surface, then the angle between equipotential surface and electric field is always 90 degrees. So correct answer is option A. Next question. A spherical conductor of radius capital R is carrying a charge of capital Q. The ratio of the electric potential corresponding to a point on the surface of the conductor and a point at a distance 2r from the center of the conductor are in the ratio. So let's see. Electric potential, the charge that is being carried is plus Q. The radius is given by R, and what will be the potential at 2R? We know that on the surface of a conductor or inside the conductor, electrostatic potential is constant, and that is given by KQ upon R. What about at a distance 2R? It is given by V dash equals to KQ by 2R. As simple as that, only 1 upon R. So V by V dash equals to KQ upon R divided by KQ upon 2R. So it will be 2, and the ratio will be 2:1. Ratio will be 2:1, not 1:2. Order, whenever there is a ratio based question, make sure what is the order. So electric potential corresponding to a point on the surface first, and second is at a distance 2r. So on the surface first, and the second point is next. So that's how you calculate the potential ratio. So ratio based question, the order is very, very important, because you can see 2:1 is there, 1:2 is there. So if you have calculated V dash by V, you might have thought that okay, maybe it is 1:2. So whenever you are solving a ratio based question, make sure that you are correctly calculating the ratio order. Now let's move on to the fill in the blanks. A molecule possessing permanent dipole moment is called dash molecule. So a molecule which possesses a permanent dipole moment is called polar. Let's see if it is given in the option or not. Yes, polar is given, so definitely the correct answer will be polar molecules. Next, the potential due to a dipole depends on dash. So potential due to a dipole can be depends on many things. Let's see the options. Non-conducting, not making any sense. Nanofarad, not making any sense. Distance could be an answer. Let's see. Increases, decreases. So potential due to a dipole depends on increases, decreases. Also not making any sense language wise. So that means the correct answer for this will be distance. So we know that electric potential and electric field both depends on distance. So correct answer is distance. So for example, electric potential due to dipole also depends on the dipole moment, but dipole moment is not given in the option. So make sure that whatever is the correct answer, you make sure that this is making sense and the sentence is complete. As the distance between the plates of a capacitor is increased, the capacitance. So distance between the plates is increased. So what will happen to the capacitance? Whether it will increase or it will decrease. So increases and decreases both are given. So one of them will be answer for this question. Let's see. Capacitance is given by normal air capacitor A epsilon naught by D. So capacitance is inversely proportional to the distance. So if distance is increasing, then capacitance must decrease. So if the distance between the plates of the capacitor is increased, then capacitance must decreases. Capacitance is measured in, so what is the unit of capacitance? So out of all these things, the unit of capacitance is given by nanofarad. So nanofarad is the unit of capacitance. Correct answer will be nanofarad. Dielectrics are dash substances. So dielectrics are actually non-conducting substances. Okay, so dielectrics are non-conducting substances. Now let's move on to the 2 marker section. So now we will be discussing few 2 marker important questions. What is an equipotential surface? What will be the shape of equipotential surface corresponding to a single point charge? So any surface which has the same electric potential at every point is called an equipotential surface. The shape of equipotential surface is spherical for a single point charge, and you also have to draw a diagram. Okay, this is the 2-dimensional representation of a 3-dimensional thing. A spherical equipotential surface becomes circle in 2 dimensions. That's how you can represent it. Next, what factor does the capacitance of a parallel plate capacitor depends? So factors, we know that capacitance is given by Ka epsilon naught by D. Out of that, epsilon naught is an universal constant. So it depends on dielectric, it depends on area, it inversely depends on the distance between the plates. So if you are mentioning over here, you have to mention that capacitance is directly proportional to area. Capacitance is directly proportional to the dielectric, and 3 you can mention capacitance is inversely proportional to distance. Okay, if you write it in terms of word, that is fine. If you are writing in terms of variables, then this equation is must. Okay, then this equation is must, and you have to mention what are all these variables means. Okay, I will tell you that you should write them in terms of words. Okay, capacitance is directly proportional to area, capacitance is directly proportional to the dielectric medium between the plates, capacitance is inversely proportional to the distance between the plates. Now whatever you are comfortable with, you can write, but if you write only like this, teacher may be unhappy. Next, write 2 properties of equipotential surface. Now this question can be as a 3 marker question as well. So in 3 marker you have to write 3 properties. In 2 markers you have to write 2 properties. No work is done in moving a test charge over an equipotential surface. So work done to move a test charge in an equipotential surface is 0. Electric field is always normal to the equipotential surface at every point. No 2 equipotential surfaces can intersect each other. This is similar to the electric field. No 2 electric field lines can intersect each other. Similarly, equipotential surfaces can also not intersect each other. The electrostatic potential energy of a system of 2 like charges is positive explain. So this question is from one of your model paper this year, latest model paper. So let's see. So electrostatic potential between 2 point charges is given by Q1 Q2 by R. So we have two charges, Q1 Q2 and R. Okay, so if two charges separated by a distance r, then that is their equivalent surface. But if you just write this equation, you will not get any marks. Okay, you have to explain why it is positive. When two charges have the same sign, both can be positive or both can be negative. They repel each other. So normally when both charges are of same sign, they repel each other. Like charges repel each other. Okay, due to electrostatic force. To bring these charges closer together, so if I want to make the distance smaller, okay, then what we have to do, you must do work against this repulsive force. Okay, so when charges are repelling each other, they are trying to move away. But what you are trying to do, you are trying to bring them closer. That's why, that means you are trying to apply some force, and you have to apply the force externally. So external force has to be applied to bring them close. And we know that if external force is to be applied, then that work we consider positive. Okay, so work done, this repulsive force, the closer you try to push them, the stronger they repel and more external work you have to do. So that's why the work, the potential energy of a system of charge, potential energy of two similar charge is positive. Okay, now next question, what is meant by equipotential surface? Same question. Okay, draw the equipotential surface for an electric dipole. So this is a new question again from your new model blueprint. Previously the question is to come for a point charge. They have added dipole this year. So almost similar, only thing you have to be careful, equipotential surface is the surface which has the electric potential remains same at every point. So definition is same, but when you are drawing the dipole, make sure that these lines are little closer. These lines are slightly wider. Again, these lines should be slightly closer. This line should be slightly wider. Okay, the gap should be like that. Okay, so how to do that? Positive, negative, and what you can do, you can draw them like that. Okay, you don't need to use a compass. Okay, you can use your hand so that it appears that it is like this. Okay. So make sure dipole, electric field lines of a dipole and equipotential surface of a dipole are separate. So make sure you are doing the correct diagram. Next, obtain the expression for effective capacitance of two capacitors connected in series. So either series or parallel, any one of them can come as a 3-marker question. So first we will start with series. So here we have two capacitors. They are asking you only two capacitors, so no need to add more. Two capacitors is sufficient. So two capacitors, C1 and C2, they are connected in series. They have a battery. This is C1, this is C2. Now what? Now you have to be careful what is happening in case of series combination. In series combination, we know that the current in the circuit remains same. In case of capacitors, instead of talking in terms of current, we talk in terms of charge. So total charge in the circuit remains same. So whatever charge is stored in the capacitor C1, the same charge must be stored in the capacitor C2. So both capacitors should have the same charge, right? Now what? So we will start with the concept of equivalent circuit. Concept of equivalent circuit is when you replace the combination of capacitors using a single capacitor such that everything remains same. That means the charge in the capacitors remains same. Okay, you applied the same voltage. So this is called equivalent circuit. Okay, now first we will see what is happening in each and every capacitor. Suppose the voltage drop across this is V1, voltage drop across this is V2. Okay, we know that Q is equals to CV1 or C1 V1, or V1 equals to Q by C1. This is for the first capacitor. Similarly for second capacitor, we can write V2 equals to Q upon C2. Now what? So this is the voltage across these two capacitors, and you have applied only one external source, that is V. So that means V must be equals to V1 plus V2. Okay, now put the values. V equals to Q upon C1 plus Q upon C2, or Q common, you get 1 upon C1 plus 1 upon C2. This part is done. Now we will do the same mathematics for equivalent circuit as well. Now if you do the same mathematics for equivalent circuit, what you get? Charge stored is Q, C equivalent is capacitance, voltage you applied is V. So Q again is equals to C equivalent into V, or V equals to Q upon C equivalent. So from this equation we will put that over here, and we get Q by C equivalent is equal to Q common 1 upon C1 plus 1 upon C2. So Q gets cancelled, and you get 1 upon C equivalent is equals to 1 upon C1 plus 1 upon C2. This is the expression for capacitance of two series combination of capacitors. Okay, now let's move on. Obtain the expression for effective capacitance of two capacitors connected in parallel. Now same question, only thing is we are using it for parallel combination. And what is common in parallel combination? What is same? What remains same in parallel combination? In parallel combination, the thing that remains same is voltage. Charges vary. So this is Q1, this is Q2, this is say C1, this is say C2, and the voltage that you have applied is V, and the equivalent circuit is everything remains same. The total charge remains same, that is Q, and this is V, this is the C equivalent. Okay, this is the equivalent circuit. Okay, in parallel combination the voltage remains same across both capacitors. So from there we can say Q1 equals to C1 V1, and Q2 is equals to C2 V2, or because the voltages are same, let me just write them as C1V and C2V. Now what is the total charge Q? By the way, total charge Q must be equals to Q1 plus Q2, right? Total charge must be Q1 plus Q2. So that means again for the this circuit we can write that Q must be equals to C equivalent into V. Okay, this is for equivalent circuit. Now we will put that Q over here and these Q's over here. We get C equivalent into V equals to C1V plus C2V. V gets common, C equivalent equals to C1 plus C2. It gets common and gets cancelled as well. So we get C equivalent equals to C1 plus C2. So this is the easiest of the two. Okay, series one is more common in exams because it is slightly tricky. Parallel one is easier, that's why they generally do not ask parallel combination. Now give three results of electrostatics of conductors. Now this question was there in your last year's blueprint, and it is still there in your this year's blueprint as well. So this question, even though this question never came, this might come in your board exam. Inside a conductor, electrostatic field is 0. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. The interior of a conductor can have no excess charge in the static situation. So these are the three properties, three results. Okay, also you can add that if there is a cavity inside a conductor, electric field is 0 inside a cavity. That is called electrostatic shielding. Now derive the relationship between electric field and electric potential due to a point charge. This is one of the VVIP question. Okay, almost every alternate year this question comes. For that, first of all you have to draw this circuit diagram. So you have to draw this diagram first. So this diagram is basically representing the potential at some point V and at some point A and at some point B. Okay, so these are the two equipotentials. We call them equipotentials. So and we have a test charge which is kept at point A. We have a test charge kept at point A, and we are trying to bring this test charge at point B or point P. Okay, I don't think it is P, let me maintain B only. So here we are trying to bring this test charge from A to B, and we will try to calculate what is the work done to bring it. Okay, there is a relationship between work done and potential, so that theory we will try to explore. So what is the initial potential energy of this test charge? Initial potential energy is given by Ui equals to Q into V. Initial potential energy, and as you are moving from higher potential to lower potential, final potential energy is given by Q into V minus delta V. Right, this is the change in potential energy. Now what is the work done? Work done is given by change in potential energy, that is equals to UF minus UI. Remember, always final minus initial. Be it positive, be it negative, does not matter. So Q into V minus delta V plus Q V. So if you calculate it, you will get minus Q into delta V. Okay, minus Q into delta V is the work done to move a positive test charge from point A to point B. Now this is one thing. Now we will use our mechanical formula to calculate work done. Okay, so these two points A and B are very close. Okay, why I am saying that? Electric field at point A and point B are almost same. So if electric field is same, whenever you keep a charge in an electric field, there will be a force acting on it. So what is that force? The force acting on the charge is given by Q into E. Okay, so Q into E is the force that is acting on a charge kept in an electric field. So if you want to move this charge, you have to apply minimum this amount of force to move the charge. Okay, so when you are applying this amount of force, what is the work done to move it by a distance of delta L? Delta L is the distance between A and B. So the work done is given by F into X or F into delta L. Okay, or it will be Q into E into delta L. Now you are calculating work done. So work done, no matter how many methods you use, the work done in both methods should be same. So comparing equation 1 and equation 2, we can say that minus Q delta V must be equals to Q into E into delta L. Okay, these two work done must be equal. So Q gets cancelled and we get E equals to minus delta V by delta L. And in differential form we can write this as dV by dl. Okay, this is the relationship between electric field and electric potential. Okay, now you have to remember that electric field is pointing from higher potential to lower potential. That is why there is a negative sign. The negative sign signifies electric field points in the direction of higher potential to lower potential. Okay. Now, derive the expression for electric potential at a point due to a point source charge. This is a 5-mark question, and this is the most important derivation from this chapter. Okay, almost every year, I will not say every year, but almost every year this question has come in your board exam. Okay, so this is the star question of this chapter. So if a derivation is coming from this chapter, then 90% chance that this will be the question. There are 10% cases, there are some other questions have come, but out of the 3 papers, so if you are applying for improvement exam as well, out of the 3 paper, at least one of them will have this question. Maybe it is your first time paper, maybe it's your second time paper, maybe the third time paper, but this question will come every year. So in that sense, it has came every year. Okay, so first of all, you have to draw a diagram. We have to take a charge, say capital Q, and we are trying to find electric potential at some point R, at a distance R. So at a point P at a distance R from this source charge. Now for that, what you have to do, we have to remember the definition of electric potential. We have to go certain beyond, and we have to add some dots as well. So this is say a point A, this is say a point B, and the distance between them is dx. Okay, they are very close points, close friends. Okay, now what is electrostatic potential? Electrostatic potential is defined as the work done to bring a unit positive test charge from infinity to a point in electrostatic field. Okay, so that means if you take a unit positive charge, okay, a test charge, unit positive test charge, and if you are bringing it from infinity to that point, okay, then whatever work that you are doing is basically the electrostatic potential at that point. Now infinity is a something which is we cannot easily handle, right? Infinity is something bigger than you can imagine. So that's why what we will do, we will imagine an intermediate point at a distance x. We will imagine an intermediate point at a distance x, A, and we will find if I am moving this charge from A to B, where A and B are very close to each other, then how much work I have to do. Okay, then we will extrapolate that from infinity till the point P. That is the process, because infinity is beyond us. Infinity, if we start at infinity, we will not be able to calculate, and that's why the mathematics is developed, the mathematics that is required for physics. If you know, Newton developed differentiation and integration, because physics required integration and differentiation particularly to handle such cases. Okay, so if you start at infinity, you will not be able to solve this problem. So for that you have to take some intermediate point which is actually finite point, then we will extrapolate that. So how to do that? So first of all, we will assume that these two points are very close to each other, so that means electric field is constant at this point. Okay, electric field is constant at this point. Okay, so if you take a charge, say test charge Q, if you keep a test charge at Q, what will be the electric force that will be acting on this? So electric force acting on this charge is given by Q into E. So the force that is acting on this charge is Q into E. Now if you want to move this charge from A to B against the electric field, if you are moving it against the electric field, then you have to apply this much external force to move this charge. So what will be the external force that will be required? The external force that we have to apply must be equals to opposite to that of this force. Okay, this force is, suppose this is positive, this force is trying to take it away, so you have to apply external force which is against this internal force. This is internal force, the external force has to be opposite in direction, that's why minus Q into E, that is the force that you have to apply. Now if you are applying this much force and if you are moving it by a very small distance dx, then what the work that you are doing? The work that you are doing is given by the external force times the displacement. Force times displacement into cos theta. Here cos theta is 0, theta is 0, so cos theta is 1. So F external into dx, this is your work done. Now let's put the value of this Q into E dx. Okay, now this point is at a distance x, so we know from the concept of electric field at a distance x is given by K, this charge capital Q, divided by the distance square and dx. Okay, why? Because electric field is given by KQ by K capital Q by x square, right? Here we are assuming the charge, original charge is capital Q, that's why capital Q we have used here, right? Now what you have to do, you have to just calculate the total work done. Now for here, obviously K, capital Q, small q, they are constants, and what we have is dx upon x square. Okay, so this is the small work that you have done to bring the charge from very small distance B to A. But this is not our work. Our work is not yet done. We have to do more work because we have to start at infinity and we have to calculate the total work. So how to calculate the total work? For that we have to start at infinity and we have to reach our destination point at a distance r, and we have to integrate this entire thing minus k capital Q dx upon x square. Obviously this one is constant, so this one constant means this will straight away come out of the integration, right? Any constant comes out of integration and differentiation, k capital Q small q integration infinity to r. Okay, now what? Now this will be equals to minus k capital Q small q. Now what is the integration of 1 upon x square? Integration of 1 upon x square is minus 1 by x. So when you first started at the beginning, okay, when you just started at a PU2, chapter 1 was over, chapter 2 was over, and teacher was doing this derivation, you thought, what is this integration? Because you had no idea about integration back then. Okay, integration was not yet to be taught to you in your PU board. Most of you, some of the colleges, some students are smart, they already realized, but at that point of time it was very difficult for you to remember. You have to do the integration x to the power of minus 2 plus 1 minus 2 plus 1. Now you are familiar. Okay, 1 upon x square means it is be minus 1 by x, right? So as the time progresses you are improving, so you have to improve with this as well. Okay, so minus and minus gets common and it cancels each other. So k capital Q small q, and we put the value of this 1 upon r minus 1 by 1 upon infinity. Now 1 upon infinity is 0, x by 0 is infinity, something by infinity is 0. Okay, so we get this as k q by r. Now whatever we have calculated is work done, and work done to move a test charge q. What is electrostatic potential? Electrostatic potential is defined by work done to move a charge from infinity to a point by unit positive test charge. So unit positive test charge means here you have to divide this work done by small q. This is the test charge. Instead of taking 1 we have taken q, so finally we have to divide it by q. So we get this as k q by r. Now k value is 1 by 4 pi epsilon naught. Finally when it time for the result, you put the exact value. So before going into a marriage, you dress up, right? You put your best shirt on, your best perfume on. So similarly at the this is the wedding dress. So for wedding dress you have to put up the 1 by 4 pi epsilon naught as a value. Okay, this is starting point 1, this is second stage 2, and this is the final concluding stage 3. Okay, now let's move on. Obtain an expression for potential energy of an electric dipole placed in an uniform electric field. So we have a uniform electric field, and a dipole is placed inside this electric field. We have to calculate the potential energy of this dipole. Okay, so when you place a dipole in an electric field, first of all you have to remember what is the torque acting on it. The torque that we have calculated was given by PE sin theta, right? PE sin theta. Now torque is equivalent to force in rotational motion. Okay, if you remember rotational motion, torque is equivalent to force in rotational motion. So when we calculate the potential energy, we calculated the work done. So potential energy is equals to work done, and what was work done? Work done was given by force into displacement, right? Force into displacement. Similarly, work done can also be calculated by torque into angular displacement. torque into angular displacement can also be work done. That's what we are going to use in this case. So the potential energy is basically, first of all, obviously small potential energy. Small potential energy is equals to small work done, and that is given by torque into d theta is the work done, or Pe sin theta d theta. Okay, so this is the way to calculate the total energy. So total energy must be equals to integration Pe sin theta d theta. Again, another integration that you are struggling with at the beginning. So it is Pe integration. Now integration has to have some limit. In physics, whenever you are doing an integration, it has to be a definite integration. Now we have to, when you are rotating the dipole from some angle and reaching at an angle theta, you are assuming that initially the potential energy at that particular location is 0. Okay, and then when you are rotating it, the whatever final position is, that is the final energy. Okay, so work done means you are moving it, you are rotating this dipole from some initial angle to some final angle. Now in case of potential, we assume that potential, when it is rotated exactly like at an angle 90 degree, the potential is 0. Okay, and from there whatever angle it is gone, that is the final potential. So we will start at an angle of pi by 2 and we will reach our destination theta. Okay, so it will be, why we are taking pi by 2? Because we assume that potential energy is 0 at an angle 90 degrees. We will see that eventually. So from here we get P. What is the integration of sin theta? Integration of sin theta is minus cos theta, and it is pi by 2 to theta, or equals to Pe minus cos theta minus 0. Cos pi by 2 is 0, so we get this as minus Pe cos theta. Okay, now you can start it from 0 as well, does not matter, but this is the easiest way, because we know that potential energy when theta is 90 degree, potential energy is 0. So potential expression for potential energy is minus Pe cos theta, or it is minus P dot E. Both are vector, so finally you have to add the vector form as well. So this is the final result. Okay, remember these steps. This is slightly tricky because this is something which we do not do every day. Okay, electric field, electric force still common, but from rotational motion to work, we generally do not calculate too many of cases. That's why this can be slightly tricky, but if you remember that you have to start from the torque, then you are good to go. Now this question, this is taken from one of your previous year papers. So this question is not a single 5-mark paper, a 5-mark question, but it is a 3+2 question. So 3-mark question was that one. Now this is a 2-mark question. Define energy density of a charged capacitor. How is the energy density related to the electric field present between the plates of the capacitor? So energy density is defined as, energy density is given by small u. It is defined as energy stored in the capacitor divided by the volume of the capacitor. This is called energy density. So energy stored in a capacitor per unit volume is called energy density of the capacitor, and it is denoted by small letter u. Small letter u is given by half epsilon naught E square. The derivation is now out of your syllabus, but this is the relationship between energy density and electric field. So energy density is directly proportional to the square of the electric field. Okay, now Next, another 2+3 question. What is the polar and non-polar molecules? So non-polar molecules are those which the center of positive and negative charges coincide normally. The molecules has no permanent or intrinsic dipole moment. So in this case, positive and negative, they coincide. Polar molecules are those in which the centers of positive and negative charges are separated even when there is no external electric field. Such molecules have permanent dipole moment. So in molecular level, a polar molecule has permanent dipole moment. Example you can add is water. Okay, here the example is carbon dioxide. Carbon dioxide is an example of non-polar molecule, and water is an example of polar molecule. Okay. Now next, derive the expression for the capacitance of a parallel plate capacitor. Again, important derivation. This can be coming as a 3-marker separate question. This can be coming as a part of a 5-marker question, but itself this question will not come as a 5-marker. Okay, this is a 3-marker question. Can be asked in a short answer type 3-marker. It can be asked in a derivation as well. So here we have a capacitor. Area of the capacitor, say A. The distance between the plates, say D. Okay, and you have applied a potential of V across the capacitor. Now the charge which is stored on this capacitor, say this is plus Q, this is minus Q. Okay, the potential that you have applied is V. Okay, now this can be considered as a very large charge sheet. So in case of charge sheet, we know that electric potential near the charge sheet is constant. And what is the electric field near a charge sheet? It is given by sigma by 2 epsilon naught. Electric field is given by sigma by epsilon 2 epsilon naught near a charge sheet. Okay, now electric field here, if you consider the zone number 1, we will get the electric field in zone number 1 is given by sigma by 2 epsilon naught. Due to this positive, should be away from, it will be away from. Similarly, electric field due to this negative will be towards. So sigma by 2 epsilon naught minus sigma by 2 epsilon naught. This is due to the positive charge, this is due to the negative charge, it will be 0. Similarly, if you consider this zone number 2, you will get the same result. So E2 and E1 will be equal, and outside the capacitor plates net electric field will be 0. But if you consider the zone number 3, then you will get something interesting. So in zone number 3, electric field due to the positive charge will be away from, and due to the negative charge will be towards. Okay, so positive and negative both will be in the same direction for zone number 3. For zone number 3, the electric positive and negative electric field both are in the same direction. So the net electric field will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that is sigma upon epsilon naught. So this is the electric field in zone number 3. And the potential that you have applied is applied only in zone number 3. So we know that electric field is given by dV by dL, right, when small voltage difference is there. Here the voltage difference is given by V. So voltage difference is given by V, and the distance is given by D. The distance is given by D. So electric field can be written as V upon D. Okay, magnitude. Okay, so this must be the electric field in zone number 3. So we will use that as well. So V equals to E3 equals to V by D equals to sigma by epsilon naught. Now what is sigma? Sigma is charge density. Charge density means total charge on a plate divided by the surface area. surface area is A, okay, and total charge divided by surface area is the charge density, so we will put that as well. So we get Q by A into epsilon naught, okay, or Q equals to A epsilon naught upon D into V. So we just cross multiplied and we have organized it. Now for a capacitor we know that Q is given by C into V. So this is our equation number 1, this is our equation number 2. So if you compare equation 1 and 2, you will see that Q is common, V is common, only thing that is not common is this, that means this must be equal. So C is given by A epsilon naught upon D. So this is the derivation of the capacitance between two parallel plate capacitor. Okay, easy derivation, not difficult. Practice 2-3 times, you will be able to remember it. Now next, calculate. Now we are time for us to solve some numerical questions. Calculate the potential at point P due to a charge of 400 nanocoulomb located 9 centimeter away. So calculate the potential at point P due to a point charge of 400 nanocoulomb located 9 centimeter away. So this is the location of the charge, this is the point, and the distance is 9 centimeter. 9 centimeter means 9 into 10 to the power of minus 2 meters. So whenever you see a centimeter, you always have to convert it into meters with this formula. Okay, always multiply with 10 to the power of minus 2, you will calculate. So first you have to calculate the potential. So what is the formula for potential? Formula for potential is, let me start from here. Okay, there is a part B as well. So let me start at here. So V equals to K Q upon R. Okay, so K is 9 into 10 to the power of 9. The charge is 400 nanocoulomb and the distance is 9 centimeter. Now cancel, 9 cancel, 10 to the power of 9, 10 to the power of minus 9 cancels. So you get 400 into 10 to the power of 2 or 4 into 10 to the power of 4 volt. This is the electrostatic potential. So potential we have calculated. Now what? Part B. Obtain the work done in moving a charge of 2 nanocoulomb from infinity to the point P. Okay, now we are trying to calculate to bring a charge from infinity to this point P. Okay, so work done is given by, work done to bring a charge from infinity to a point is given by magnitude of the charge times the potential at that point. Magnitude is given by 2 nanocoulomb, that means 2 into 10 to the power of minus 9, and voltage is given by 4 into 10 to the power of 4. So that will be 8 into 10 to the power of minus 5 joules. Okay, or this can also be written as 80 microjoules. Okay, 10 to the power minus 6, 10 microjoules. So 80 microjoules can also be answer. Now the part says that, does it depend on the path along which the charge is taken? So if you see the calculation, the path is not involved. Also you should know that electrostatic field is a conservative field, so it is independent of path. No, answer for the second part, you have to mention a no, it does not depend on the path taken. This is very, very important. If you miss that, 1 mark will be lost. Okay, for just writing this statement you will get 1 mark. Okay, so correct answer is 4 into 10 to the power of 4 volt, 8 into 10 to the power of minus 5 joules, and last part no. So everything you have to answer, otherwise you might lose marks. So be careful. 3 capacitors of capacitances 2 microfarad, 3 microfarad, 6 microfarad are connected in series. Determine the effective capacitance of the combination. So here we have a 2 microfarad, a 3 microfarad and a 6 microfarad are connected in series with some battery. Battery initially is not required. 2, 3 and 6, all of them are microfarad. Now first stage is to calculate the effective capacitance. So how to calculate effective capacitance? 3 capacitor connected in series, so equivalent capacitance will be 1 by C1 plus 1 by C2 plus 1 by C3. Okay, not 2. In case of 2, you know the shortcut, C1 C2 by C1 plus C2, but here we have 3, so we cannot use that shortcut. So 1 by 2 plus 1 by 3 plus 1 by 6. So if you see that microfarads 10 to the power of minus 6 factor we have not used here. Why? Because that is common and our result will also be in microfarad. So now the resultant of them is 6. So 3 plus 2 plus 1. So 3 plus 2 5, 5 plus 1 is 6. So 6 by 6. So it is equals to 1. So C equivalent must be equals to 1 microfarad. So first part is 1 microfarad, done and dusted. Next, find the potential difference across 6 microfarad capacitor if the combination is connected to a 60 volt supply. Okay, so we have to calculate the potential difference across this one. If a 60 volt supply is connected. Okay, so for that we will use this C equivalent and we will find what is the charge that is flowing in this circuit. Okay, charge in a series combination remains constant. So if we replace this circuit using a equivalent capacitance circuit, the charge should be same. Okay, charge should be same. Now what is that charge? So Q should be equals to C equivalent into the voltage that you have applied, and Q is given by 1 microfarad, that is 1 into 10 to the power of minus 6, and voltage is 60. So this is the charge that is flowing through each of the capacitor. Now if the voltage across this 6 microfarad is V, then what is the charge of this capacitor? Charge of this capacitor will again be Q because it is series combination, and that is given by 6 microfarad into the potential across this. Now this is equation number 1. This is equation number 2. So if we compare these two equations, we get 1 into 10 to the power of minus 6 into 60 equals to 6 into 10 to the power of minus 6 into V. Okay, so first thing, calculate the charge. First step is to calculate the charge. Okay, then calculate the charge for equivalent as well as calculate the charge for this. Both charges should be same. Okay, and you just need to compare these two values. One of them will have this unknown V, and then you can easily calculate V. 10 to the power of minus 6 cancels, so V must be equals to 60 by 6, that is equals to 10 volt. Okay, if you have any doubts regarding this numerical, you can mention that in the comment section below. This is easy numerical, just follow the steps and you will get the full marks. Okay, 1 microfarad, 10 volt. In a parallel plate capacitor with air between the plates, each plate has area of 4 centimeter square and the distance between the plates is 2 millimeter. Calculate the capacitance of the capacitor. Take epsilon naught equals to 8.854 into 10 to the power of minus 12. Now you will use this. I personally will use 9. So when you are writing this in an exam, the value of epsilon naught will be given to you. You have to use that, and you have a small simple calculator, so you can calculate it. I do not have calculator, so I will use 9. Okay, so that is my benefit, but when you are solving in the exam, because you have access to a simple calculator, use the exact value. Okay, if this capacitor is connected to 100 volt supply, what is the charge on each plate of the capacitor? So first we will calculate the capacitance, part A. So what is the formula for capacitor? Formula for capacitor is simple A epsilon naught by D. Yes, the same formula that we derived few minutes back. Okay, so here area is given by 4 centimeter square. So 4 centimeter means 4 into 10 to the power of minus 4 meter square. Okay, 1 centimeter is equals to 10 to the power of minus 2 meter. So 1 centimeter square means 10 to the power of minus 2 whole square meter square. So basically you are taking square on both sides. 1 square does not change anything. So that is equals to 10 to the power of minus 4 meter square. So these conversions, if you remember, it will be very, very handy. So area is 10 to the power of minus 4. 4 into 10 to the minus 4. Epsilon naught, as I mentioned, I will take 9. Sorry for that. Okay. Answer will differ by a small margin. The distance between the plates is given by 2 millimeter. 2 millimeter means 2 into 10 to the power of minus 3. Okay, 2 into 10 to the power of minus 3 is millimeter. So 2 2s are 4. So 2 into 9 is 18 into 10 to the power of minus 13, or 1.8 into 10 to the power of minus 12, or 1.8 picofarad. Okay, 1.8 picofarad is the capacitance. Easy. Now next part number B. If this capacitor is connected to a 100 volt supply, what is the charge on each plate of the capacitor? Charge on each plate of the capacitor is given by Q is equal to C into V. C we have calculated this. So 1.8 into 10 to the power of minus 12. Voltage is given by 100. So it will turn out to be 1.8 into 10 to the power of minus 10, or 0.18 into 10 to the power of minus 9, or 0.18 nano coulomb. This is coulomb, everything is coulomb. Okay, so final answer is 0.18 nano coulomb. Easy question, nothing, no rocket science. You apply the formulas, calculate by step, and you will get the answer. So 1.8 picofarad and 0.18 nano coulomb. Okay, now I think this is the last question so far. This question is from your model question paper. This is also from your model question paper. 3-point charges, 3 nanocoulomb, minus 2 nanocoulomb, 4 nanocoulomb are placed at the vertices of A, B and C of an equilateral triangle ABC of sides 0.2 meter. Calculate the potential energy of the system. Also calculate the amount of work required to place the same charges at vertices of an equilateral triangle of side 0.1 meter. So let's see. So here we have 3 charges on the vertices of an equilateral triangle A, B, C. So what is the distance between the sides? Distance between the side is 0.2 meter. Each side is 0.2 meter. Now charges are placed at A 3, B minus 2 and C 4. So this is the system of 3 charges. Now we know that the potential energy between 2 charges K, Q1, Q2 by R. What about 3 charges? So potential energy of 3 charges is slightly tricky, but not super tricky as well. So it is given by K, Q1, Q2 by distance between them plus Q2, Q3 divided by distance between them plus Q3, Q4, Q3, sorry, not Q4, Q3, Q1 divided by distance between them. Okay, so this is the potential energy of 3 charges. Right, now potential energy of 3 charges is given here. Now if you see this, all cases the distance is same. This is R, this is R, this is also R. All 3 distances are same. So we know that for this particular problem, R12 equals to R13 equals to R31 equals to R. So this 1 upon r from each equation will be common, so therefore we can write the potential energy of the system is given by K upon R Q1 Q2 plus Q2 Q3 plus Q3 Q1. Okay, so we will calculate these things one by one. So K by R, I am writing K by R. I will try to calculate this one first. Okay, we will try to calculate this one first. What is the first charge? Q1. Q1 is 3. What is the second charge? Second charge is minus 2 plus minus 2. What is the third charge? Third charge is 4. And first and third charge 4 into 3. Now we will put the value. K by Q minus 6 minus 8 plus 12. So it will be minus 14 plus 12, that is K by Q, sorry, K by Q, no, K by R. So it will be minus 2. So now we will calculate the potential energy. U equals to 9 into 10 to the power of 9, that is the value of K, and distance is 0.2 into 10 to the power of and one more thing, they were all nanocoulombs. So nanocoulomb means nanocoulomb, 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 nanocoulomb. That means here we also have to multiply with the factor of 10 to the power of minus 18. That one we have not done over here. So that also there, because nanocoulomb square is there. Okay, so two charges are getting multiplied, that means nanocoulomb's square is there. So that's why this is turning out to be minus 2 10 to the power of minus 18. So minus 2 10 to the power of minus 18 and minus 2. Okay, so this will turn out to be 1 0, 2 cancels and 1 0 goes up. So 9 into 10 to the power of minus 8. So 9 into 10 to the power of minus 8 is the potential energy, that is joules or 90 nanojoules. Okay, 90 nanojoules. Nanojoules is the potential energy which is of the system, of this system. Now second case, everything remains same. Okay, this is the first case. In the second case, what we have done, this is answer A. In the second case, what we have done, we have from this system we have moved it to another triangle of distance 0.1 meter. Okay, so first we will calculate at this combination what is the potential energy of the system. So this one will become our initial potential energy and this one will become our final potential energy. So we will calculate the final potential energy. What is the formula for final potential energy? Everything is same. Okay, only the distance will be changed. So K by R dash Q1 Q2 plus Q2 Q3 plus Q3 Q1. Okay, now that's why I have done this calculation like this, so that you can write the answer in one line. Okay, this is why you have to be careful, same formulas is being used once or twice. So K value is 9 into 10 to the power of 9, R value is 0.1 meter mentioned in the question. Okay, 0.1 meter, and this one we have already calculated, so we will not calculate once more. So minus 2 into 10 to the power of minus 18. So now simplify, you will get this exactly as 18 into 10 to the power of minus 8 or 180 nanojoules. So 180 nanojoules is the final potential energy of the system. So how much work you have done? The work that you have done is final potential energy minus initial potential energy, that is equals to 180 minus 90 equals to 90 nanojoules. So same formula we are using two times. First we are calculating for the bigger configuration, second time we are calculating for the smaller configuration, and they said what is the work done to take the same charges to the new configuration, that will be final minus initial. And one more thing I missed, there is one thing I missed, is that this will be a negative sign. There will be a negative sign. This negative sign I have missed. This negative sign was here. Similarly here as well there will be a negative sign, and this final result will also be negative. Okay, final minus initial, both of them are negative, minus 180 and minus 90. Okay, so you might be thinking, sir, there is a negative sign you missed. Yes, I missed it, so now I have added it. Okay, so negative 180 minus negative 90, that is plus 90, so that will become minus 90 nanojoules. Okay, so this is the question from your model question paper. So practice this question, maybe similar question will come. So this is slightly trickier than previous year questions and from previous year model papers, but again not super difficult. Only the thing that you need to know one formula, you have to apply the same formula two times to solve this question. Okay, according to your latest blueprint, you can get up to 13 marks from this chapter alone. Okay, and very important thing is that from this chapter you are going to get 1 mark question 1, small answer type question 2 marker 1, no 3 marker question from this chapter, but there are going to be 2 long answer type question from this chapter, and that means there will be at least 1 long answer type theory based question, derivations, and 1 numerical going to be coming from this chapter. So you are going to get 2 questions from this chapter, 1 long answer type theory question and 1 long answer type numerical question. So both will come from this chapter. That's why this is a very important chapter. Now let us see how many questions we are going to discuss in this session today. So 15 MCQs. We will also discuss fill in the blanks 5. Now this chapter may be not that important for fill in the blanks, but we are not sure if MCQ will come or fill in the blanks will come, but I am assuming maybe in case they give you 5 fill in the blanks, and obviously in your preparatory exam there is no such thing that they can give fill in the blanks from this chapter as well. So this I am going to discuss 15 MCQs, 5 fill in the blanks, 6 2-marker questions, 4 derivations, as well as 5 numerical questions in this session. So don't go anywhere. All the questions, all the important questions, as well as your model question paper questions and some important numerical questions I will discuss in this series, in this session. Sorry. Now let us start with a 1-marker session, 1-marker question. In case of metals with increase in temperature, so we are dealing with metals, okay, specifically metals, no other objects. The conductivity decreases, so you are increasing the temperature. So if you increase the temperature, then its conductivity decreases, it becomes a bad conductor. So correct answer is option A directly, but if you are interested you can read the other options. The average speed of conduction electrons decreases. Average speed of conduction electron always increases with increase in temperature. The resistivity increases, okay, conductivity decreases, resistivity increases. The number of conduction electron increases, number of conduction electrons remain same. It does not depend on temperature, only their velocity can change. Okay, now let's move on to the next question. Identify the wrong statement from the following. So wrong statement means there are 3 of the statements are correct, only 1 is incorrect. That incorrect statement you have to identify. The drift speed acquired by free electrons per unit electric field is called mobility. This is the definition of mobility. Mobility means, if you remember, mobility is given by drift speed divided by electric field. So this is the definition of mobility. Drift speed acquired per unit electric field means this E is 1. So this is a correct statement. The conductivity of semiconductors decreases with increase in temperature. This is the wrong statement. Conductivity of semiconductors are not like metals. For semiconductors, its conductivity increases as you increase the temperature. So this is a wrong statement, and wrong statement means this is our correct answer for this question. The conductivity of conductors decreases with increase in temperature. This is a correct statement. Just we have discussed it in our previous question. Alloys are widely used in construction of standard resistors. Actually, nichrome, manganese, their resistivity actually remains constant with temperature increase, almost constant. That's why it is used in standard resistance. Standard resistance means the resistance box that you use for experiments in your laboratory. Let's move on. A wire has a non-uniform cross-sectional area as shown in the figure. A steady current I flows through it. Which one of the following statement is correct? So let's see the figure once. So here we have non-uniform cross-sectional conductor. So here we have an area A and here we have an area B. Okay, as you can see, the area B is much larger than area A. Okay, suppose the drift velocity here is VA, drift velocity here is VB. Current is steady, that means current is constant. Now we know that current is given by NEAVD. So current is constant, that means N constant, E constant, I constant. So only A and VD is changing over here. So from continuity equation we can say A into VA must be equals to B into VB. Okay, so higher the area, smaller will be drift speed. Smaller the area, higher should be drift speed. This is constant. That means here, as you can see, that area is smaller, that means drift speed will be bigger. Here area is bigger, that means drift speed will be smaller. Now let's see the options. The drift speed of electron is constant. Obviously not. As we can see, drift speed is changing with depending upon area. The drift speed of electron increases while moving from A to B. So now see, VA is definitely greater than VB, right? Why? Because area is smaller. Area smaller means drift speed will be bigger, right? So that means as you are moving from A to B, drift speed is actually decreasing, not increasing. The drift speed of electron decreases while moving from A to B. This is the correct statement. So we will mark this. The drift speed of electron varies randomly, which is obviously a random option, not correct answer. Now let's move on to the next question. The resistivity of metallic conductor dash with decrease in temperature. Okay, so the resistivity of metallic conductor dash with decrease in temperature. So resistivity, what happens if you decrease the temperature, resistivity also decreases because we are dealing with conductor. Okay, so resistivity decreases, not increase, not randomly increase, decrease. It does not happen like that. So if you are decreasing the temperature, resistivity will decrease, conductivity will increase. Kirchhoff's junction rule is a reflection of conservation of charge. Okay, conservation of charge. Kirchhoff's loop rule is a reflection of conservation of energy. Loop rule is energy, junction rule is charge. The value of internal resistance for an ideal cell. Ideal cell means ideally two options can be possible, either 0 or infinity. Now for ideal cell, the internal resistance should be 0. Next, when current flows through a conductor, its temperature increases, decreases, remains same, may increase or decrease. Now when current is flowing through a conductor specifically, the temperature will always increase because we know that Joule's heating law, H equals to I square RT. So as the current is flowing, heat is being developed from Joule's law, so that means conductors will heat up, that means its temperature will increase. SI unit of current density. Current density is given by J is equal to current divided by area. So its SI unit will be ampere per meter square. Okay, so correct answer is ampere per meter square, not ampere per meter cube, not ampere per meter, but ampere per meter square. The magnitude of the drift velocity per unit electric field. So magnitude of drift velocity per unit electric field, we have seen that in one of the previous question. It is called mobility. So mobility is given by drift velocity per unit electric field or drift velocity divided by electric field. Okay, so this is called mobility. Which of the following characteristics of electron determines the current in a conductor? Thermal velocity alone, drift velocity alone, both thermal and drift velocity, none of the above. Now, just to remind you, current in a conductor is given by NEA VD. There is no thermal velocity component over here. That means current in a conductor depends only on drift velocity. No thermal velocity is involved over here. Okay, thermal velocity, current in a circuit is independent of the thermal velocity. Next question, a piece of metal is to be converted into a rod of highest resistance. Which of the following is the best choice for the length L and diameter D? So we know that resistance of a conductor is given by rho L upon A. Now what is A? A is area, which is given by pi r square, or it is given by pi d by 2 square, or pi d square by 4. Okay, so from this we can say that resistance is directly proportional to length and resistance is inversely proportional to square of the diameter. Okay, if you put this, you will get it. Okay, so if you have any doubt, rho L by pi d square by 4 or 4 rho by pi L by d square. Now this is constant, so only it is proportional to L, it is proportional to 1 upon d square, or inversely proportional to square of d. Okay, so basically if you want to have highest resistance, the length should be highest and diameter should be smallest. That the combination we should look. So in the given combination, if you see that highest length is 2L and smallest diameter is d by 2, so this should be the option where you should get the maximum resistance. Okay. For highest resistance, for smallest resistance, length should be smaller and diameter should be maximum. This is smallest. Okay, from the given option, this should be smallest. Okay, if the same question is asked with the smallest resistance, in that case you have to remember that length should be smallest, diameter should be largest, so that resistance is smallest. Okay, from this option, highest length, smallest, diameter is the highest, because in the question it is mentioned highest. So now let's see question number 12. A steady current I is flowing through a conductor of uniform cross section. Which of the following is conserved? Conservation of momentum, conservation of current density vector, conservation of charges, conservation of energy. Now in case when a current is flowing in a conductor, always charges are conserved. That's why we say Kirchhoff's junction rule. Current is always involved with Kirchhoff's junction rule. That means charges are conserved. So option C is correct. Now next question, a wire of length L is stretched to double its length. So whenever a wire is stretched, okay, what happens is that whenever you are stretching the wire, okay, its length increases but its area decreases proportionally. Okay, so if length becomes 2L, so suppose this is L, this is A, then once the length becomes 2L, the area will be proportionally be halved. Okay, so when area length increases to 2L, area becomes half, and the resistance, new resistance, is actually N square R, where N is this factor. For this problem, this is N, so resistance will be 2 square R, that is 4R. So resistance will be 4 times. Okay, resistance of the wire will be quadrupled. Quadrupled means 4 times. Quad means 4. Okay, quadrupled means 4 times. Okay, so resistance will be quadrupled. Resistivity remains same. Okay, resistance becomes quadruple. Resistivity only depends on material as well as only temperature. Okay. Now let's move on. Ohm's law is applicable to diode, transistor, electrolyte, conductor. Ohm's law is only applicable to conductor. These are non-ohmic conductors, so the Ohm's law is not applicable to them. As the temperature increases, the resistivity of metals increases and semiconductors decreases. So as the temperature increases, the resistivity of metals decreases and resistivity of metals increases and that of semiconductor decreases. So option A is correct. Okay, that means metals become poor conductor and semiconductors become better conductor. Resistivity decreasing means it is becoming a good conductor. So semiconductor is becoming a good conductor, whereas metals resistivity increases, that becomes a bad conductor. Okay, so all the MCQs are over. If you have any doubt regarding any MCQs, please mention that in the comment below. In a current carrying conductor, the net charge is dash. So in a current carrying conductor, the net charge is, if you see that, it is 0. Net charge of a conductor whenever it's carrying current is 0. So correct answer is 0. The magnitude of the drift velocity per unit electric field is called mobility. So correct answer is mobility. The SI unit of dash is ohm meter. So what is ohm meter, by the way? Ohm meter is the resistivity. Okay, ohm meter is given by resistivity, so it is electric resistivity. From the option, it must be electric resistivity. Next, the resistivity of certain metals or alloys drops to 0 when they are cooled below a certain temperature. This phenomenon is known as superconductivity. So there are certain materials whose resistivity becomes 0, it becomes the perfect conductor, and that happens for superconductors, and this phenomenon is called superconductivity. The Kirchhoff's loop rule is based on conservation of energy. Okay, loop rule is based on energy, junction rule is based on charge. Now let's move on to the 2 marker section. Define the drift velocity and mobility of free electrons in conductors, or define mobility, mention is SI unit. So these are both common questions. Let's see. Drift velocity is given by the average velocity with which free electrons drift under the influence of an electric field is called drift velocity. Very important to remember, it is always happens when there is a electric field is involved. Now mobility, the mobility of free electrons is defined as the drift velocity of the electron per unit electric field applied. That means mobility is given by drift velocity divided by electric field, and its unit is the unit is very interesting, meter square second to the power minus 1, volt to the power minus 1, or meter per second Newton to the power of minus 1 coulomb. How to remember this, by the way? So we know that mobility is given by Vd by E. So mu is given by Vd by E. Now what is Vd? Vd is drift velocity or drift speed. So what is the unit of speed? Unit of speed is meter per second, and division is electric field. So what is the unit of electric field? Unit of electric field is volt per meter, or you can say Newton per coulomb. Any one unit is sufficient, so Newton per coulomb. So what is the unit of mobility? Unit of mobility will be meter, okay, second minus 1, this is minus 1, Newton to the power minus 1, because this is in the division, and coulomb. Coulomb was division of division, that means it becomes plus 1. Okay, so this is the common unit of drift velocity. Now let's move on. Mention 2 limitations of Ohm's law. Very common question. Ohm's law is applicable only if all the physical conditions remain same. Ohm's law is not applicable at very low and at very high temperature. Ohm's law is not applicable to non-ohmic devices like semiconductor devices, discharge tube, etc. Okay, so these are the 2 limitation. Any 2 you can write, but if this question comes as a 3 marker, I have given is 3. Anyway, from this chapter 3 marker question is not going to come, so any 2 you can remember. Now next, give any 2 differences between current and current density. So difference between current and current density: current is defined as the amount of flow of electric charge per unit time, whereas current density is the amount of current per unit area. Now unit of current is A, unit of current density is ampere per meter square. Name two factors on which the resistance of a metallic wire depends. Okay, so resistance is given by rho L by A. So it is directly proportional to length, that is R is proportional to L. Now do not write this only R proportional to L, you have to write it in, you are getting 2 marks, right, for just doing this. So please write it in a sentence. And inversely proportional to area. That means R is inversely proportional to area. Okay, so these are the 2 factors on which resistance of a wire depends. Next, name the mobile charge carriers in metals. Write the expression for mobility in terms of average collision time or relaxation time for charge carriers. Now this is a new question from your latest blueprint. Electrons are the mobile charge carriers in metals. We know that, not anything else, only electrons can carry electricity in a metal. Mobility in terms of relaxation time, tau is given by mu is equal to E tau by m. Okay, E tau by m. E is the charge of an electron, m is mass of the electron. Okay, so this is the common form. State and explain Ohm's law. Ohm's law, this is also generally did not came, but this is given in your new model paper, so it might come this year. So if temperature and other physical conditions remains the same, the current I through a conductor is directly proportional to the applied potential difference. V is proportional to I, or V is equals to R. V is equal to IR. The constant of proportionality R is called the resistance of the conductor. Okay, so this is the statement and this is the explanation. Now let's move on to the 5 marker derivation section. 2 cells of different EMFs and different internal resistances are connected in series. Derive the expression for effective EMF and effective internal resistance of the combination. This is one of the easiest derivation. Okay, among all the derivations that we are going to do, this is the easiest derivation. So here we have 2 cells, epsilon 1, epsilon 2, R1, R2, and we have an external resistance R. The current in the circuit, say I. So this is the original circuit. Now original circuit is we are not interested, we are trying to find the equivalent circuit. So that means equivalent circuit will have only one EMF source, only one internal resistance. External resistance will remains the same, R. Okay, so epsilon equivalent and R equivalent. Okay, so these are the combination that you have to be careful of. Current in the circuit should remains the same as it was in the previous case, that is I. Okay, now we will apply Kirchhoff's laws and we will see what is the relation. So current I is passing through all the resistors. Okay, they are all connected in series. That means all the resistors should have the same current I. So we will apply Kirchhoff's laws in the original circuit. So this is say circuit number 1, this is say circuit number 2. Okay, so we are applying KVL in circuit number 1 and we are getting IR plus IR1 plus IR2 equals to epsilon 1 plus epsilon 2. Okay, Kirchhoff's law says that we take voltage drop across each and every resistors according to the direction of current. If they are going in the same direction, everything will be positive, plus, and if, in between if you are going in the opposite direction, then it will be negative. But here everything is in the same direction, that's why everything is positive, and that is equals to EMFs of one or two EMF, whatever is connected. Now if you see that both the EMF are connected, cells are connected such that they are sending current in the same direction, that means they will be simply be added, or IR equals to epsilon 1 plus epsilon 2 minus I into R1 plus R2. This is equation number 1. Okay, so this is our equation number 1. Now we will apply the same, applying KVL in circuit 2. So now we will apply KVL in our circuit number 2, and initially it will be same IR plus I into R equivalent equals to epsilon equivalent. Only one equivalent is there, so IR in this case will be epsilon equivalent minus IR equivalent. Okay, so now this is our equation number 2. So if you compare equation 1 and 2, our left hand side is same. On our right hand side we have something minus something, here also something minus something, and one of them has a term current involved in it, and another one has only EMFs. So if you compare these two, so we can write comparing one and 2, we get epsilon equivalent must be equals to epsilon 1 plus epsilon 2, and R equivalent must be equals to R1 plus R2, right? So this must be equals to this, and this must be equals to this, okay, because they are same equation. So from there we can compare and we can say this is the correct derivation. So easy derivation, not super long, not super difficult. So this is, if you do that, you will get full marks. Now next, obviously circuit diagram is compulsory in this derivation. Next, move on. Derive the expression for effective EMF and effective internal resistance of two cells of different EMFs and internal resistances connected in parallel. So here we have two cells connected in parallel. Epsilon 1 R1, epsilon 2 R2, and because they are connected in parallel, the equivalent resistance in question should be connected in parallel as well. This is the original circuit, say circuit number 1, and the equivalent circuit is given by only one. Equivalent circuit is always the same, okay, only one equivalent resistance, equivalent EMF, and the resistance R. Okay, so now what we will do, we will do the same thing, apply the KCL and KVL, but in this case if you notice, here we have I1, here we have I2, and the total current in the circuit is given by I1 plus I2, that is equals to I, say. So here in this case I1, I2 will be not there, only I current, that is the sum of these two current will be there. Okay, so first we will take the outer loop, okay, from in circuit in CKT1 there are two loops, okay, if you name it, it will be very good, A, B, C, D, E, F. So first we will take A, C, D, F. A, C, D, F, A. Okay, A, C, D, F, A. What we are getting? Current passing through this resistor is I1. Remember that whatever current is coming out of a cell, same current should always go back to the cell. So anything is directly attached to the cell, it will always get the same current whatever is associated with that cell particularly. So I1 R1 plus, because we are skipping this cell altogether, we are going to the resistance directly, we can write IR equals to epsilon 1. Okay, only one EMF is connected in this loop, okay, loop. And second we will apply the same thing in loop B, C, D, E, B. B, C, D, E, B. We will get the similar thing, I2R2 plus IR, I capital R equals to epsilon 2. Now if you see these two equations, you will notice that we are trying to find the total current I. I1 and I2, if they are alone, we can calculate I. But because they are associated with this R1 and R2, we need to simplify them a little bit. So how to do that? We will divide each and every term with resistance R1. So we get I R by R1 equals to epsilon 1 by R1. Okay? Or, okay, let me leave it like that. Similarly, we can get here I2 plus IR by R2 equals to epsilon 2 by R2. Okay, so now this is our equation 1, this is our equation 2, and we will add them. So 1 plus 2. By doing 1 plus 2, what we are getting? I1 plus I2 plus IR is common. So IR is common and we get 1 upon R1 plus 1 upon R2 equals to epsilon 1 by R1 plus epsilon 2 by R2. Okay, so this is our first step. Now what we will be doing? We will be trying to do what? We know that this is equals to I. So let me write that I plus IR 1 upon R1 plus 1 upon R2 equals to epsilon 1 by R1 plus epsilon 2 by R2, or IR equals to epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 upon R1 plus 1 upon R2 minus I divided by 1 upon R1 plus 1 upon R2. So we have taken this I on the left hand side and everything we have divided by this term, because we are, whenever you are trying to find the equivalent EMF and equivalent resistance, always you need to calculate is IR. Okay, now we will apply the same Kirchhoff's laws, KVL, in the equivalent circuit. So from circuit number 2 we can write IR plus IR equivalent equals to epsilon equivalent. Or now this is our equation number 3, let me name it. So IR is equals to epsilon equivalent minus IR equivalent, and this is our equation number 4. So now if you compare the equation 3 and 4, we can see this is the independent term without I and this is the term with I. So by comparing 3 and 4, what we can say that the equivalent EMF must be given by this entire term. So equivalent EMF is given by epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2. Similarly, R equivalent is given by 1 by R equivalent is given by, because it is in division, so that's why 1 by R equivalent is given by 1 by R1 plus 1 by R2. So see here R is in multiplication, here R is in division. So that means you have to convert it into division by doing 1 by 1 by R. Okay, so 1 by R equivalent is this. Okay, so this is a slightly lengthy derivation, but not super difficult. If you practice it 2 to 3 times, you should be able to do it. Okay, practicing is the key for mastering this derivation. Okay, previous one was easy, this one is slightly tricky because you need to remember the steps. If you forget it, you will not be able to do it. Now let's move on. Arrive at the balance condition of Wheatstone bridge using Kirchhoff's rules. So this is the most common, came in the previous years. Okay, but this year, particularly in 2026, this may not come. Be cautioned about this, because in 2024 it did not came, main exam, first exam. Okay, but it came in 2025. So 2026, there is a chance some other question might come, namely the parallel combination of cells, series combination of cells, or whatever we are going to do the next, that is taken from your model question paper. But again, remember that this year it may not come in the first exam. Okay, there is a possibility, 50-50 chance is there. Okay, so don't tell me that later on. But I am not saying this is not important. This is the most common question. Other questions have come and gone, but this question is always the charm. Okay, there is a galvanometer. So you will name A, B, C, D. This is our P, this is our Q, this is our R, this is our S. Wheatstone bridge. Wheatstone is the name of a person, and this is called bridge because this was used to measure unknown resistance. There was a gap there in S, so unknown resistance can be measured using that value. That's why it is called bridge. Okay, bridge means it's not the bridge that you cross. Okay, because there was a gap there and unknown resistances used to put between those two gaps, so it is said that resistances are bridging the gap, and that's why it is called a bridge. Okay, when I was a student, even this was as a part of our experiment as well. Nowadays it is not there. Okay, anyway, so P, now you have to see that what is the balanced condition of a Wheatstone bridge. The balanced condition of a Wheatstone bridge condition is, what is the balanced condition? Ig must be equals to 0. So balanced condition of a Wheatstone bridge is Ig, that is the galvanometer should not have any current passing through it. So the balanced condition means the current through this galvanometer must be 0. That means if current I1 is passing through this, at this junction no current passing through this, means entire current I1 must also pass through this one as well. Similarly, if I2 current is passing in this direction, then the entire I2 current should also pass through this, because no current is being added or subtracted from G. So first you write this. What I am going to do is the smallest or shortest derivation of this condition. Okay. Now first we will take the loop A, B, D, A. So from loop A, B, D, A. So when you are using loop A, B, D, A, we see that how many resistances are there? I1 into P plus current through this is 0, so G into 0 plus, now when we are going from B, D, A, okay, AB in this direction, BD in this direction, DA is, when we are going from D to A, if you see that the current is going in this direction, but our loop is moving in a circular way, so this is a opposite direction of the current. That means it will no longer be plus, it will be a minus, and it will be minus I2 into R, and that is equals to 0, or I1P equals to I2R, or P by R equals to I2 by I1. This is our equation number 1. Now if you see that current through P is I1, current through R is I2. So P is in numerator on the left hand side, whereas I1 is in the denominator. Similarly, R is in the denominator, I2 is in the numerator. So that means it's a inverse relation. So because of that, we can write similarly from loop B, C, D, B, B, C, D, B, we can write that Q by S. What is the current through Q? Current through Q is I1, and where is Q is located? Q is located in the top, so I1 must be in the bottom, and current through S is I2, S is in the bottom, so I2 must be in the top. Okay, so this is our equation number 2. Right, clear? That's how you can write similarly, because everything is similar. So comparing 1 and 2, comparing 1 and 2, P by R must be Q by S, both have same on the right hand side, so P by R must be equals to Q by S, or P upon Q equals to R upon S. This is the condition for balanced Wheatstone bridge. Very simple, very easy derivation. Okay, this is the smallest or shortest derivation. In your college, in your textbook, in your teachers, they will do a longer form of derivation, but this will also give you 5 marks. That will also give you 5 marks. If you can do it in a shorter way, why to do it in a longer way? Right? That is my thing. Now let's move on to the numerical. One more derivation is there, sorry, one more derivation. This is also taken from your latest model paper. Assuming the expression for drift velocity, derive the expression for conductivity of a material. Sigma is equal to n e square tau by m, where symbols have their usual meaning. Now this question I have not seen in the first paper, but this question is very common in second and third paper. Previously also improvement exams used to be held. From last year onwards, they have legalized the improvement. There is no improvement or supplementary exam. They have directly made it. You can attempt as many times as you want. Previously it was only if you have failed in the first paper, you should be able to attend the second or third paper. Now this is no longer there. You can consider them as improvement. Even if you want, so you got 90, you want to get out, you can still attempt the second one. Previously it was not there, but as I mentioned, this question never came in the first paper, but in the second and third paper this is a very common question. Maybe this year they will give this as a first paper question, who knows. So let's see. The derivation is not difficult. Assuming the expression for drift velocity, derive the expression for conductivity of a material. Sigma equals to n square tau by m. So drift velocity means what? Drift velocity is given by I equals to n EA VD. That equation we will use. Okay, nothing else. NEA VD, the simplest equation. Okay, or I upon A equals to NEVD. We have taken this in on this side. Now what is I by A? I by A is called current density. So current density is NEVD. Now we know that alternate form of Ohm's law is J equals to sigma E. Right? J equals to sigma E. So from Ohm's law we will put sigma E equals to NEVD. So if you remember, we are trying to find the sigma, that is conductivity. So sigma equals to NEVD by E. Now VD by E is drift velocity per unit electric field, that is, this is the term called mobility. So this is mobility, so NE mu. Okay, now if you have remembered the short answer questions, mobility was given by E tau by M. E tau by M. Okay, so we will put that over here. Sigma equals to NE into E tau by M, or NE square tau by M. So this is the derivation, this is the formula that we are trying to derive. Okay, so this is how we have done the derivation. Very easy derivation, nothing difficult. Only critical thing you have to remember this and this. So if you follow these steps, you can answer this derivation. The no complication is over here. you have to start with I is equal to NE VD. From there divide by current, get the current density and do it. So this is an easy derivation, that's why it is given to the second and third paper, so that weaker student can also attempt, but they always practice this derivation, that Wheatstone bridge derivation, and it did not came, and many students failed again in the second paper as well. So you have to practice all the derivations so that you are prepared. Now let's move on to the numerical questions. A copper wire of length 50 centimeter and diameter 1 millimeter carries a current of 3 ampere. The number density of free electrons of copper is 8.5 into 10 to the power of 28 meter cube. Calculate the current density, drift velocity of free electron, and the time taken by the electrons to drift from one end to the wire of the other end. A similar question was there in the last year model paper. This is directly from your this year's model paper. Only current density was not asked, otherwise these two was asked, and the values was slightly different. Now this kind of questions is always required to use calculators. I have seen this trend in your PU exam. The questions are asked such a way that you have to use calculator to solve it, but I recommend you do not use the calculator for everything. Try to solve it as much as possible, then use the calculator. So we know that what is first task? First task is to calculate the current density. So what is current density? Current density, this is first part A. Current density is given by current divided by area. Now current is given over here 3 ampere. Area is not given. Instead diameter is given as 0.1 millimeter. So we have to calculate the area. So how to calculate the area? Area is given by pi r square or pi d by 2 square. This is the area of a circle. Your cross section of a conductor is a circle, so that's why we are using this formula. Now what is the value of pi? The value of pi is 3.141. Diameter is 1 millimeter. So 1 millimeter means 1 by 2 into 10 to the power of minus 3 meter. So don't forget to convert the unit. So main problem that student faces, the question is easy, they forget to change the unit. So every time you are solving it, you have to change the unit. Okay, so it will be 3.14 into 0.5 into 10 to the power of minus 3 square, or 3.14 into 5 into 10 to the power of minus 4 whole square. So I have taken this decimal and put it on the 10 to the powers value. So it will be 3.14 into 25 into 10 to the power of minus 8. Square was there, so we have broken the square. This will be 78. This will be 78, approximately 78.5 into 10 to the power of minus 8. Okay, you can use the calculator and calculate this value. So area we have calculated. Now it's time for us to calculate the current density. Current is 3 divided by 78.5 into 10 to the power of minus 8, which will be, I think, some 0.38. I'm think it is with 0.38 into 10 to the power of 8. Okay, or let me see, 338 into 10 to the power of 6. Okay, and unit will be ampere per meter square. Okay, so this by this 0.38 10 to the power of minus 8 goes up, and it will be 38.10 to the power of 6. You can use the calculator to calculate the exact value. So part 1 is done. Next is part B. Part B is drift velocity of the electron. So we know that current is given by NEAVD. So from there we will not use this, by the way, we will even simplify this, NEAVD, or VD equals to I upon A divided by NE. Okay, why I have taken I upon A separately? Because I upon A is our current density, so we will put the current density value directly and the value of NE directly. So let's see. So VD equals to, current density is 38, I think it will be 3.8. There is a mistake over here. This will be 038, 3.8. Okay, 3.8 into 10 to the power of 6. Okay. Because I am not using calculator, I am relying on my memory. Okay, it will be 3.8. So 3.8 into 10 to the power of 6 divided by number density of electron is given 8.5 into 10 to the power of 28 into charge of an electron 1.6 into 10 to the power of minus 19. You will get some value. We will see the value in a while. Now next is you have to calculate the time taken by the electrons to drift from one end to other end. So that is point C. So to time taken by the electron to drift from one end to other is given by time equals to the distance or the length of the wire divided by the drift speed. Okay, length of the wire is given by 50 centimeter, that is 50 into 10 to the power of minus 2 meters divided by drift speed. Okay, and if you calculate everything, you will get that this will be 2.8 into 10 to the power of minus 4 meter per second, and this will be coming out to be 1.8, approximately 1.8 into 10 to the power of 10 to the, this will be plus, sorry, this is plus 10 to the power of 3 second. Okay, okay, so this will be plus. So if you see that the time taken by the electron to reach from one end to another is very, very high. So this is the approach. First you calculate the area, next you calculate the current density, and using the current density you can calculate the drift speed. If current density is not asked, you have to calculate the area and directly put these values over here and calculate the drift speed, and then time taken. Time taken is length divided by drift speed. Okay, S is equal to Vt. So from there T equals to S by Vt. Now what is S over here? S is the because current is traveling from one end of the wire to other end, that means electron which starts here, it has to travel the entire length of the wire. So that is the distance traveled by the electron. Okay, understood? Formula based problem, nothing else, but calculation is you require a calculator. Now let's move on to the next question. Calculate the power dissipated in the 10 ohm resistor in the given circuit. This is also taken from your model question paper, circuit theory based question. You can solve it in two ways. One is a shortcut way that I am going to do in this lecture. There is a longer way. So in that case you have to calculate the current through each parts and then add them. So current, suppose the current through this is I1, current through this is I2, current through this is I3. Okay, then we can, from Kirchhoff's laws, we can say I2 is equals to I1 plus I3. Okay, and then you apply the KVL. Okay, KVL across this loop, KVL across this loop, and then you calculate I1, I2, I3, and we are trying to find the power through this 10 ohm resistance. So I2 you have to calculate. So once we calculate I2, I square R will be the power dissipated in this circuit. But here we will use a slightly different approach. This is same. Okay, this part is same, current part is same, but here all of them are connected in parallel, and 1 ohm means there is a 1 ohm in series. This is not a simple battery. Okay, so be careful about that. This is not a simple battery. There it has an internal resistance. Internal resistance is not shown in the circuit, but it is mentioned as a comma. That means this is the internal resistance which is in series with it. Now first of all, if you see that all of them are connected in parallel, so in parallel combination, the voltage across each of them must be same, and that one we will apply. Voltage across each of the components is same. So we say voltage across this one is V, voltage across this one is V, voltage across the resistance is also V. Okay, so now we will use our shortcut method. So first we will take this battery only. So what happens is that because they are all connected in parallel and we have taken the common voltage, we do not need to consider any loop. Okay, you can simply consider this part only. So if you consider this part, current through this is I1, terminal voltage is V, terminal voltage of a cell, that concept we are going to use. So what is the formula for terminal voltage of a battery? Terminal voltage of a battery is given by epsilon minus I R1, here I1 R1. Okay, first battery. So terminal voltage is V equals to epsilon minus IR. Here V is same, epsilon 1, I1, R1, they are different. Okay, so from there we can say that V for top battery, top cell. Okay, so from here we can say V equals to 2 minus I1 into 1. Okay, resistance is 1. Or from here we can say I1 is equals to 2 minus V. I1 equals to 2 minus V. Now what about I2? I2 is only the resistance and the voltage. That means V is equals to, for resistance, V is equal to current times resistance. That means current is given by V upon R. So that is equals to V. We do not know V. We have to, if we can calculate V, we should be able to solve this question. So V by 10. Okay, resistance is given R equals to 10. So V by 10. Now for bottom cell, what about for bottom cell? Same principle. V equals to epsilon 2 minus IR2, I3R2. Okay, so V equals to 4 minus 2I3. Okay, R2 here is 2. So from here we get I3 equals to V minus 4 by 2. Okay, so terminal voltages are calculated. Now from Kirchhoff's current law we know this is the case. Okay, so I2 must be equals to I1 plus I3. So we will put that in this equation. So V by 10 equals to 2 minus V plus V minus 4 by 2. So this is, from this equation we need to calculate V. Okay, now multiply everything by 10. If you multiply everything by 10, you will get V equals to 20 minus 20 V plus 5V, 4 5s are 20. Okay, so now let's take all the V's on our left hand side. We get V plus 20 V minus 5V equals to, so there is a small mistake I made. Here it will be V 2 minus V. Okay, this is correct. This is correct, 2 minus V. Here I made a mistake. Here it will be 2I3 equals to 4 minus V, or I3 equals to 4 minus V by 2. So that is the mistake. So let me correct that. So here it will be 4 minus V. Okay, so it will be, and one more mistake I made here. We are multiplying with 10 each and every quantity, so it will be 10 to the 5. So if you multiply 10 5 cancels, only 5 is left, so plus 20 minus 5V. Okay, so what I have done, 4 minus V by 2 into 10, so 2 cancels, 5, 4 5s are 20 minus 5 V is a 5V. Okay, clear? That's what I have done over here. So now take everything on our left hand side. Here we have V plus 10V plus 5V equals to 40. Okay, so V so 15 plus 1, 16V equals to 40, or V equals to 40 by 16, that is 5 by 2, that is 2.5 volt. So V is calculated. Now this is, even though this might look long, actually this is the shortest way to solve it. I1, I2, if you apply KVL and KCL, this can be little tricky. So I have done that in my live class yesterday, so you can go and check that out. There I have solved it using normal method of Kirchhoff's current law and Kirchhoff's voltage law. Okay, so V is 2.5. 2.5. Now we can calculate the current. We are only interested in the current I2, that is the current through this 10 ohm resistor. Okay, so I2 equals to V by 10, that is 2.5 by 10, that is 0.25 ampere. Okay, so 0.25 ampere is the current. Now what is the power? Power is I square R, that is 0.25 whole square into 10, and it will be 0.625 watt. You can use the calculator and calculate it. Okay, correct answer is 0.625 watt. Now let's move on. 3 resistors, 2 ohm, 3 ohm, 6 ohm, are combined in parallel. What is the total resistance of the combination? If this combination is connected to a battery of EMF 2 volt and negligible internal resistance, determine the equivalent resistance current through each resistor and the total current drawn from the battery is. So first of all, we have to calculate the equivalent resistance. 3 resistors connected in parallel, so equivalent resistance is given by 1 upon 2 plus 1 upon 3 plus 1 upon 6, that is 6, 3 plus 2 plus 1, that is 6 by 6, that is equals to 1. So R equivalent is equals to 1 by 1, that is 1 ohm. So R equivalent is calculated. First part is done. Next part is calculate the current through each resistance. Now here we have three resistors connected in parallel. Okay, connected in parallel. So in parallel combination, the voltage across each resistor should be same as the battery. So suppose I1, I2 and I3. So current through each of them should be same. So what is the current voltage that we have applied here is 2 volt. So current through first resistor, this will be I1 equals to the voltage that you have applied divided by the resistance R1. Okay, R1, R2, R3. Okay, is equal to 2 equals to 3 equals to 6. Okay, so 2 by R1, that is 2 by 2, that is 1 ampere. I2 equals to 2 by R2, that is 2 by 3 ampere. You don't need to make it into a fraction. I3 equals to 2 by R3, that is 2 by 6 equals to 1/3 ampere. So these are all the 3 currents. So total current in the circuit is given by I1 plus I2 plus I3 equals to 1 plus 2/3 plus 1/3, that is 3 by 3. 1 plus 3 by 3. So this is 3 by 3. That is 1. That means 1 plus 1 is 2 ampere. So current through the circuit is 1 ampere. Now if they ask you what is the power through R3, power through R3 will be I square R. I is given by 1 by 9, R is 6, so 6 by 9. Okay, you can calculate the power through any component as well. So this is the standard problem, and answer is 1 ohm, 1 ampere, 2/3 ampere, 1/3 ampere and 2 ampere. Now next, for copper, the number density of electron is 8.5 into 10 to the power of 28 per meter cube, and resistivity is 1.7 into 10 to the power of -8 ohm meter. Calculate the conductivity of copper and relaxation time of free electrons in copper. Take the mass of electron is given by 9.1 into 10 to the power of -31 kg, and E is 1.6 into 10 to the power of -19 coulomb. Okay, so resistivity is given. First of all, you have to calculate the conductivity. Conductivity is given by 1 upon resistivity. Okay, so conductivity will be 1 by 1.7 into 10 to the power of -8, or 10 to the power of 8 by 1.7. You can take this as 10 divided by 1.7 into 10 to the power of 7. Okay, so I have taken one 10. I have so many tens. I have 8 tens. I have taken one of them. Okay, and it will come out to be, I think, 5, 6 approximately. I am not sure. 6 into 10 to the power of 7. Okay, conductivity will be ohm, not ohm meter. Ohm to the power of -1, meter to the power of -1. Resistivity is ohm meter, so conductivity will be 1 by ohm, so ohm inverse, meter inverse. Be careful about the unit. Now what? Next we have to calculate the relaxation time. For relaxation time, we know that conductivity is given by N E square N E square tau divided by M. We did this derivation few hours ago, few minutes ago. So N is given in this question 8.5 into 10 to the power of 20. So this formula you have to remember. Even if you remember the derivations or not, the formula you have to remember. This question again from your model paper and question bank. I think this question is taken from your question bank. So 8.5 into 10 to the power of 28. E square means this square. 1.6 into 10 to the power of -19 whole square. Tau we are trying to calculate. So this value we have known, 6 into 10 to the power of 7. Exact value I will tell you in a while. Mass of electron is 9.1 into 10 to the power of -31. So you have to cross multiply, square this, but while squaring be careful. Here we have 10 to the power of -19 whole square. That means it will be 10 to the power of -38. This one will go up and become plus. So all the 10 to the power calculation you have to do properly, and you will see that this will be approximately, tau will be approximately 0.25 into 10 to the power of -13 seconds. Okay, so this is the answer, and I have taken this as 6, but it can be taken as 0.59. Okay, both are okay. 0.59 10 to the power of 8. I have taken it 6 into 10 to the power of 7. Okay, so even my guess was not that bad. Okay, so just you have to use the calculator to calculate these values. As I mentioned, in board exams, the data or values are given randomly. They don't care about whether it is solvable without calculator or not. Their main objective is to give the accurate values as much possible, and that's what they have done. Now, next question. the terminal potential difference of a cell connected to an external resistance 4 ohm is 2.4 volt. When the same cell is connected to an external resistance of 9 ohm, the new terminal potential difference becomes 2.7 volt. Find the EMF and internal resistance of the cell. So cell based questions are day by day coming common. Last year also they asked one question based on cell, parallel combination of cell, but this is a separate question again from your model question paper. What is the terminal voltage? Terminal voltage, always remember, is given by epsilon minus I into R. Okay, so in the first case, terminal voltage is given 2.4 when you are connecting to an external resistance of 4 ohm. Now what is V? By the way, V is given by I into R. Okay, so from combining these two relations, we can say IR equals to epsilon minus IR. Okay, so I should be equals to epsilon by R plus R. Okay, this is the easiest formula, but we will not use this formula. What we will use something different. What different is from this relation we will calculate the current. Current is given by V by R. Okay, so first case, so these are the all general formulas. First case, okay, voltage V1 is given by 2.4, resistance is given by 4 ohm. So what is the current in the circuit? Current in the circuit is given by voltage by resistance, which is 2.4 by 4, which is 0.6 ampere. Okay, so 0.6 ampere is the first stage current. Now we will come back to our common equation, this equation we will use. So V1 is again equals to epsilon minus I1 R. We do not know epsilon, we do not know R, right? So two variables, we need two equations to solve. So V1 is 2.4 and epsilon we do not know. I1 we have calculated 0.6, R value we do not know. Next case number, this is case number 1 by the way. Next we will use case number 2. So let me erase everything here and we will use case number 2. So what is case number 2? In second case, same battery is connected across 9 ohm and voltage is 0.27 volt. So what will be the second current? Second current will be the voltage divided by the resistance R2, here it is R1. So V2 is 2.7 and R2 is 9, that means current is 0.3. So again we will use the same equation, 2.7 equals to epsilon minus 0.3 R. Okay, so now we have to eliminate one by one and solve it. So we will, this is our equation number 1, this is our equation number 2. So if we put this equation over here, we can get 2.4 equals to epsilon minus 0.6 R. Now what we will be doing, we will be subtracting minus minus plus. So we get 2.7 minus 2.4 is 0.3 equals to 0 minus plus 0.6 minus 0.3, that means it will be plus 0.3 R. Be careful, the values are not complete, so you have to take the fraction. Okay, so 0.3 equals to 0.3 R, or R equals to 1 ohm. So R is now calculated. Now we will use any one of the equation. I am using this equation. So putting R equals to 1 ohm, we get 2.4 equals to epsilon minus 0.6, or epsilon equals to 2.4 plus 0.6, that is 3 volt. So 3 volt is the EMF and 1 ohm is the resistance. Clear? Not a difficult problem if you know how to solve it. Better than circuit diagram related questions. Okay, students started avoiding this chapter because of the circuit diagram related questions. That's why the board also decided that we may not give circuit diagram related questions from this chapter. Okay, so this is the end of this chapter. Have a look at the blueprint of the 2026 year. So 1 mark question will be one small answer type questions will be there, one small answer type 3 mark questions will be there, a long answer type questions, obviously 1 question will come, and total marks in this chapter is 11. So how many questions we are going to discuss in this lecture? We are going to discuss 15 MCQs, 5 fill in the blanks, 2 marker question 5, 3 marker question 5, and long answer type 5 questions. So this is our structure for today's lecture. So without much delay, let us start. A moving coil galvanometer can be converted into a voltmeter by connecting a low resistance in parallel with the galvanometer, a low resistance in series with the galvanometer, high resistance in parallel with galvanometer, high resistance in series with galvanometer. So for galvanometer to voltmeter, we need a high resistance in series with the galvanometer. So correct answer is option D. Now next question. The physical quantities related to magnetism are listed in column 1 and dimensions are listed in column 2. Identify the correct match. So here we have a dimension as well as some quantities, and you have to match it. So magnetic field, then we have magnetic permeability, we have magnetic moment as well. Now you might be thinking, sir, this can be little difficult. So you have to remember that magnetic moment is given by current times area. So that is the matching for this particular thing will be magnetic moment into area. That means this is the matching for number 3. So number 3 with B. Let's see how many of the options are there. So even if you are not sure, you check if you know any one of them, and once you at least find one of them, see how many of the options are there with that matching option. So here number 3 with B is there only once, that is option D. Okay, so remaining matching is automatically done. Magnetic field is given by this, magnetic permeability is given by this, so option D must be the correct answer. A charged particle small q is moving in an uniform magnetic field. The angle between the velocity v of the charged particle and magnetic field B is theta. The trajectory of the charged particle varies with angle theta. Match the following table by choosing the appropriate trajectory for different possible values of the angle theta. So the different angles are given, and they asked you what will be the trajectory of the particle. Now we know that when the particle is moving along the magnetic line, that is the angle theta is 0, then it is a straight line. Okay, angle theta 0 is a straight line. Also we know that when the angle is 90 degree, it gives you the circle, right? So this is a circle. So only other match 45 degree must be helix. So anything between 0 and 90 gives you an helix. It does not necessarily to be 45 degree. It can be 30 degree, it can be 60 degree, it can be 31 degree. Any angle between 0 and 90 will always give you helix, whereas 90 degree will give you a circle and 0 degree will give you a straight line. So 1 is matching with B, 1 is matching with B, 2 is matching with C, and 3 is matching with A. So 1B, 2C, 3A. So correct answer option B. Right? Next. The Lorentz force is the force on a charged particle moving in a region containing both electric and magnetic fields. So Lorentz force is basically a force when both electric and magnetic field exist in some area, and the force experienced by the charge is given by the Lorentz force. Next, force on a charged particle moving in a magnetic field is maximum when the angle between the velocity of the charge and the magnetic field is. So force on a charged particle moving in a magnetic field is given by QVB sine theta. So when the force is maximum when sine theta is maximum. When sine theta is maximum, when theta is equals to 90 degrees, right? So correct answer is 90 degrees. Next, a charged particle is released from the rest at a region of uniform magnetic and electric field parallel to each other. The particle will move in a helix, in a circle, in a straight line, in a cycloid. Let's see. So we have a charged particle which was initially static. Now electric and magnetic field, they are parallel to each other. Okay, if you read the question, electric and magnetic field are parallel to each other. Okay, now if you release the charged particle Q, what will happen? Initially it was at rest, so definitely no force is acting on it. Now when you release it, what happens? The electric force is acting on it, that is given by Q into E, and because of this force it will accelerate in the direction of electric field. Okay, now because electric field and magnetic field, they are parallel to each other, then what happens is that magnetic field will not apply any force on this charged particle, because the angle theta in this case will be 0. We know that magnetic force is given by Q VB sine theta. Okay, because theta is 0, sine theta will be 0. So because sine theta is 0, magnetic force will be 0. So it will move in a straight line. Okay, the particle will move in a straight line because of the electric force, but magnetic force will be 0. In case they are perpendicular to each other, then it will be moving in a circle. Now, next, the path traced by a charged particle moving perpendicular to a uniform magnetic field is. So path traced by a particle moving perpendicular to the particle is Q VV sine theta. Theta is 90 degree. So definitely it will be a circle. Okay, velocity and magnetic field, when they are perpendicular, then we get a circular motion. The dimensions of magnetic moment is, so what is magnetic moment? Magnetic moment is given by current into area. So current's dimension is A and area is L square. So L square means L square A is the dimension of magnetic moment. So L square A is the dimension. Next, a current flows along a length of an infinitely long straight thin walled pipe, then the magnetic field is. This is a question from one of your previous year, I think 24. So I flows along a length of an infinitely long thin walled pipe. So the thin wall is very, very thin. Okay, and it's a pipe. Pipe means internally it is hollow. Okay, externally it has some thickness. The pipe wall is very, very thin. Okay, now what is the question? Then the magnetic field at all the points inside the pipe is same but not 0. At any point inside the pipe is 0. Is 0 only along the axis of the pipe, is different at different points inside the pipe. So we are considering any point inside the pipe. So inside the pipe, if you observe that because the wall is very, very thin, if you consider a loop, and if you construct the loop and apply Ampere's circuital law, B dot dl, you will see that mu naught current enclosed through this area is equals to 0. So it will be mu naught 0. So B dot dl will be 0 and dl cannot be 0. So only thing is B should be 0. So magnetic field inside this thin walled pipe, whenever you consider a pipe or a shell, okay, magnetic field will be 0 because of Ampere's circuital law. Okay, so at any point inside the pipe it is 0. Next, parallel currents dash and anti-parallel currents dash. So parallel currents attract, anti-parallel currents repel. So parallel currents attract, anti-parallel currents repel. So correct answer is option C. A planar loop carrying a current I having n closely wound turns and area A possesses a magnetic moment M, where M is equals to NIA. So normally it is IA for one loop. For one loop it is IA, but if there are n number of loops, then it will be NIA, National Investigative Agency. Okay, so it is the answer M. Next, a charged particle moving in a circular path in a uniform magnetic field, then choose the wrong statement among the following. So that means here we have 3 correct statements, only one of them is incorrect. Radius of the circular path varies directly with its velocity. Radius of the circular path varies inversely with the magnetic field. Frequency of the revolution varies directly with the charge. Frequency of the revolution varies directly with the kinetic energy of the charge. Let's see. So we know that whenever there is a charge moving in a circular path, there has to be a centripetal force which is given by mv square by r, and from the Lorentz force we know that it is given by qvb sin theta, and for circular motion theta is 90 degree, that means sin theta is 1. So from here we can calculate the radius first. So radius, obviously one of the v is cancelled and we get r equals to mv by qb. So we can see that radius is directly proportional to velocity and radius is inversely proportional to 1 upon magnetic field. So both statements are true. Okay, it is radius varies directly with velocity and inversely with magnetic field. Both statements are true. Now we have to calculate the frequency of revolution. Frequency of revolution means omega, angular frequency. Okay, and even if you try to calculate normal frequency, it is same because omega is equal to 2 pi f, so it does not matter. Okay, so frequency or angular frequency is same. So how to calculate that? Now mv square by r can be written as m omega square r. Okay, and that is given by m qvb, sorry, not m, qvb. Now v is given by r omega. Okay, v is given by r omega. So let's put that q into r omega b. So r cancels, one of the omegas cancelled, and we get omega equals to qb by m. Omega equals to qb by m. So now see, frequency of revolution varies directly with the charge. So frequency of revolution is directly proportional to the charge. So this is a correct statement. Frequency of revolution varies directly with the kinetic energy of the charge. Now if you see that nothing is related to with kinetic energy over here, that means this is a wrong statement. Wrong statement means this will be the correct answer for our question. Okay, now next question. An electron is traveling horizontally towards east. A magnetic field is vertically downward direction exerts a force on the electron along. So the electron is traveling along the east direction. Okay, and our north is not along upside, north is along this side and south is along this side. Obviously, if you see north, east, south, and south, east, west, north. So if you are familiar with this, it is actually not upward direction. Upward is different. Okay, so this is our upward direction. This is our downward direction. Okay, this is east, this is west, this is north, this is south. Okay. Now what they said, that the particle is moving, the electron is moving in the east direction and a magnetic field is acting in the downward direction. So what will be the direction of the force? So we know that from Lorentz force, force is given by Q into V cross B. V is first, B is second. So if you first, how to find a cross product? To find the cross product, what you have to do? You have to first align your fingers in the direction of electric field. In the direction of velocity first. So velocity is along east direction, and then you rotate your fingers towards the second vector, which is magnetic field in this case. So in this case it will be downward. Okay, so downward means the other direction must be into the page of the paper, that is north. So it will be along the north direction. Be careful if you see such questions. Draw the diagram properly and understand that it is V cross B. So first will be in the direction of V, cross product principle. So first you have to align your fingers in the direction of first vector. Order of cross product is very, very important. Okay, if it is V cross B or B cross B, based on that direction will change. So V cross B means first you point your fingers in the direction of the first vector, and then you curl your fingers towards the second vector, then your thumb will point the direction of the resultant vector. Okay, so this is the resultant vector in this case into the page of the paper. Okay, so north is the correct answer. Next, the resistance of an ideal voltmeter is infinity. Resistance of ideal voltmeter is infinity. Resistance of ideal ammeter is 0. In a moving coil galvanometer, a current I produces a deflection theta. Then I is proportional to tan theta, I is proportional to theta, I is proportional to theta square, I is proportional to square root of theta. So if in a moving coil galvanometer a current I produces the deflection theta, then it is proportional to theta. Okay, the small angle approximation I is always proportional to theta. Next, fill in the blanks. When the charged particle move in a combined magnetic and electric field, then the force acting on it is known as. So when the charged particle moves in a combined electric and magnetic field, the force is known as Lorentz force. So correct answer must be Lorentz force. Let's see the answer. Yes, the direction of the magnetic field due to a current loop is found using the, so direction of magnetic field due to a current loop is found using the right hand thumb rule. It is called right hand thumb rule. So if this is a current carrying loop and the direction is given by this, then how can you find the direction of magnetic field? Curl your fingers in the direction of magnetic current, then your thumb will point towards the magnetic field. So this is called right hand thumb rule. Let's see where it is. Right hand thumb rule, this is the answer. Next is the alternative form of Biot-Savart law is Ampere's circuital law. So if you have watched any of my KCET lecture, there I have discussed that Ampere's law and Biot-Savart's law, they are actually the same. Only thing is Biot-Savart's law is more general. Ampere's law is some cases can be tricky if you if the line is not symmetrical. You can apply Ampere's circuital law as well, but it can be tricky if the line is not symmetrical. Okay, so Ampere's law and Biot-Savart's law are almost similar. So Ampere's circuital law is the answer. Current carrying circular coil is equivalent to a magnetic dipole. Okay, current carrying circular coil is equivalent to magnetic dipole. The north pole is formed like this and the south pole is on the opposite side. Okay, so this is a magnetic dipole. Resistance of an ideal voltmeter is infinity. Resistance of a ideal ammeter is 0. So correct answer is infinity. Okay, done. Now let's move on. A long air core solenoid of 10,000 turns per unit length carries a current of 2 ampere. Calculate the magnetic field at the midpoint on its axis. Now from this chapter, there is a tendency that a 2-marker numerical question will come, very simple, easy numerical. So let's solve it. So long air core solenoid, 1000 turns per unit length, carries a current of 2 ampere. Calculate the magnetic field at the midpoint of this axis. What is the formula? Magnetic field inside a long solenoid is given by mu naught Ni. Okay, mu naught Ni. What is the value of mu naught? Mu naught is 4 pi into 10 to the power of minus 7. Remember, it is mu naught, not epsilon naught. Epsilon naught's value is different, mu naught's value is different. Okay, number of turns per unit length is given by 1000 and current passing through is 2. So now let's simplify it. We get 4 to the 8 pi into 10 to the power of minus 4. Now you can leave the answer over here, or you can multiply 3.14 and you will get approximately 25 into 10 to the power of minus 4 Tesla. Okay, approximately this will be the answer. In this case I have kept it 8 pi, but 25 is also acceptable. Now let's move on. A moving coil galvanometer gives a deflection of 10 divisions when 200 microampere of current pass through it. Find the current sensitivity of the galvanometer. So this is a very easy question. Okay, number of divisions divided by current. Okay, 10 divisions divided by 200 microampere. It will be 10 into 10 to the power of plus 6 divided by 200. Why 10 to the power of plus 6? Because microampere. Microampere means, if you are confused, then let me write it one more line. So microampere means 10 to the power of minus 6. So this will go up and you will get 10 into 10 to the power of 6 by 200. Now, one important thing about current sensitivity, 10 into 10 to the power of 5 by 20. So it will be 5 into 10 to the power of 4 division per ampere. Now, in some cases, it might be given in the unit of ampere per division. So both are okay, ampere per division or division per ampere, but unit, if you are mentioning, you have to mention the units. So here it is given is 50 divisions per ampere. I think there is some mistake. It is microampere, not milliampere, but it will be 10 to the power of 4 division per ampere, not 10 to the power of not 50. Okay. Now, next. When does current carrying conductor placed in a uniform magnetic field experiences maximum force, minimum force? So what is the expression for force acting on a straight current carrying conductor? The expression for force on a straight current carrying conductor is given by BIL sin theta. Bill. Okay, remember bill. Okay, you are paying monthly bill. I used to, when I was a student, Bill Clinton was the president of America, so you used to remember Bill Clinton. Okay, I think a few years back, before I studied, Bill Clinton was president, so he was famous for some, like today, nowadays, Trump is famous. So back in the day, Bill Clinton was also very, very famous person. So we used to remember by this, Bill is correct, and Bill sin theta is the correct formula. Now, when will be the force will be maximum? The force will be maximum when theta is equals to 90 degrees. So when theta is 90 degrees, force is maximum. When the force will be minimum, when theta is equals to 0 degrees. Okay, that's it. So you just need to mention the formula and explain that when theta is equals to 0, sin theta will be 1. Okay, when theta is 0, sin theta is 0. That means force will be BIL, and in this case force will be 0, minimum force, right? Let's move on. Write the expression for magnetic force per unit length between two long straight parallel conductors carrying current. Give the nature of the force between two parallel conductors carrying current in the same direction. So the expression for force per unit length is given by mu naught by 2 pi Ia Ib by d. Now you have to mention mu naught equals to Ia equals to, okay, Ib equals to, and d equals to. You have to mention these quantities, and then you have to mention parallel currents attract and anti-parallel currents repel each other. So without this explanation, you will not get one full mark. They will deduct 1 mark for if you don't explain the terms. Next, a galvanometer has a resistance of 12 ohm and meter shows a full scale deflection for current of 3 milliampere. How will you convert this into a voltmeter of range 0 to 18 volt? So whenever you see such kind of questions, you have to take the maximum value of the voltage. Maximum value of the voltage is very, very important. So here we have a galvanometer, and the maximum current that it can withstand is given by 3 milliampere. The resistance of the galvanometer is 12 ohm. Now you are trying to convert it into a voltmeter. What is the basic process of converting into a voltmeter? The basic process is to add a high value resistance in series. So that's what we will do. Now remember that no matter what, the maximum current through the galvanometer cannot exceed this milliampere rating, whatever rating of the galvanometer. This is the maximum allowed current through the galvanometer. Okay, and if you are trying to measure 18 volts through this galvanometer, that means when 18 volt is applied across this galvanometer, when 18 volt is applied across this combination of the system, then the current in the circuit will be 3 milliampere. Okay, the maximum value not for any other value. The maximum value of the voltage when you apply, the current should be the maximum as well. Similar thing goes for ammeter as well. When maximum current is being passed, the current through the galvanometer should be the maximum range that is given. Okay, here 3 milliampere is given, so that means 3 milliampere should be the range, or 3 milliampere should be the value of the current that is being passed through the galvanometer, right? Now what we will be doing, we will apply the law, Ohm's law. So what is the total resistance? Total resistance is R plus 12. What is the current through it? Current is 3 milliampere. Milli means 10 to the power of minus 3, and that should be equals to the voltage that we have applied, and we said that maximum voltage gives maximum current, so this must be the applied voltage. Now we have to simplify it. 3, 6, 18. So we got R plus 12 equals to 6 divided by 10 to the power of minus 3, or 6 into 10 to the power of 3, or 6000, or R equals to 6000 minus 12, that is 5988. Simple question, simple answer. 5988 ohm is the resistance that you have to connect in series. So you have to mention that in series. Okay. Next, state and explain Biot-Savart's law with a suitable diagram. So what is the diagram that you have to explain? You have to draw a diagram. Okay, a wire carrying current I. Okay, you take a small element dl, then you are trying to find the magnetic field, say at a point P, and if you take this angle will be theta. Okay, this is the direction of this element dl, and the distance between this point is small r. Then Biot-Savart's law states that the small magnetic field due to this element at point P is directly proportional to the amount of current that is being passed. dB is directly proportional to the length. dB is directly proportional to angle theta, sine theta, and dB is inversely proportional to square of the distance. And combining everything, we can write dB equals to mu naught by 4 pi I dl sine theta upon r square. Okay, this is the formula for Biot-Savart's law. Now next, derive an expression for angular frequency of revolution for a charged particle moving in perpendicular to the uniform magnetic field, or obtain an expression for the radius of the circular path taken by a charged particle moving in a perpendicular to the uniform magnetic field. Now we have solved both of them. We will be doing again. So what is the starting point? Starting point is the magnetic force is given by QVB. Okay, QVB is the magnetic force. Now sine theta is obviously 1, and whenever it is rotating in a circular path, there has to be a centripetal force which is given by mv square by r. Sometimes this is also written as m omega square r. Okay, m omega square r we will be using for the first part, and this one we will be using for the second part. Now let's see. First is expression for omega. For omega. Okay, now how to calculate that? So at equilibrium, these two forces must be equal, so FB must be equals to FC. So we can say QVB equals to m omega square r, m omega square r. Now V for a rotational motion is given by r omega into B equals to m omega square r. Now R cancels, and if you simplify QB by M equals to omega square by omega, or one of the omegas cancel, so omega is equal to QB by M. This is the correct formula for angular speed. Now what about radius? Radius is easy, just compare these two forms. So QVB, so now it is expression for R. Okay, QVB equals to mv square by r. So just r comes over here and remaining goes to that side. So mv square by qvb, one of the v's gets cancelled, so mv by qb. So r equals to mv upon qb. So this is the correct formula. Okay. Now next, what is Lorentz force? Write an expression and explain the terms. This is one of the most common question from this chapter. 2 marker, 3 marker, both question might come. Force acting on a moving charge particle in the presence of an electric and magnetic field is called Lorentz force. Okay, in case of 2 marker question, they will ask you write the formula and explain the terms. In case of 3 marker, they will also ask what is Lorentz force. So this statement is only for 3 marker. For 2 marker, this formula and this expression is compulsory. So F is equal to Q into E plus Q into V cross B. Q is charge, E is electric field, V is velocity of the particle, B is the magnetic field. Next, how can a galvanometer converted into an voltmeter? Explain with diagram. So voltmeter should have a very high resistance as it is connected in parallel to the circuit. A galvanometer is converted into a voltmeter by connecting a suitable high resistance in series with the with it. This way the overall resistance of the galvanometer remains high. So we have to connect a very high value resistance with series with the galvanometer so that the overall resistance remains high. And if current through the galvanometer is given by Ig, the voltmeter is measuring a voltage V, then V equals to Rg plus R into Ig. Okay, this is the voltage that you measure. Okay, this simple equation, if you write it, you will get full marks. Next, how a galvanometer be converted into an ammeter? Explain with the terms. Now among these two questions, galvanometer to voltmeter came the most in the past. Galvanometer to ammeter came a little bit less, but this is also very, very important. An ammeter should have a very low resistance as it connected in series in the circuit. This is achieved by connecting a suitable low resistance S in parallel called shunt with the galvanometer. This way the overall resistance of the ammeter remains low and the galvanometer is converted into an ammeter. So if you see the diagram, this is the diagram for galvanometer to ammeter. Here we have connected a low value shunt in parallel. Okay, now this is also very, very important. You have to find the value of this current Ig, that the current and the total current I. So this is I minus Ig. So you have to find the current I. I is the current that you are measuring, and you have to calculate this current I in terms of Rg and Rs. So how to do that? So voltage, they are connected in parallel, so voltage across this should be voltage across this. That means Ig Rg should be equals to I minus Ig into Rs. Okay, or don't calculate Ig only. Okay, you have to calculate I. Remember that you have to calculate I, not Ig, because ultimately you are measuring this current, not this current. This current is already known for a given galvanometer. Okay, so Ig Rg plus Ig Rs equal to I Rs. So I equals to Ig into Rg plus Rs divided by Rs. Okay, if you know this, if you can remember this expression, very good, you can directly write this expression. If you don't remember this expression, you have to start from here. Remember, the voltage drop across the galvanometer is same as the voltage drop across this small resistor. Okay, so these are all the 3 marker questions. Now let's move on to the 5 marker questions. State ampere circuit law. Now from this chapter, numerical questions do not come. We are expecting a full theoretical question from this chapter. State ampere circuit law and arrive at the expression for magnetic field due to a long straight current carrying wire. So ampere circuit law is statement is current through any closed loop is given by B dot dl if a current passing through a closed loop is I and magnetic field along the closed loop at any point is B, then B dot dl equals to mu naught I. You have to write the statement. I am not writing the statement you have to write. Okay, if you want to if you want my help to write the statement, you can tell me in the comment below. Otherwise, statement is very standard. Only thing that you have to do, you have to mention the statement and write the mathematical term as well. Now for a very infinitely long straight wire, let us we are trying to find the magnetic field, say at a point P. We will construct a circular Amperian loop, circular Amperian loop of radius r. So these are the very important thing the students do not write. If you don't write it, you will lose some marks. Okay, circular Amperian loop of radius r across the wire. Now if we apply ampere circuit law, then we will see that B dot dl equals to mu naught I. I is the amount of current that is being passed through this wire. Right now, if you see that this is a circular wire, that means it's a symmetrical. Circle is one of the most symmetrical two-dimensional object, right? So any point on this circle, if you consider the distance should be same distance from on this side, same distance on that side, same distance this side and that side. Okay, all sides, not only this and that, all points on this circle will be at equal distance from this wire. Okay, that means it is a circular symmetry. So if there is a circular symmetry, that means the magnetic field has to be constant along the line joining along the curved line, right? So what we will be doing, so magnetic field is constant, so we will magnitude wise we will take that out and we will say B into dl. Okay, mu naught I. Now what is this weird symbol? Integration we know. What is this? This represents close integration. Okay, I told you in the Gauss's law chapter as well, this represents closed integration. Closed integration means your starting point and your ending point. If you start say at this point, after rotating the entire circle, if you again end at this point, then this is called a closed integration. It can be due to a surface, it can be due to a line, it can be due to a curve. Okay, but normally if the line is open, it is not possible. If it is a curved line, okay, starting and ending point can be closed, then only close integration is possible. Not every case you can consider a close integration. That's why in case of Gauss's law also, in case of Ampere's law also, in Gauss's law surface must be closed. In case of Ampere's law also, the loop must be closed loop. Open loop does not applicable for Ampere's law. So close integral dl means basically if you take small portions, dl, all dls if you take and if you add them, that gives you the close integration. Integration means basically some kind of addition. Okay, integration is a type of addition. Okay, so if you take small portion of this entire loop and if you add them, you will get the close integration dl. So what is the meaning of small portion? If you add all the portions of a circle, what do you get? You get the perimeter of the circle. So perimeter of the circle is what? Perimeter of circle is given by 2 pi r, and that is equals to mu naught I. Okay, so close integration dl is basically the perimeter, which is equals to 2 pi r for a circle. Okay, now from here you can calculate what is B. So B will be equals to mu naught I by 2 pi r. Now we can write it in little bit civilian way, mu naught by 4 pi I by 2I by r. Okay, this expression is similar to that of a straight wire, charged wire. Remember, 1 by 4 pi epsilon naught, 2 lambda by r. Similarly here also mu naught by 4 pi I by r, 2I by r. Okay, you can have 2 pi over here, and you can cancel 1 2, but this is a standard way of writing. You can write, you can leave the answer in the previous form also, you will get full marks. Next, derive the expression for magnetic field at a point on the axis of a circular current carrying loop. Now for your year there is a possibility that this will not come, but there is no guarantee. What I have seen from the past few years of paper analysis, this generally comes alternate years. Okay, this generally comes alternate year. This derivation came last year, so there is a less chance it will come for your year. Your year, the next derivation is important. Anyway, no harm in practicing, and that is for board exam, by the way. For your pre-board exam, this question might come, and it is an important question. So in some of your cases in pre-board exam, this question will come definitely. Not every one of you, but some of you, this will come. Okay, so radius is given by r, and we are trying to find magnetic field at some point, say P, at a distance x. Okay, we will consider a small element over here, and what is the distance of this element from this, say small r. From Pythagoras theorem we can write this distance as capital R square plus x square. Okay, now we will apply, what we will apply? We will apply Biot-Savart's law. Okay, Biot-Savart's law states that the magnetic field due to a small element is given by I dl sine theta upon r square. Now here this theta is the angle between the top portion of the loop, that is this one, and the distance vector, which is actually 90 degrees. Okay, so this angle and this is 90 degrees. So this theta is 1. So dB will be I dl by r square. Sin theta is 1. But this is not it. If you consider what will be the direction of the magnetic field, the direction of the magnetic field will be along some direction like this. Okay, and this angle, if this angle is phi, then this angle will also be phi. Okay, this can be proven geometrically. I am not doing it. So this angle is phi, this angle is phi, because we are not getting any marks for this derivation. So you see that there will be two components. One will be along the y direction, one will be along the x direction. So this will be dbx and this will be dby. Now if you consider a diametric opposite point, then the magnetic field will be in this direction. Again there will be an x component, there will be an x component, there will be an y component. So as you can see, for each and every point there will be a diametric opposite point. So that means the y components will cancel each other. Eventually only thing that we will be left with is the x component. So y component will not play any role, only the x component will play a role. That means the net magnetic field will only have x component, which is given by dB cos phi. That will be given by dB cos phi. So what is the value of that? So dB, so if you consider this angle, cos phi is given by base by hypotenuse. So base is r and hypotenuse is small r. Okay, now we will put these values over here, and we got there was one thing I missed, I forgot. Mu naught by 4 pi was there. Okay, so mu naught by 4 pi. Okay, and we have I dl r divided by r square. Initially was here, there was one small r, another added, so it will be r cube. Okay, so this is the magnetic field due to this small element. Now why we are only calculating x component? Because if we when we do the sum of all the components, when we take the integration of this, y components will cancel. That's why we are only considering the x component of the combination. So what will be the total magnetic field? Total magnetic field is integration of dBx. Again it's a closed integration because circular path, so you have to take start and end at the same point, so it will be again a closed integration. Now when you are doing a closed integration, mu naught by 4 pi I r cube, everything is constant except this small dl, so that will be only left. So mu naught I r by 4 pi small r cube integration dl, close integration dl. Now what is close integration dl? We already explained. Close integration dl is nothing but the circumference of the circle, so it will be mu naught I r. So mu naught I r divided by 4 pi r cube times what is the circumference of this circle, that is close integral dl, that is 2 pi capital R. Don't make any mistake, it will be 2 pi capital R. So 2 pi will be cancelled and we got our result as mu naught I r square. 1 r was here, 1 r is here, so I r square divided by 2 r cube. But this is not the final answer, you have to substitute the value of r over here. R is square root of r square plus x square, that means r cube must be equals to r square plus x square to the power 3 by 2. Why 3 by 2? By 2 represents the square root and this cube represents the cube. So we have to put that value as well. So we got, after little bit rearrangement, mu naught by 2 I r square divided by capital R square plus x square to the power of 3 by 2. So if you see that in my entire derivation I have used this expression at the end, but I have seen students they start using this from the beginning and somewhere in the middle they lost and they make some unnecessary error in this expression. Okay, so don't do that. Use this way your derivation will be cleaner, smaller and lot less error free. Okay, so a lot less error. Okay, so errorless derivation is important, so that's why you have to do this like this way. Now next, derive an expression for force per unit length on two infinitely long thin parallel straight conductors carrying current and hence define ampere. Now this question is important for your particular this year, for your board exam. Okay, almost every alternate year this question and the other question are coming, but with a pinch of salt, this is not guaranteed, as I mentioned. Okay, this my intuition tells that this question is important for you. Yeah, so you have to practice both this one and the previous one. Okay, all the other ones are did came in the past once or twice, in especially the second and third papers, improvement papers or supplementary papers, but these two are predominantly the main question for your PU board papers. Now let's see, here we have two parallel wires, 1 and 2. Okay, now if we want to consider this wire, say wire I carrying a current I1, this is a wire 2 carrying a current I2, both of them are carrying current in the same direction. We are assuming for now the distance between them is d. Okay, so if I want to find the magnetic field due to this infinitely long wire at this junction, at this point, what will be the magnetic field? The magnetic field due to wire 1 at the location of wire 2 is given by, we just did the derivation by the way, it is given by mu naught by 4 pi 2I by R, or here we will not use this symbols, we just to remember it I used it, so I by D, I1 by D. So this is the magnetic field of wire 1 at the location of wire 2. Okay, this is the magnetic field of wire 1 at the location of wire 2. Now what will be the force acting on this wire 2 due to this magnetic field? For that, what you have to do, you have to consider a length, because magnetic field infinite wire does not work. You have to consider a length of the second wire. Okay, suppose we are considering a length of L, then the force is given by force on 2 due to 1. Okay, force acting on the wire 2 due to first wire is given by BIL sin theta. Now theta here is 90 degrees, so only BIL, so it will be mu naught by 2 pi I1 by D into I2 into L, or mu naught by 2 pi I1 I2 by D into L. Now this equation is very symmetric. What is the meaning of that? If you swap the location of 1 and 2, this expression will not change. So if you do the same process for the wire 2 at the location of wire 1 and then calculate the force acting on wire 1 due to wire 2, you will get the same expression. So you can write similarly. Why you can write similarly? You have to understand these small points. Okay, if you understand it, it will save some time for you during the exam. Not always you can write similarly. Okay, some cases you can write similarly if it is actually similar. So for example, in this case it is similar because if you swap the location of I1 and I2, the expression does not change. So F12, so F21 is, first is coming 1, second is 2, so F12 will be again the same thing, mu naught by 2 pi I2 I1 by D into L. Okay, so this is the force. So or again you can write 2 pi, now I2 I1 is same as I1 I2 by D into L. So this is the force. Now vectorially F12 is exactly opposite of that F21. So if this force is trying to pull it in this direction, then this force will try to pull it in this direction. So this is F on 2 due to 1, this is F on 1 due to 2. Okay, so if you apply this logic, okay, they are in the opposite direction, but magnitude wise F12 equals to F21, and say that is equals to F. Say this is F. So what is the value of F? F is given by this expression, mu naught by 2 pi I1 I2 by D into L. Okay, now L here we have assumed because the wires were infinite, right? So this L actually has no meaning. For that, what we have to do, we have to find the force per unit length. Force per unit length is given by F by L, which is given by mu naught by 2 pi I1 I2 by D. This is the expression for force per unit length due to two current carrying wires. Now here also, this is not the end, you have to also define the term ampere. Okay, so how to define ampere? To define ampere, if I1 equals to I2 equals to 1 ampere, D is equals to 1 meter, then the force will be given by mu naught by 2 pi. Now mu naught is 4 pi into 10 to the power of minus 7. So if you put that value, you will get the value of the force per unit length will be given by 2 into 10 to the power of minus 7. Okay, Newton per meter. Okay, so that is how we define ampere. So ampere is the current when flows through each of the two parallel conductors kept at a distance of 1 meter. So I1 and I2 both are equal to 1 and this distance is equals to 1 meter. Then the force is 2 into 10 to the power of minus 7 Newton per meter. Okay. So what is the meaning of this? The meaning is if I1 equals to I2 equals to 1, D is equals to 1. So they are actually 1 ampere and this is equals to 1 meter. Then force per unit length is mu naught by 2 pi. So what is mu naught by 2 pi? Mu naught is 4 pi into 10 to the power of minus 7. So mu naught by 2 pi will be 2 into 10 to the power of minus 7. Okay, 4 pi by 2 pi, only 2 left. Okay, so this is how you can define ampere. This is a way to define ampere. From this formula, the definition of ampere came in the existence. That's why this is very important. Now let's move on. With the help of a diagram, derive the expression for torque on a rectangular current loop placed in an uniform magnetic field. So we have a rectangular loop, current carrying loop, carrying a current I. We have a magnetic field here, say north, and we have magnet over here, say south. So magnetic field lines are passing like this. Okay, current is here, current through this is here. This is current, this is the current. Now here, whenever a current loop is placed in a magnetic field, it will experience as a torque. Now how to calculate that torque? Suppose the length of this loop is given by A and breadth is given by B. Okay, breadth is given by B, length is given by A. So the current through both of the wire part is I. Now whenever you place a current carrying wire in a magnetic field, it experiences a force. What is that force? That force is given by BIL sin theta. Okay, BIL sin theta. Now if you see that for the wire, say this is 1, say this is 2, this is 3, this is 4, 4 sides of the rectangle. For wire 1 and wire 3, for wire 1 and wire 3, the angle, for this case angle theta is 0. This case theta is 0 and this case theta is 180 degrees. Now if theta is 0 or 180 degree, both cases it will be 0, right? Sin theta 0 is 0, sin 180 degrees also 0. For this case angle is 90 degree, this case also angle is 90 degree but in the opposite direction. So in one case there will be a torque in the upward, there will be a force in the upward direction. For the other case there will be a force in the downward direction. Okay, so basically if you consider this is your rectangular loop, these two sides are parallel, that means parallel or anti-parallel, there will be no force on these two wires. Only force that will act along this wire and this wire. Okay, so in this case it will be upward and this case it will be downward. Okay, so sin theta is 90 degrees, so the force is only BIL sin theta. Okay, and what is L in this case? L is A. So force on any one of them is given by BI small a. BI small a, but this is force on both cases. So this is F4 and F2. F on 4, F on 2. Okay, so F on 4 and F on 2 both will be BIA. Right, so this is the force acting on these two wires due to the external magnetic field. Okay, now what will be the torque? So when two equal and opposite force acts on a system, but at a different point the system experiences a torque. So what is the value of the torque? Value of the torque is any one of the forces, any one of these forces, we are using F commonly, times the distance between the forces. What is the distance between these two forces? So this force is acting along this line, this force is acting along this line. So what is the force between the distance? Force between the distance is B. So F into B. Now put the value B I A B. Now what is AB? So this is a rectangle. Rectangular length is A, breadth is B. Length into breadth gives the area of the rectangle. So it is B I A. So this is the torque acting on this particular loop. Now if the loop contains more than one turn, then the torque will be N into B into I into A. Okay, N, B, I, A. Okay, or to remember the formula, this is a way. Okay, Nayab. Okay, Nayab is a Hindi word or a Urdu word which means very rare. Okay, so Nayab is the term that you can remember. This is how you can do the derivation. This is a very simple derivation, and if this derivation is coming there, along with that there will be one more question like state the Ampere's law or state Biot-Savart's law. There will be one more question associated with this. Otherwise this is a very simple and easy derivation. Okay, so Nayab is the formula, but this formula we'll be using in our next question as well. What is the next question? What is the principle behind working of a moving coil galvanometer? With the help of a neat level diagram, obtain the expression for angular deflection produced in moving coil galvanometer. So this is the neat level diagram. Okay, everything is same. Only thing is that here we have a spring. Principle: when a current carrying coil is placed in a uniform magnetic field, it experiences a torque. What is the expression of the torque? Expression for the torque we have already calculated. NIAB is the expression for the torque which is acting on this coil. Now this torque, what is the role of a torque? What does a torque do? The torque always try to rotate. Right? If you apply a torque on a static object, then it will try to rotate the object. Okay, so if this is left unchecked, then the galvanometer coil will keep on rotating. But to keep it in check, we apply a spring. That spring will try to resist this rotation, and it will actually stop the rotation after some time. And if the angle of deflection of this is given by theta, then the moment of inertia of the coil times the angle of deflection theta, okay, can be given by Nayab. Now in this particular case, if you apply the spring constant, that will also be fine. Spring constant K. Torque is given by I theta. Okay, in this case it will be K theta. Theta is the deflection. Okay, theta is the deflection, and K is the spring constant. Okay, from here we can say that theta or the deflection of the galvanometer, theta is the deflection of the galvanometer, is given by NIAB by K. Okay, or theta equals to NBA by K into I, or theta equals to G into I, or G is NBA by K is called the galvanometer constant. Very simple and easy derivation, nothing much. Okay, so theta is proportional to the current, so more current passing through the galvanometer, more deflection it will be giving. Okay, so this is the simple and easy derivation. It came once or twice, and it came once in the third paper of the second or third paper, means improvement or supplementary papers. Okay, it did came, but main paper I think it came only once. This derivation never came in the main paper, but it came in the supplementary papers once or twice. Similarly, this also came only once in the main paper, and in the supplementary paper it came 2-3 times. Okay, so maybe it will come in your exam, but as you can see the derivations are easy. If you practice it once, you should be able to remember it. Main important derivation is this one. This is little tricky and long derivation. This one is also tricky and long derivation. So these two derivations you have to practice 2-3 times, and also you have to remember this definition of ampere. These derivations are easy. Diagram and derivation should not take much more than 5 minutes of your time. Here we have 1 marker questions coming from this chapter is 2, not 1. So far all the chapters that I have discussed, only 1 questions was coming from 1 marker section, but from this chapter 2 question is coming from 1 mark as a 1 mark question. But from the blueprint that we have studied, we realize that and as well as the model question paper and previous year question papers, after studying everything, we realized 1 MCQ question will come from this chapter and 1 fill in the blank. So not 2 MCQ question. Okay, so 2 questions coming means 1 question is from your MCQ and 1 question is for your fill in the blanks, right? So a short answer type 2 marker question is not going to come from this chapter. Only short answer type 3 marker question is going to come from this chapter, and total marks allotted for this chapter is 5. So if you watch this short video, it is not going to be a very long video. So if you watch this video, all 5 marks you can definitely guarantee it from this chapter. So this is the question breakup. So as usual, we are going to discuss 15 very important hand-picked selected MCQs. We will also discuss 5 fill in the blanks and 10 3 marker questions. So as you can see, all questions will be covered here from this chapter and nothing will be left behind. So if you watch this video, your entire PU2 preparation will be done. So let's start with the first question. So question number 1, in the following table, column 1 is the list of magnetic property and column 2 is the list of an item related to magnetic property. Identify the correct match. So you have to find the correct match between the following table. So in the column 1, some properties are given, for example, paramagnetism, diamagnetism, ferromagnetism, and in column 2 some of their properties are given. So let's see, magnetic property common to all substances. So what property is common to all substances? The common property among all substances is diamagnetism. Diamagnetism is common to all substances. Okay. Next, domain formation. Now which material shows domain formation? Only ferromagnetic substances shows domain formation. So domain formation is associated with ferromagnetism. Now sodium is an example of this magnetic property. So even if you don't know what type of material sodium is, so from after elimination you can easily see that it is definitely going to match with paramagnetic substance. Okay, so match the following questions are maybe sometimes tricky, but if you can at least find 50% of the matches, remaining 50% you can either guess from the option or you can guess from the whatever is left. Okay, now let's find the match. 1 is matching with R, so we will look for 1 is matching with R. So this is option B, 1 is matching with R. Option C is also 1 is matching with R. 2 is matching with P. 2 is matching with P, but here 2 is matching with Q, so definitely this is not the correct match. So correct match is 1 is matching with R, 2 is matching with P, and definitely 3 is matching with Q. So correct answer option B for this question. Right, now let's move on to the question number 2. The ferromagnetic material among the following is, so you have to find the ferromagnetic material. Copper is not a ferromagnetic material, nickel is a ferromagnetic material, lead and calcium, they are also not ferromagnetic material, only nickel is a ferromagnetic material. So remember 3 metals: copper, iron and cobalt. Okay, they are 3 materials which are directly ferromagnetic. There are some alloys obviously, but these 3 are in elemental form are ferromagnetic in room temperature. Okay, copper, nickel and iron. Gadolinium has a transition temperature around room temperature, but gadolinium only below room temperature can be considered as a ferromagnetic, not at room temperature. Okay, now next, The physical quantities related to magnetism are listed in the column 1 and dimensions are listed in column 2. Identify the correct match. Now sir, this is a very difficult question. I don't have any idea about dimension. So what to do about in that case? So you have to remember some of the few easier dimensions and hope that only one option is given from that option. So first of all, magnetic field can be tricky. Magnetic permeability trickier. Magnetic moment easy. Magnetic moment is current times area. Magnetic moment is given by M equals to current times area. Okay, there is a number of turns involved, but number of turns is a dimensionless quantity, so current into area is the major thing. So what is the dimension of current? Dimension of current is ampere. Dimension of area is meter square, so definitely it will be L square A is the dimension of magnetic moment, so this is directly matching with this. Okay, so 3 is matching with B. Now let's see what are all the options given in this question. So if you see that only one correct option with 3 with B, so this is 3 with C, 3C, 3A, 3B. Only one correct option with 3B, definitely this is the correct answer. And if you forget 1 is matching with C, that means the magnetic field's dimension is given by this one and permeability dimension is given by this one. Now one thing you can remember is that out of magnetic permeability and magnetic field has one less ampere compared to magnetic permeability. Permeability and magnetic field are almost same, only difference is in the dimension of ampere. So ampere or current dimension is -1 for magnetic field and it is -2 for permeability. Okay, these two are very close to each other, so sometimes it gets confused between what will be the dimension of these two quantities. Okay, also in magnetic permeability there is a length involved, in magnetic field length is not there. Okay, so these two things you can remember, otherwise at least try to find the common dimension and try to figure out what will be the other two dimension. And remember that generally, one more point to remember, generally direct match is not given in the match the following question. Okay, so direct match, so for example 1 is matching with A, very less chance of giving it like this. Okay, so from if you find one match, remaining 2 matches will be easy, at least for 3 match the following type question. So one match is this, that means it cannot be matched with this, so it should be matched with this, and this one will match with this one. Okay, this is a technique or trick to match the following type of question. Okay, another match the following type of question, and all the match the following type of questions are given in your current model paper. So this is also from your model paper, so be sure you practice the questions, those are match the following type. Okay, based on the magnetic properties, materials are listed on the column 1 and values of magnetic susceptibilities are listed in the column 2. So this is magnetic materials and this is their susceptibilities, so easy match the following. Let's see what is the option here. Okay, so diamagnetic substances have negative susceptibility, so small and negative is the match for diamagnetic. Paramagnetic substances have small and positive, so this is the match, and for ferromagnetic this is the match, large and positive. Okay, this is easy question. Now let's see the option. 1 is matching with R, 1 is matching with R, only one option is there where 1 is matching with R, 2 is matching with the P, and 3 is with Q. So correct option B. Okay, not a difficult one. Now let's move on. The SI unit of magnetic flux. What is the unit of magnetic flux? From Gauss's law we get to know about magnetic flux. Magnetic flux is the SI unit of magnetic flux. There are 2 units. One is Tesla meter square, or this is also called Weber. This entire thing is also called Weber. Okay, so Weber or Tesla meter square is the unit of magnetic flux. So Weber is the correct answer for this question. universal property amongst all substances. So what is the universal property? This is from 2024 PYQ. Universal property among all substances is diamagnetism, and this question you will be able to answer only if you read the NCERT completely. So from NCERT this question came, but again I am here, I am helping you to understand all difficult questions that you need to answer. So universal properties among all substances are called diamagnetism. Magnetization of a sample is magnetic moment per unit length, magnetic moment per unit area, magnetic moment per unit volume, magnetic moment per unit current. So magnetization is defined by total magnetic moment or mnet divided by the volume. Okay, it's a vector quantity, so it is the sum of all the vector magnetic moments divided by the volume. So it is magnetic moment per unit volume. Okay. Next question, the net magnetic flux through any closed surface is 0. This is in accordance with Gauss's law of magnetism. Gauss's law of magnetism. So this is talking about magnetic flux. So definitely it is magnetism, not electrostatics. Okay. A magnetic dipole of magnetic moment is placed in a uniform magnetic field such that the angle between magnetic moment and magnetic field is theta. So it will be mentioned M and B is theta. Okay, if the magnetic dipole is in the stable equilibrium position, then theta is equals to 0, theta is equals to 90 degrees, theta is equals to 180 degrees, theta equals to 45 degrees. So what is the torque acting on a magnetic dipole? Torque acting on a magnetic dipole is given by mb sine theta. Okay, mb sine theta. So if it is in equilibrium, then the torque must be 0. So torque can be 0 in two positions. One is theta equals to 0, another one is theta equals to 180 degrees. Okay, but which one of them is stable position? For stable position, you need to know the potential energy as well. What is the form for potential energy? Potential energy is mb cos theta. Okay, both are important to know. So stable equilibrium, what is the theta for equilibrium? Theta for equilibrium is theta equals to 0 as well as theta equals to 180 degrees. These two angles gives the equilibrium because torque becomes 0. So understand this. Okay, even though it's an easy question, I am trying to explain the concept so that you memorize it, you remember it. Whenever if the question comes a little difficult, so same question is asked when it will be unstable equilibrium, you will know, you will be able to answer it. So stable equilibrium means when torque is 0. First of all, equilibrium means torque is 0. Now whether it will be stable or unstable, that depends on the potential energy. So what is the potential energy at theta equals to 0? So potential energy at theta equals to 0 is given by minus mb. Cos theta is 1. What about the potential energy when theta is equals to 180 degree? So in that case, potential energy will be plus mb. Why? Because cos 180 degree is minus 1. So minus minus plus, so it will be plus mb. So potential energy is negative and lowest. This is the lowest value of potential energy. In case of stable equilibrium, potential energy has to be lowest, and in case of unstable equilibrium, potential energy is highest. Okay, so as you can see, this is the highest potential energy, this is the lowest potential energy, and 0 is not the lowest potential energy in this case. Okay, anything negative is less than 0, that means it is smallest. So this is the smallest potential energy, that means theta equals to 0 gives the stable equilibrium, whereas theta equals to 180 degree gives the unstable equilibrium. Needles N1, N2 and N3 are made of ferromagnetic, a paramagnetic and a diamagnetic substance respectively. A magnet when brought close to them will. So we have needles N1, N2 and N3. Okay, and first one is ferro, second one is para, third one is dia. Now you brought a magnet. Magnet means it is a permanent magnet, so it has a north-south pole. So what will happen? So this magnet will definitely attract this one. Okay, attract the north or attract the ferromagnet. It will even attract the paramagnet, but it will repel the diamagnet. Okay, so this is strongly attract, it will weakly attract, and diamagnet will be again weakly repel. Okay, so it will attract N1 strongly, N2 weakly, and repel N3 weakly. So this is the correct answer, option B. Make sure if you are confused to draw this small diagram. Okay, this kind of questions are very common nowadays. Even in KCET exam some years back this question came, and it is given in your question bank as well. So now let's move on. The susceptibility of a ferromagnetic material is, susceptibility of ferromagnetic substance is much greater than 1. So correct answer is option C. Again, this is from your PYQ of last year. Which of the following properties is false for a bar magnet? Okay, so there are 4 properties. 3 of them is correct, 1 of them is incorrect. It does not produce magnetic field. So a bar magnet will definitely produce magnetic field. So that means this is the wrong statement. This is our correct answer. Its poles cannot be separated, correct statement. It points in the north-south direction, correct statement. It like poles repel and unlike poles attract, this is also a correct statement. So 3 of the statements are correct. First statement is wrong. So that is our answer for this question. A susceptibility of a certain magnetic material is 400. What is the class of the magnetic material? So susceptibility, we know that if it is very greater than 1, then it's a ferromagnet. So 400 is definitely very greater than 1. So this must be a ferromagnetic material. Next question. The magnetic field lines inside a bar magnet. So magnetic field lines inside a bar magnet, what happens? We know that for a magnet, the magnetic field lines outside a bar magnet moves from north to south. Inside the bar magnet, it goes from south to north. So are from south pole to north pole. Inside the bar magnet, it is opposite to that of outside. So inside the bar magnet, it goes from south pole to north pole. So option B is the correct answer. Now question number 15. When a bar magnet of dipole moment m vector is placed in an uniform magnetic field, then what is the torque acting on it? Calculate the torque acting on it. The torque acting on it is given by m vector cross b vector. This is the expression for torque acting on a dipole moment, on a bar magnet or a magnetic needle. Okay, the torque is given by m cross b, not b cross m. Okay, it is m cross b. Now let's move into the fill in the blanks section. An example for dimensionless quantity is, so let's see what are all the quantities mentioned in this option. Diamagnetic, solenoid, magnetic susceptibility, magnetization, paramagnetic, ferromagnetic. So only quantity that is mentioned over here is magnetic susceptibility. So definitely this is the correct answer for this. So magnetic susceptibility is a dimensionless quantity. The magnetic susceptibility is negative for dash material. So here we have 3 materials: diamagnetic, paramagnetic, and ferromagnetic. All 3 materials are given as an option. So magnetic susceptibility is negative for diamagnetic substances. Okay, it is positive but small for paramagnetic, and it is positive but large for ferromagnetic substance. Okay, so correct answer for this is diamagnetic. Now a current carrying dash is equivalent to a bar magnet. So let's see what are also options left. So we already have diamagnetic sorted, magnetic susceptibility sorted. So we have solenoid, magnetization, paramagnetic, ferromagnetic. So which one will be the option here? A current carrying solenoid is equivalent to a bar magnet. So that is only thing that makes some sense. So always I told you, I says that multiple times, whenever you are doing fill in the blanks, say check if the option is making any sense or not. So here only solenoid is making a sense. So definitely solenoid will be our answer, and we will effectively mark it. Next question, the net magnetic moment acquired per unit volume of a sample is called. Again, if you see the remaining option, we have magnetization, paramagnetic, ferromagnetic. Only magnetization is making any sense over here, so magnetization will be the correct answer for this question. So correct answer is magnetization. 20, the magnetic susceptibility is slightly positive for dash materials. So magnetic susceptibility is slightly positive for paramagnetic substances. Okay, so correct answer is paramagnetic. Now let's move on to 3 marker question. There is no 2 marker question. Now in your FA2 maybe you will see some 2 marker question, possibly some 2 marker question from this chapter, but don't worry, you can answer those 2 marker questions if you study these 3 marker questions. All the questions will be knockoff version of this 3 marker question. So here they will ask you 3 differences. In a 2 marker question they will ask you only only 2 differences. Now this question is basically actually 3 questions. Okay, this one question is equivalent to 3 questions: diamagnetic, paramagnetic, diamagnetic, ferromagnetic, paramagnetic, ferromagnetic. So any combination of difference might come, and this is very common, very popular question. If you take the PYQs, this question has came multiple times, and not only any 2 of them, diapara, diaferro, paraferro, all 3 of them has come in the past. Okay, so here is one slide, one page answer to every question that might come from this chapter. So practice them very by heart them, and remember it is very easy to remember anyway. So what is the property? First is property magnetic behavior. They are weakly repelled by magnetic field. Diamagnetic substances weakly repelled by magnetic field. Paramagnetic substances, these are weakly attracted by magnetic field, and ferromagnetic substances, these are strongly attracted by magnetic field. Now magnetic susceptibility, for diamagnetic substance it is small and negative, for paramagnetic it is small but positive, for ferromagnetic it is positive and large. Okay, next is effect in a magnetic field. Induces a magnetic field, magnetic moment in the opposite direction of the applied field. Here induces a magnetic moment in the same direction of the applied field. Here induces a magnetic moment in the same direction, but it is a very strong magnetic field in the direction of applied magnetic field. Okay, now next question, mention any 3 properties of magnetic field lines. Another very common question, possibly asked multiple times again. So any 3 properties, easy question. The magnetic field lines of a magnet form continuous closed loops. The tangent to the field line at a given point represents the direction of the net magnetic field at that point. The magnetic field lines do not intersect, for if they did, the direction of magnetic field would not be unique at the point of intersection. So let me explain the third point, but before I have to explain the second point. So if you have a magnetic field line like this, and if you draw a tangent at any point, that line gives you the direction of magnetic field at that particular point. But suppose 2 field lines intersect at some point, okay, then what will happen at the point of intersection? At the point of intersection, we will have one field line in this direction, another field in this direction, so 2 separate field meeting at a same point. So practically what will happen? Practically they will not give you neither this nor that, but you will get a resultant magnetic field which will be like this. Okay, so these 2 field lines will never exist, and you will not get a crossover of 2 field lines. Even if you bring 2 magnets closer to each other, they will give you a resultant field, not a crossing field. Okay, so 2 field lines will never cross, even if they are coming from 2 different magnets or more than 2 different magnets, they will never cross each other. Okay, remember that, because magnetic field is a vector quantity and it has a uniqueness. What is a uniqueness? Every vector quantity has a unique direction. Any vector quantity, okay, any vector quantity is unique, and they only have one direction, not multiple direction. Define magnetization of a sample, how it is related to magnetic intensity. Magnetization M of a substance, magnetization M of a substance is measure of the net magnetic moment per unit volume of the material. Okay, So it is given by M equals to net magnetic moment divided by volume. Okay, relation between magnetic intensity and susceptibility is given by M equals to chi H. Okay, here chi is called magnetic susceptibility. Okay, chi is called magnetic susceptibility. The pronunciation for this is chi. Okay. State and explain Gauss's law of magnetism. Another very common question. Gauss's law for magnetism is very easy. Unlike Gauss's law for electrostatics, magnetism one is actually 0 on the right hand side. So whenever we see 0, except for marks, we feel happy, right? So if you see 0 in your mark sheet or score sheet, you get disappointed. But if you have to write the 0 as an answer, maybe for an MCQ, maybe for a question answer, then we feel happy because we don't need to do too much for it, right? So this is one of them. So the net magnetic flux through any closed surface is 0. Okay, that is the major thing, and you can write a small s over here. Physical significance. What is the physical significance? Magnetic monopole do not exist. Okay, so in case you see any magnetic monopole, then it would have been magnetic monopole by mu naught or mu naught into magnetic monopole moment, but that is not there. Magnetic monopole do not exist. So on our right hand side we can easily write 0. Okay, magnetic field lines always form closed loop. Okay, so magnetic field lines always form closed loop. That means whatever exit from north pole, it will not only go to south pole, it will also come back to north pole via inside route of the magnet. Okay, that is the major difference between electric field and magnetic field. Okay, now which materials show perfect diamagnetism? Write the susceptibility and relative permeability values for such material. Again, this is a question from your model question paper, latest model question paper. Superconductors show perfect, not model question paper, sorry, it is from question bank. This question is taken from your question bank. Superconductors show perfect diamagnetism. Superconductors, okay, so far we have not discussed too much about superconductors, but this question is given in your question bank, might be coming, but easy question, not super difficult to remember either. That's why I decided why not include it. Superconductors show perfect diamagnetism. For such materials, magnetic susceptibility is exactly equals to -1. Remember this, for superconductors, susceptibility is exactly equals to -1, and you might see one MCQ question also can come from this information. Okay, one MCQ question can sometimes come from this information. Also, superconductors are called perfect diamagnets. Okay, they are also sometimes called perfect diamagnets. Why? Because their susceptibility is -1. So remember this simple facts. Okay, so they are called perfect diamagnets. Relative permeability exactly equals to 0. Relative permeability is exactly equals to 0. Now next, derive the expression for magnetic potential energy for a magnetic dipole placed in an uniform magnetic field. Now you might seem this is a new question. Actually it is not. It is the same derivation for electric dipole. Only difference is that the terms are different. Okay, so in case of magnetic dipole also, electric dipole also, we did this derivation. Okay, not the torque but the magnetic energy. Okay, potential energy. Suppose we have a magnet inside a magnetic field. So this is north, this is south. Okay, and when you place it inside a magnetic field B, okay, there will be a torque that will act on it. And if you want to derive the expression for torque, it is same as electric field. Only thing you have to take magnetic monopole moment for individual poles, strength of individual poles, and then you have to calculate it. But here for this case we do not need to do that. What we will be doing, we will be directly taking the expression for torque. Now for electric field, if you remember, torque was given by PE sin theta. PE sin theta. Okay, but for magnetic torque it is given by MB sin theta. Okay, sin theta is same, only instead of P we are writing M, for E we are writing B. M is magnetic dipole moment and B is magnetic field. Okay, now initially suppose this thing was at an angle theta. Okay, initially it was at an angle theta. Now if you slightly rotate it by a small angle, if you rotate it by a small angle, say d theta, then how much work you need to do? The work that you need to do is given by dw to rotate the needle, magnetic needle, we are assuming magnetic needle or magnetic dipole, okay, to rotate the dipole by a small angle theta, d theta, the work done is dw. Why we are taking small rotation? Because as you know, torque depends on the angle theta. So if you change the angle by very large amount, then the sin theta value changes drastically. That value of torque will also change. But if you change it by very small angle, we can still consider the previous torque is still acting on it, and we can apply the formula for work done, which is given by force into displacement for normal case, torque into angular displacement for rotational case. Okay, torque into rotational displacement in case of rotational motion, force into displacement for linear motion. So this is the small angle d theta. So the work done is given by mb sin theta d theta. Okay, now what is the total work done? Total work done must be equals to integration of this entire thing. Okay, that is our technique. Okay, we do integration. What is the meaning of integration? Integration represents taking small portions and adding it. Okay, so we will take small angle d theta 1, d theta 2, d theta 3, and corresponding sin thetas also we will take, and we will add them, then we will get the integration, right? Integration is basically type of addition. So what is the angle? What is the starting point? Starting point has to be where the potential energy is 0. Generally we consider potential energy is 0 when it is at an angle theta equals to 90 degree. Okay, theta equals to 90 degree or pi by 2, that we consider as our 0 point. So here we will start at theta equals to pi by 2 and we will end up at some angle theta. Okay, so from pi by 2 to theta, how much work we are doing? Starting point, ending point. Now let's do the integration. So mb is constant, by the way, so it will come out of integration. So only integration is left is sin theta d theta, and limit is pi by 2 to theta. Now what is the integration of sin theta? By this time I hope everyone has completed the integration process and already aware what is the integration of theta, sin theta, right? Like unlike in your PU1 when physics teacher was trying to teach you integration, differentiation, you are thinking what is this? This is a completely hard subject. I am not able to understand. But now everything is very much easier, because you think okay, physics, mathematics is much easier compared to that of mathematics, right? I hope you have the same feeling. We all had gone through this situation once in our life. Okay, so mb, w equals to mb, and integration of sin theta is minus cos theta. Okay, it is minus cos theta. Now we will put the limit pi by 2 to theta. Now how to apply the limit? First we will apply the upper limit. Upper limit is theta, so minus sign we are taking common. Okay, minus sign we are taking common outside. So cos theta is again cos theta only, and minus the lower limit cos 90 degree or cos pi by 2. Now what is the value of cos pi by 2? Value of cos pi by 2 obviously 0. So we get work done is minus mb cos theta. And this work is being stored as the potential energy of the magnetic dipole. So the energy of the magnetic dipole is basically minus mb cos theta. Okay, so this is the expression for energy. and if you do this small derivation you will get full 3 marks. And as you have already understood, this is nothing different than that of electric dipole. Only thing is the names are different. In case of electric dipole it was PE, it is MB in magnet. Okay, nothing else is different, everything is same. Now list any 3 properties of paramagnetic substances. Now this is the same question that we have done in the previous one, that when we are doing the difference table. So if you remember the difference table, you can still answer this question. Okay, these are nothing different than that of the difference table. Okay, but this question can also come, so you have to prepare your mind about this. The 3 properties of magnetic substances: these are weakly attracted by magnetic field, they have small positive magnetic susceptibility, these materials introduces a magnetic moment in the same direction as the applied field. So these are the 3 properties. Next, list any 3 properties of diamagnetic materials. 3 properties of diamagnetic substances are: they are weakly repelled by magnetic field, they have small negative susceptibility, these materials induces a magnetic moment in the opposite direction of the applied field. List any 3 properties of ferromagnetic substances. 3 properties of ferromagnetic substances: these are strongly not repelled, strongly attracted by magnetic field, they have a large positive magnetic susceptibility, these materials introduces a strong magnetic moment in the same direction of the applied magnetic field. Okay, so these are the 3 points of ferromagnetic materials. Now what are hard ferromagnets and soft ferromagnets? Give example of is easy question. Hard ferromagnets: in some ferromagnetic materials the magnetization persists even after external magnetic field is removed. Such materials are called hard ferromagnetic materials or hard ferromagnets. Example: alnico, steel. These are examples of hard ferromagnets. Soft ferromagnets: these is a class of ferromagnetic materials in which the magnetization disappears on removal of the external magnetic field. Such materials are called hard magnetic materials or soft ferromagnets. Example: soft iron. Okay, soft iron is an example. Another one is, you can say, pig iron. Okay, soft iron, pig iron, they are example of soft ferromagnetic materials. So blueprint of this chapter: 2 questions will come as 1 marker, so that means we can expect one MCQ question and 1 fill in the blanks question. So both type of question will definitely come from this chapter, as well as we also have a 2 marker question and 3 marker question. So total marks allotted for this chapter is 7. Okay, now one important part from this chapter is that sometimes there is a possibility that a 2 marker numerical or a 3 marker easy numerical, all of the numericals coming from this chapter are easy and formula based. So there is a small possibility that you might face a question based on numerical based question from this chapter. Okay, but other questions are again important. So what are all the questions we are going to discuss? We are going to discuss 15 MCQs as usual. We are also going to discuss 5 fill in the blanks, 5 2 marker question and 5 3 marker questions. To total 30 questions I am going to discuss in very quick time. So let's start with the first question. The energy stored in an inductor of inductance capital L in establishing the current in it is. So what is the energy stored in an inductor? Energy stored, work done is same, both are given by half Li square. So correct answer is half Li square. So option D is correct answer. Okay, so this same question might be coming as what is the work done to establish a current in an inductor? What is the work done to establish a current in a conductor? What is the energy stored in an inductor? Everything will have the same formula, half Li square. Now the following are the statements related to self-inductance. So there are 2 questions related to self-inductance. The self-inductance of a coil depends on its geometry and on the permeability of the medium inside it. Second point says that the self-inductance is a measure of electrical inertia and opposes the change in the current in the coil. Now self-inductance depends on the mu naught or mu that is permeability of the medium. It also depends on its area, depends on its length. So this statement is a true statement. This is also a true statement, okay, because self-inductance acts like inertia. Now if you forget what is inertia, suppose you are at rest. Okay, I am asking you, please go and study. So what is your inner motion is saying? Sir, ignore sir, I don't want to study right now. So basically it's like the inertia of your initial inertia which is stopping you from being studying. So if you are studying right now and if you are very deeply into the studies and someone asks you, hey, can you come and do something for me, then you will say, no, I am studying, I don't want to go right now. So that is another inertia, okay, that is a good inertia, one is bad inertia. So there are also inertias of motion, inertias of rest. So when the object is at rest, it does not want to move, it wants to stay at the state of rest. Similarly, if an object is moving, it always wants to stay in the state of motion and it does not want to stop. So these are the two types of inertia that we have learned in mechanics. Now electrical inertia means when electron is trying to flow through a conductor, okay, initially it does not want to go through that motion, and that stopping, whatever is stopping that is actually the self-inductance, okay, and self-inductance acts, that's why it is called self-inductance, acts like electrical inertia. So it's trying to stop the current, okay. So that is why the second statement is also correct, okay. Both statements are correct, both statements are correct. So option C is correct for this question. Now next question, magnetic flux is a scalar quantity and its SI unit is Weber, okay. Magnetic flux is a scalar quantity and its unit is Weber. So correct answer is this, option B, okay. Now let's move on to the next question. This is actually a two question. Instead of giving them separately, I have given them in one question because options are same. The polarity of induced EMF in a coil is given by dash, okay. Or another version of the question, which of the following is a consequence of conservation of energy? Both questions have same answer and you guessed it correctly. It's Lenz's law or Lenz's law, okay, whatever you say it, Lenz's law, okay. So that determines the polarity of the induced coil. Also it is the consequence of conservation of energy. We will see that in a while in a descriptive question how it is related to conservation of energy. So that's this is the question. Both questions have came in the past and might come in the future as well. Just you need to remember what is the language and answer. Next question, current in a coil changes from 1.6 ampere to 0.2 ampere in 2 seconds, inducing an EMF of 2.8 volt. The value of self-inductance of the coil is. So they asked you what is the self-inductance of a coil. We know that in case of self-induced coil, the induced EMF is given by the self-inductance into di upon dt, change in current, okay. So similar to that of normally if induced EMF is given by n d phi by dt, right, from Faraday's law. There is a negative sign, but this is the normal expression for the magnitude, right. Here they asked you that again there is a negative sign here as well, but because current is decreasing we can ignore the negative sign, but current decreases from 1.6 ampere to 0.2 ampere. So what is the change in current? Change in current is given by 1.6 minus 0.2. So it was initial value, it changed to 0.2. So the change is 1.4. Okay, so this is the change in current. Change in current is basically difference between two currents. Okay, 1.4 is the change in current. Now what is the time given over here? Time given is 2 seconds. So if you divide it by dt, it will be 2 seconds and you will get 0.7. Okay, so 0.7 is the value of di by dt, and induced EMF is given by 2.8. so just put the values. So 2.8 is the induced EMF, L is unknown, and di by dt is 0.7. so L is equal to 2.8 divided by 0.7, that is 4. Okay, so correct answer is 4 Henry. Correct answer 4 Henry. Okay, next question. The dimensions of inductance is. So dimension of inductance is, how to calculate this? So for that we will use a basic rule that energy, okay, energy stored in an inductor is given by half Li square, right? We already discussed it in one of the MCQs that energy stored, work done, etc. is given by the same formula, which is half Li square. Now it is very difficult for us to understand what is the dimension of inductance if we start from any other formula. This is the easiest formula to start with. Why? Because energy is same as that we learned in our mechanics. Now what was the energy formula? If you remember, energy or work done, that was given by force into displacement, and there was a cos theta, but if they are in the same direction, theta is cos theta is 1, so Fx. Okay, what is the dimension for F? This is the one dimension that you have to remember. There is no other way. What is the dimension of force? Dimension of force is mL t to the power of -2, mass into acceleration. Okay, mL t to the power of 2 is the dimension of force. What is the dimension of x? X is nothing but length, so you multiply them. So mL t to the power of -2 into L, that means the dimension of Fx or energy is given by mL square t to the power of -2. This is the easy dimension. You can remember this dimension, or you can formulate what is the dimension of energy. Now that dimension we know. So dimension of energy is mL square t to the power of -2 equals to, this half is dimensionless, so dimension of L and dimension of current. So what is the dimension of current? Dimension of current is known, it is A, so A square, right? I square is there, so that means dimension will be A square. Now you can find the dimension of L. So dimension of L is given by mL square t to the power of -2 a to the power of -2. This a comes to other side and becomes to the power -2. Okay, so the correct answer is mL square t to the power -2 a to the power -2. Option A is correct. Okay, this question is one of given in one of your model question paper. So if you are wondering, sir, why we should do the difficult question, this is given in your model paper, so you have to do it. Now next question. Which of the following quantity is measured in Weber per ampere? So Weber per ampere, what is Weber? Weber is magnetic flux. Weber is magnetic flux. Okay, and you are trying to find what is Weber per ampere. So Weber per ampere means if you divide flux with current, you get self-inductance. You get self-inductance. This is nothing but self-inductance. So self-inductance is the unit of Weber per ampere, also called Henry. Okay, Weber per ampere and Henry are same. An AC generator is a device used to convert electrical energy into mechanical energy. Device used to convert mechanical energy to electrical energy, both A and B, none of the above. So AC generator is something which generates AC. Okay, generates AC means, what is AC? AC is a alternating current. AC means alternating current, right? So basically AC generator is generating alternating current, that's why it is called AC generator. Okay, and generation means it has to generate from somewhere. So what form we are using? We generally use rotational motion of turbine to generate electric current. So basically it's a device used to convert mechanical energy into electrical energy. So all the places where you have heard that hydroelectric power plant, coal power plant or windmill, they all are basically an AC generator, okay, which is generating AC by using some other form of energy, mainly mechanical energy. Okay, even if you are using hydroelectric power plant where you are using energy stored in water, basically the energy stored in water is basically the mechanical energy. That mechanical energy is given into a rotator turbine. That turbine rotates with the high speed, and because of that the power is getting generated. Okay, that is the major principle. Okay, except solar power plant. Solar power plant can directly convert energy, solar energy into electrical energy. Okay, where we use solar cell. Other than that, all the forms of energy are basically coming from our AC generator, and AC generator always converts mechanical energy to electrical energy. The SI unit of mutual inductance, Henry, okay, or Weber per ampere, both are same, so Henry is the answer. The expression for motional EMF is BVL or BLV, okay, so this is the expression for motional EMF. Next, the magnetic flux through a surface of area A placed in an uniform magnetic field B is defined as, so magnetic flux is defined as phi equals to B dot A. Phi equals to B dot A. So this is the magnetic flux, so this is the correct answer. Next, to induce EMF in a coil, the magnetic flux linking must remain constant, must increase, must decrease, both B and C. It can increase or it can decrease, both is possible. As long as it is changing, there will be an EMF induced linked with the coil, okay. So as long as magnetic flux changes with time, with respect to time, okay, there will be an induced EMF. So both B and C is correct. If it is increasing, the current direction of current in a particular direction. If it is decreasing, the direction of current in the opposite direction. So only the direction of current will change, but as long as it changes, okay, as long as magnetic flux linked with the coil changes, there will be an induced EMF. Next question. When a magnet is moved with its north pole towards a closed coil, the nearer end of the coil acts as. So here is a coil and you are moving a north pole towards the coil, okay, towards the coil. So the north pole is moving towards the coil. That means this near end of the coil must produce another north pole so that it tries to stop the motion. That is the Lenz's law. Lenz's law says that the direction of current is such that it tries to stop or oppose the cause of the motion. So cause of the motion is the motion of the north pole, so that's why it will produce a north pole in the side of the coil facing the magnet, okay. So the nearer end of the coil will be a north pole, so correct answer option A. Next question. The magnetic flux linked with the coil varies as phi equals to 2t square plus 2t. What is the magnitude of induced EMF at t equals to 0.5 second? So phi is given as 2t square plus 2t. So induced EMF is d phi by dt at t equals to 0.5. So that is 4t plus 2, and we have to put the value of t as 0.5. So 0.5 into 4 is 2, so 2 plus 2, that is 4 volt. Okay, I think the options are given here in wrong, so correct answer will be 4 volt. So 1 volt, 2 volt, 3 volt, 4 volt. So correct answer will be 4 volt, option D. Next, the SI unit of magnetic flux is Weber per meter, Tesla per meter square, Weber per meter square. So again it's Weber, again it is from your model question paper. They have directly asked what is the SI unit. Okay, in one of our previous question it was asked whether it is a scalar quantity or vector quantity. So it's a scalar and unit is Weber. Now next, now you have to solve fill in the blanks question. The device which works on the principle of electromagnetic induction is. So which of the device works in the principle of electromagnetic induction? Let's see. Magnetic potential energy, is it a device? It's not a device. Conservation of energy, is it a device? Not a device. Inertia, is it a device? Not a device. AC generator, is it a device? Yes, it is a device. Is there any other device mentioned here? Alloys and opposes. Alloys and opposes again are not a device. So only AC generator is a device. So it's an easy answer. Even if we don't know, we can guess the answer. It is AC generator. Lenz's law is based on conservation of energy. Okay, it's based on conservation of energy or consequence of conservation of energy. So we also know the second answer. Self-inductance plays the role of electrical inertia or normal inertia. Okay, so basically self-inductance plays the role of electrical inertia is more accurate, but inertia is also fine. The energy stored in a inductor, energy stored in an inductor in the form of, so energy stored in a inductor is in the form of magnetic potential energy. It is called magnetic potential energy. So from the option we can see that magnetic potential energy is the correct answer. Induced EMF always dash any change in the magnetic flux. So again this is a statement of Lenz's law which says that it always opposes any change in the magnetic flux. So correct answer is opposes. Okay, so this is opposes. Okay, so fill in the blanks are also done. Now let's move into the 2 markers category. Give the principle of AC generator. Why is a current induced in an AC generator called alternating current? Very interesting. Mention the expression for induced EMF in it. Okay, so either this question will come, give the principle of AC generator, why the current induced in an AC generator called alternating current, or give the principle of working of AC generator, mention the expression of induced EMF in it. So this is actually a 2-mark question when principle and expression or principle and why it is called AC, this question will come. All three questions generally will not come. If all the 3 are coming, then it will be a 3-marker question. Now what is the principle? An AC generator converts mechanical energy into electrical energy by changing the flux linked with this rotating coil. So here is a rotating coil, and as it is rotating, the flux linked with the coil changes, and that's why there is an induced EMF. And induced EMF means it produces current as well, because EMF is the source of current, it's a parent of current. Okay, the direction of the current produced in an AC generator changes periodically. Okay, so the direction of current produced in an AC changes periodically, and therefore the current is called alternating current. Normally the current that we have used so far in our current electricity chapter was a DC current, direct current. Direct current means, suppose this is the value of voltage, okay, and this is time. So DC current means it does not change its direction, it remains same. But when you talk about AC current, okay, so what happens in this case is that if you are considering the voltage, okay, the voltage alters every now and then. Okay, there is a fixed time interval after which the direction of the current changes, and as you move on the with time, okay, after each and every time it will change its direction, and that's why it is called AC. So this is an example of AC current. Okay, the voltage value changes, plus and minus, whereas in direct current the direction of current remains same. Okay, the expression for induced EMF in a AC generator is given by NBAW omega T. Now if this question is asked, you have to mention what is N. N is the total number of turn. What is B? B is the magnetic field. What is A is area. And what is omega? Omega is angular speed. Right? So you have to mention these terms as well to get the full marks. Now, next question. State Faraday's law and Lenz's law of electromagnetic induction. Okay, Faraday's law, the time rate of change of magnetic flux through a circuit induces EMF in it, and Lenz's law, this came only once. Most of the time it came was Lenz's law. Okay, the polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produced it, and it is basically minus d phi by dt. So this negative sign comes from Lenz's law, and this d phi dt comes from Faraday's law. D phi dt is due to Faraday's law, and minus sign comes from Lenz's law. mention any two factors on which the self-inductance of the coil depends. So self-inductance formula is given by mu naught n square A into L. Self-inductance is directly proportional to the square of the number of turns per unit length. Self-inductance directly proportional to the cross-sectional area A of the solenoid. Self-inductance is directly proportional to the length of the coil. In fact, if you take most general expression, then instead of having mu naught, it will be mu. Okay, so L will be mu n square AL. Okay, so in that case, even you can mention that self-inductance is directly proportional to the permeability of the medium. That is also true. Okay, so here we have only taken n square, A and L. Now 2 factor means any 2 will be fine. If they ask you 3 factors, that's why you have to remember all the factors, and if you remember the formula, that will be very helpful to write this question, answer this question. Okay, so that's why I have given 3 options, even though it's mentioned in 2 marker, even though 2 options are given in this question. But if the same question is asked as a 3 marker, then also you should know how to write it. Okay, now next question, calculate the magnetic energy stored in a coil of self-inductance 0.05 Henry carrying a current of 0.2 ampere. This is again taken from your model question paper. Okay, so let's see. So energy is given by U equals to half L I square. Okay, so the value of L is given here 0.05 and current is given as 0.2. Just put the values, use your calculator and calculate it. Okay, half 0.05 into 0.2 into 0.2. So it will cancel, you get 0.1, or you get 0.2 into 0.05 is 0.01 into 0.1, that is 0.001 joules. SI unit of work done, energy is joules. So correct answer is 0.001 joules, and if you solve it, you will get full marks, full 2 marks. Simple answer, nothing to worry. Even you can use your simple calculator to calculate it. Now next question. An aircraft with wingspan of 40 meter flies with a speed of 300 meter per second in eastward direction at a constant altitude in the northern hemisphere, where the vertical component of the Earth's magnetic field is 1.75 into 10 to the power of minus 5 Tesla. Calculate the EMF developed between the tips of the wing. So there is a plane which is flying. Okay, the wingspan is given. Okay, it is flying from west to east or west to east? Eastward. It is flying eastward. So it is flying in eastward direction, and the vertical component of magnetic field is given over here. Okay, and they are asking what is the EMF induced between the wingspan of the plane. So that means we will using a simple formula. Whenever there is a motion of an object in a magnetic field, there is an induced EMF, and that is given by BVL. Okay, what is B? B is given over here, so no need to worry, everything is given. 1.75 into 10 to the power of minus 5. Velocity is given 300 and L is given as 40 meter. So if you multiply everything, it will be simple problem. 4 into 1.75, 2, 6, 3 and 4, 7. So 1 into 1.75. So 1.75 is 5, 6, 7 by 4. Okay, so 1.75 is 7 by 4. So 7 by 4 into 10 to the power of 5 into 300 into 40. So this cancels and we get 10 over here, 10 over here. So 3 7s are 21 and 1 2 3 zeros are here, so it will be 10 to the power of minus 2 or 0.21 volt. So you will get 0.21 volt as induced EMF. Now next, Derive the expression for motional EMF induced in a straight conductor moving perpendicular to uniform magnetic field. So first of all, you have to draw this diagram and show the magnetic field is either out of the paper or into the paper. Here we have taken the magnetic field into the paper. So into the paper means cross, out of the paper means dot. Okay, so this is the basic meaning. The cross means this is your target, so that means it is going into the paper. Dot means it is coming out. Okay, okay, so this is how it should look. Now what you have to do, you have to take the velocity of the rod which is moving is given by v. This is x and this is L. Okay, this length is L. So this length is L, this distance is x. Now we have to apply Faraday's law and we have to calculate the induced EMF. Faraday's law as well as Lenz's law, both law you will apply. So first of all, what is the flux linked with this coil? So flux linked is given by, magnetic flux linked with the coil is given by the magnetic field times area. Okay, cos theta, in this case theta is equals to 0 degree, so that's why it is only BA. Okay, perpendicular, in the case of perpendicular theta becomes 0 degree, so it is B dot A. Now phi is given. Now what we have to calculate is what is area A over here. So this is a rectangular frame, right? So rectangular frame means area is length into breadth. Length into breadth is the area. So flux linked with the coil is given by B into length into breadth, that is L into x. So phi we know. Now you have to calculate the induced EMF. What is the formula for induced EMF? Induced EMF is given by minus d phi by dt. Right? Why minus? Because of Lenz's law there is a negative sign. So we have to differentiate it with respect to the speed. So we get epsilon equals to B into L into dx by dt. So when we differentiate this, B is constant, the length is also constant, only thing which is changing is this x. As it is moving over towards this side, okay, the x value is changing, and x value is not only changing, it is decreasing. Okay, so x value is decreasing. So from there we can say that velocity of this rod is given by minus dx by dt. Now why this is negative sign? Because x is decreasing with time. X is decreasing with time, that's why velocity is given by minus dx by dt. So therefore we can write epsilon equals to BLV. Okay, so this is the expression for induced EMF in a coil. This is the expression for induced EMF in a coil. Now next, describe an experiment to demonstrate the phenomenon of electromagnetic induction using a bar magnet and a coil. So this is the bar magnet and coil experiment. This question has came in the past and also given in your model question paper in a different form. So that's why I thought this question, and if you are preparing for preparatory, this question is a common question which is coming in preparatory from many previous years. So let's see. So here first of all you have to draw this diagram where you have to show the coil and a magnet. The magnetic field lines, you have to clearly show these magnetic field lines, and there is a galvanometer which is deflecting. Okay, so when the magnet approaches the coil, and if you can describe the image by one line, okay, otherwise this is sufficient answer. When the magnet approaches the coil, the galvanometer needle deflects, indicating a current is induced. When the magnet is pulled away, the needle deflects in the opposite direction, showing that the current reverses. No current is induced when the magnet is stationary relative to the coil. So these are all the observations. Okay, so when you are taking the magnet towards the coil, there is a deflection observed in the galvanometer. When you pulling the magnet away from the coil, okay, the deflection is in the opposite direction. That means the current induces in the opposite direction. And if the magnet is not moving, no current is induced, that means total induction is 0. Conclusion. So this is the explanation part. Okay, this experiment demonstrates the electromagnetic induction. A current is induced in the coil when the magnetic flux through the coil changes. This confirms Faraday's law of induction, and the direction of the current follows Lenz's law opposing the change in the magnetic flux. So these are the 2 points that you have to remember. Not super difficult, easy to explain. You don't need to write the entire detail of the experiment. This is the main crux of the experiment. That is what you have to write, core of the experiment. You should not skip anything in there. Okay, but the diagram is compulsory if they ask you magnet coil experiment. Now next question, a horizontal straight wire 10 meter long is falling with a speed of 5 meter per second at right angles to a magnetic field of 0.3 into 10 to the power of minus 4 Tesla. Find the instantaneous value of the EMF induced in the coil. Again, the formula for this is also same, that is BVL. So sometimes the same problem can be asked as a 2 marker, sometimes the same problem can be asked as a 3 marker. Does not matter, as long as you can answer them, as long as you can solve them, and the formulas are very simple, straightforward, and you should get marks if you answer it. Okay, speed falling with the speed is 5 meters. So don't pay too much attention into the problem. You just need to think that the formula, only one formula which will fit for this problem is this BVL. So just put that. Length is given 10 meter. Okay, so it will be 3 5s are 0.3 into 5 is 1.5 into 10 to the power of minus 3 volt. Okay, so 1.5 millivolt or 1.5 into 10 to the power of minus 3 volt. So this is the correct answer. Okay, 1.5 millivolt. Okay, or 15 into 10 to the power of minus 4 volt. Any one form is correct. Okay, so I thought this might be the correct approach. Any one answer is, as long as the 10 to the power value is correct, you will get full marks. Lenz's law is the consequence of law of conservation of energy. Explain. This is the question I was talking about during the fill in the blanks. When a changing magnetic field induces a current in a conductor, the current creates its own magnetic field. According to Lenz's law, this new magnetic field opposes the change that caused it. So first of all, let us understand this. This is a very important point. So we know that whenever a current is passed through a conductor, it produces a magnetic field. It can be, if it is a straight wire, we know the formula. If it is a current carrying circular coil, we know the formula. Okay, in the previous chapter we have learned that whenever a current is passed through a conductor, it produces a magnetic field, right? So current and conductor is needed to produce a magnetic field. Now in this chapter, what we are dealing with, we are changing some external magnetic field, and that changing magnetic field is producing an induced current, right? So whenever a current is we are trying to produce a current, okay, for that what we are doing, we are adding some external magnetic field into the picture. So first, this case, no external magnetic field is there, only current in a coil, and current produces magnetic field. Now we have reversed the idea. We are adding some external magnetic field, and that magnetic field is now producing the current. Coil magnet experiment. Okay, in the coil magnet experiment we did that, where we had a coil, we had a circuit, and we say if we can change the magnetic field linked with the coil, okay, it produces a magnetic field, right? So this is how this works. Now magnetic field producing current, but basic property of current in a conductor is that it will also produce its own field, right? So this magnetic field is producing the current, right? But the current on its own right can also produce magnetic field. So what will happen, what should be the relationship between these two magnetic fields? Okay, one magnetic field is the original magnetic field which is responsible for creating the current. The current is also producing the magnetic field which is basically in response of the original magnetic field. So this is called induced magnetic field, and this induced magnetic field will oppose the cause. So suppose a north pole is moving towards it, then there will also be a north pole which will be produced in this end of the coil, so that they repel each other. That is basically Lenz's law. So Lenz's law is basically talking that if there is a magnet which is approaching a coil, whatever surface which is facing the magnet, the pole which is induced will be opposite. That's it. Now let us understand with explanation. If the induced current did not oppose the change, so suppose instead of opposing it, it supports it. Suppose, okay, we are just taking a hypothetical case where this is a south pole. Okay, so it would create a runaway situation where the system gains energy without any input. So what is the meaning of that? Suppose a south pole is created over here, a north pole is already there. Now you are trying to push the magnet. Now what happens, this south pole, after some time, when you are pushing the magnet towards the coil, after some time this south pole will be strong enough so that it can attract the magnet towards it. Okay, so it will be strong enough to pull the magnet towards it. So you don't need to do any work. The magnet will automatically move towards the coil. It will go away and again it will come back. So like automatically the magnet will start oscillating and you will start producing current without doing anything. So if that was possible, then electricity would have been absolutely free of cost. There would be no charge, nothing. You don't need to pay anything, and you can produce energy out of nothing, which is prohibited by conservation of energy. Okay, so you to produce energy you have to spend some energy, right? That is the conservation of energy. Okay, so that this effect is called a runaway effect. So automatically energy is getting produced without doing anything is called runaway effect. Okay, where the system gains energy without any input, violating the law of conservation of energy. For example, if you move a magnet towards a coil, the induced current generates a magnetic field that repels the magnet. You must do extra work to push the magnet closer to the coil, and this work is converted into electrical energy. Thus, no energy is lost or created. It is transformed from mechanical energy to electrical energy. So, because you are pushing, when you are pushing the north pole, and because there is a north pole which is being produced over here, you have to do some mechanical work to keep on pushing the magnet. So when you are pushing the magnet towards the coil, okay, you have to keep on pushing it so that it is not an automatic effect. You have to do some external work to produce that energy. Okay, so this is why, this is a consequence of conservation of energy principle, and Lenz's law also coming from the fact that it is a law of conservation of energy. So this is a new question, might be asked in your paper, so be prepared for this question. Now, derive the expression for magnetic energy stored in a coil. This is from your model paper. Last question of the day. Prove U is equal to half Li square. Okay. Now, how to do that? First of all, suppose we have a coil, and you have established some EMF around this coil by doing some external work. Say the EMF is epsilon. Okay, the self-induction is L. The current that is flowing in this is given by I. Okay, so you developed some back EMF which is given by epsilon. So what is the work that you have done to establish this current? That is very, very important. The work that you do to establish this current is given by dW by dt equals to epsilon into I. Okay, epsilon into I. So you remember that the work done or heat developed in a circuit was given by VIT in electrical circuit. Okay, so that is equivalent to work done. So if you consider H by T, then it will be V into I. So in this case V is nothing but EMF, current is I. Okay, so this is exactly what we know. Okay, so but the form is slightly different. Instead of heat energy, we are considering work done. Okay, work done and energy are related. So from that fact, if you forget it, the work done per unit time is given by induced EMF into current. Okay, induced EMF into current is the work done. Now what this induced EMF in a coil of self inductance L is given by L di by dt. Only we are taking magnitude. Okay, if you consider negative sign, then there will be a negative sign, but we are not using that. We are only using the positive sign. Okay, so epsilon is basically di by dt. So if you put that, you will get dw by dt equals to L di by dt into this I. Okay, now this dt and dt can be cancelled, so we get dw equals to Li di. Now what is the total work done? Total work done is given by 0 to W. Initially work was 0, dw, that is equals to 0 to I. To establish the current from 0 to I, Li di. Now L is constant, so it will come out of integration. So you will get integral I di. What is the integration of I di? I di is similar to x dx. Okay, so what is the integration of x dx? X square by 2, right? Now 0 to I is the limit, so that does not change anything. So L into half I square. 0 to I you can put, and you will say that for 0 it becomes 0, only for I it left, so you get half Li square. Now here we have calculated the work done, but in the question they asked you the energy stored. From the definition we know that energy stored is basically work that you do, that is equals to half Li square. So this is the derivation, easy derivation, and if you do this you will get 3 marks. Okay, alternating current, and then once it is over we will going to discuss EM waves. Okay, but first, before I continue, I request you please subscribe to our channel, share this video with your friends so that they can also learn and score well in your PU2 exam, right? So this is the guide towards your 95% plus in your PU2 board exam, so don't miss out on this. Now let us look into the blueprint of the chapter. So first of all, 1 marker question are 2, so that means we can expect 1 MCQ as well as 1 fill in the blanks from this chapter. There are no short answer type 2 marker or 3 marker questions from this chapter. Straight away 1 5 marker question, and as I mentioned, we are expecting a numerical question from the previous year trend and as well as the model question paper. So we are going to solve 5 numericals from this chapter. So how the discussion going to happen today? So 15 MCQ questions we are going to discuss. We are also going to discuss 5 fill in the blanks and 5 numerical problems. Very important pattern questions are being discussed in this. So if you watch this, definitely you should be able to answer one of the numerical questions that is going to come in your board exam. Now let us start with MCQs. The resonance frequency of a series LCR circuit remains constant even if there is any variation in the value or values of L, C, both L and R, option D, R. Now we know that frequency, resonance frequency in case of series LCR circuit is given by 1 upon 2 pi square root of L into C. Right, this is the formula for frequency. So we see that if any one of them, L or C, change, then the value of frequency will change. So only if the value of R is changed, the resonance frequency will remain unchanged. So resonance frequency is independent of resistance. So that is the main question. So if you understand that, then you should be easily be able to answer it, right? So frequency is basically independent of resistance R. Next question, when alternating voltage is applied to a resistor, which of the following statement is wrong? So very important, here they asked you which of the following statement is wrong. That means 3 statements are correct, only one of them is wrong. So be careful for such questions where they ask you which of the following is wrong, which of the following is correct. So be careful on such cases. The average current over a complete cycle is 0. This is a true statement. Average current in a complete cycle is 0. It goes up and down, so it's a sine theta. Average of sine theta is 0. The average voltage over a complete cycle is 0. This is again true statement. Okay. Next, the average power dissipated by the resistor over a complete cycle is 0, but average power dissipated in a resistor is not 0. For inductor and capacitor, average power dissipated is 0, but for resistance it is not 0. So this is a wrong statement. So this is our correct answer. You can check the option D. The phase difference between the voltage and the current is 0. Yes. So in case of only single resistor, the current and voltage both remain in the same phase. In case of inductor, current lags by pi by 2. In case of capacitor, current leads by pi by 2. Okay. So here the average power dissipated in a resistor is not 0. Next question, in a transformer, the windings of the primary and secondary coils are wounded one over another to reduce the energy loss due to flux leakage. So just for your information, in this chapter there is a part called transformer, and in your pre-board there is a high possibility 1, 2 or 3 marker question might come from this power loss in a transformer. Power loss in a transformer is very common type of question. So just prepare it for MCQ as well. So power loss in a transformer, there are 3-4 different types of power loss and how to prevent it. Based on that, we have seen some MCQs coming in your question bank as well as in your previous year paper. So be prepared for such question. Okay, so here what when one coil is wound over another, so that the flux that is coming out of the primary should go completely through the secondary. That's why it is done to reduce the flux leakage. Now next question, in case of alternating voltage applied to a resistor, the current leads the voltage by a phase difference of pi by 2. No. The current lags behind the voltage by a phase angle of pi by 2. No. The current and voltage are in same phase. Yes, this is the correct statement. The current leads the voltage by a phase difference of pi by 4. Again, this is a wrong statement. So the correct statement is, in case of simple resistor, current and voltage both are in same phase. Next question, the average power dissipated in an AC circuit is maximum if AC source is connected. So average power is dissipated only through a resistor. Okay, in an AC circuit, the power is dissipated only through a resistor. Inductor and capacitor does not dissipate any power. Average power dissipated in inductor and capacitor are always 0. So that means average power dissipated will be maximum when you are connected across only a resistor, nothing else. So that means when only a pure resistor is connected, the power dissipated is maximum. Next question from your question bank, different devices connected to an AC source are listed in the first column, and different phase relations of electric current with the voltage are listed in the second column. Choose the correct match. So it's a match the following type of question. So resistor, inductor, capacitor. Okay, lags behind the voltage by pi by 2, in phase with voltage, leads the voltage by pi by 2. So we know that in case of resistor they are in phase, so 1 should be matched with Q. Okay, in case of inductor it lags behind the voltage by pi by 2. So this is the for inductor, and capacitor leads the voltage by pi by 2. Okay, so now let's see the answers. 1 is with Q, 2 is with P, 3 with R. So this is the correct answer, option C. So here one thing you have noticed that in this case the matching of capacitor and leads the voltage by pi by 2 is direct match. Okay, generally you do not see it, but it is given in your question bank, so it possibly this kind of question you might expect. Generally we expect cross matching. Okay, so this should be here, this should be here, but somehow it was given in this question. Now let's see next question. The resonance phenomenon is exhibited by a circuit only if the following components are present. So for resonance, again the same formula. Resonance frequency is given by 1 upon 2 pi square root of L into C. So what are the components that we need? We need only L and C. R is optional, so L and C must be there. Okay, R is optional, so L and C both are required for resonance. Next, the relationship between peak value Im of current and RMS value is. So what is the relationship between peak value and RMS value? So IRMS is I peak divided by root 2. So correct answer is option B. Okay, remember IRMS and VRMS. So VRMS is also same formula. VRMS is equals to V peak divided by root 2. Sometime in some cases they will give you what is the peak value. So peak value is root 2 times VRMS. Generally in our society we use 220 volt power supply, right? 220 volt 50 hertz is the domestic power supply. The 220 volt that we use is basically the RMS voltage. Okay, the peak voltage is higher than that. Okay, that's why it is more dangerous. Okay, if there used to be a question in the past, why 220 volt AC is more dangerous than 220 volt DC. First of all, 220 volt AC means the magnitude or the maximum peak value is not 220 volt, but it is 220 root 2, which is equivalent to 311 volt. Okay, approximately 311 volt. So this is the reason why AC is more dangerous than DC. Same voltage, if the same voltage is given, AC is more dangerous because whenever we say AC we mention the RMS value, whereas the peak value is root 2 times more than the RMS value. Okay, so this is one thing that you should remember. Now next question. An ideal step-up transformer decreases. Step-up transformer means which increases the voltage. Okay, ideal step-up transformer, if you give say VI input, okay, and if you get VO as output, step-up means VO should be greater than VI. Okay, now the voltage increase does not happen automatically, so it has to sacrifice something. What it sacrifices current. So if IE is the input current, then the input current is more high than the output current. So in a step-up transformer, the quantity that decreases is current. Okay, the quantity that decreases is current, power remains constant. V into I is power. Okay, V into I is power. So if you increasing V, I has to decrease to keep the power constant. Okay, so when you are increasing the voltage, current decreases. When you are decreasing the voltage, current increases. So when you are transferring power from power station to our home, what happens is that the power when it is being transferred, it was increased to a very high value. So 2000 kilovolt, 2 kilovolt or 5 kilovolt, this kind of the voltage when it is being transferred from the power station to our homes, so that the value of current remains low. Okay, so lower current means lesser energy loss during transmission. We don't want to lose too much power when it is being transferred from the power generator station to our homes, right? So what they do, they initially when the power is transferred from the power station towards the city, for example, if power is being generated say somewhere and it is transferred to Bangalore, so between the station, power station and Bangalore city, the power cable are generally very high voltage. Okay, generally transferred by very high tension wire. If you have seen, okay, while traveling along a train, or if you are living in a rural area, you have seen that in the in between the crop fields, there are very huge towering structure carrying current, so that is basically high tension wire carrying very high voltage power, but that high voltage is useless when it reaches our home. So that's why every city has a power management system. So first it is reduced inside the city to a lesser value, 440 volts, generally 440 volts. 440 volt power is required in the industry, so that is directly sent over there, and from 440 volts to 220 volt is done by the local transformer which is located nearby your house. So they reduce 440 volts to 220 volt, and then it is transferred to your homes. Okay, so the journey of the current from the power station to your home is not very simple. It has involved lot of steps. Now next part, the input voltage to a pure inductor is V equals to Vm sin omega t. Then the current in the circuit is. So in case of pure inductor, we know that current lags by pi by 2. So if this is sin omega t, then the current will be omega t minus pi by 2. Okay, lags means minus, leads means plus. So current must be lagging by pi by 2. So correct answer is I equals to Im sin omega t minus pi by 2. The input voltage to a pure capacitor is V equals to Vm sin omega t. Then the current in the circuit is. So again, in case of pure capacitor, current leads by pi by 2. So leads means plus. So that means the answer will be Im sin omega t plus pi by 2. Okay. Question number 12. In a series LCR circuit, the L and the C are interchanged. The resonance frequency of the circuit will. So again, resonance frequency based question. So we know that resonance frequency is equals to what? 1 upon 2 pi square root of LC. Yes, correct. So F is equal to 1 upon 2 pi square root of LC. So that means if you interchange L and C, will the value change? Only the multiplication order will change. 3 2s are 6, 2 3s are 6. Okay, so does not matter if you interchange their positions as long as the formula is obviously valid. So that means L and C, as long as they are connected in the circuit, then the resonance frequency will remain same. So correct answer is remains same. Next question, the power factor of an AC circuit is 1. Then the phase angle between the voltage and the current is. So power factor of an AC is 1 means it is basically only a resistive circuit, or a circuit is in resonance. Okay, in resonance also the power factor is 1. In case of pure resistor also power factor is 1. That means what? The phase angle between the current and voltage is 0. Okay, cos 0. So, power factor is basically given by cos phi. Okay, power factor is given by cos phi, and it is given as 1. So that means phi must be equals to 0 degree. This is the phase difference. So phase difference is 0 degrees. Now next, which of the following is not a reason for energy loss in a transformer? Another question based on energy loss. Flux leakage is a energy loss. Eddy currents are also an energy loss. Heating effect also an energy loss. Electrochemical effect has nothing to do with a transformer. It can be there in case of an electrolytic cell, but for a transformer this is not there, so this is a wrong option. What type of material should be used as a core to reduce the hysteresis loss in a transformer? Hysteresis loss is basically if you use a permanent magnet inside the transformer core, the magnetic polarity keeps on flipping every time current changes, and it gets heated up. Okay, that is called hysteresis loss. To reduce it, you have to use a soft magnetic material. Example is soft iron. Okay, so any material with low hysteresis loss should be used. So that example is soft iron. Okay, material with high hysteresis loss, example is steel, but we generally use materials with low hysteresis loss, that is soft iron. Okay, so now let us move into the fill in the blanks questions. The principle of working of a transformer is dash. So the principle of working of a transformer is mutual inductance. So mutual inductance must be the correct matching over here. The power factor of an AC circuit containing pure resistor, power factor of a circuit containing only pure resistor is equals to 1. So if you see it, mark it and go on. Okay, 1 is also correct, maximum is also correct. Okay, maybe 1 is matching somewhere else, so that's why they have given maximum. Let's see. A rotating vector used to represent alternating quantities is called rotating vector used to represent an alternating quantities is called phasor. Okay, so a vector which represents the phase angle between voltage and current is used by a term called phasor. The average power dissipated in an AC circuit is dash if the AC source is connected to a pure capacitor. So the average power dissipated in an AC circuit is 0. It is 0. Okay, the current through an ideal inductor is called wattless current because it is it does not consume any power, so that's why it is called wattless current. Now in this case, maximum and 1 both can be the answer. Okay, 1 is not coming over here anywhere else, so that means 1 could also be the answer over here because the power factor of an AC containing pure resistor is 1 and that is also a maximum value. So 1 and maximum both are correct for this question. So options, obviously one of the options should be changed anyway, but if you see some cases there should be another question which can have another option. That's why we chose certain values as correct. But anyway, if you see such question, you can mark any one of them, you will get full marks. Now let's move on to numerical questions from this chapter. A series LCR circuit contains a pure inductor of inductance 5 Henry, a capacitor of capacitance 20 microfarad and resistor of resistance 40 ohm. If the AC source of 200 volt 50 Hz is present in the circuit, find the impedance, also find the resonance frequency of the circuit. Easy question. So first of all, what are all the given? Inductor 5 Henry, capacitance 20 microfarad and resistance 40 ohm. So we have to calculate the impedance and the resonance frequency. Resonance frequency is easy to calculate. Okay, simple formula. We have seen that formula. First we will calculate the impedance. So what is the formula for impedance? Formula for impedance is Z equals to R square plus XL minus XC whole square. This is the first formula that you should remember from this chapter. Now what is XL? XL is called inductive reactance. XL is called inductive reactance. What is its value? Its value is 2 pi F into L. As simple as that. So what is F here? Frequency of the source, which is given 50 Hz. So 2 into 3.14 into F is 50, L is 5. Okay, so it will be 100, 500. Okay, 50 into 200, 100 into 5, 500, 500 into 3.14, which will be 1500 something. Okay, 1575. Okay, if you take 3.15, then that will be 1575. Okay, this will be 1570. You are allowed to use calculator in your PU board exam, so you can use the simple calculator to calculate the exact value. So 1570 is approximated XL. What is the value of XC? XC value is given by 1 by 2 pi F into C. Okay, this is called capacitive reactance. It is called capacitive reactance, right? Now XC value you have to put, we have to calculate. So here 1 upon 2 pi, frequency is 100, frequency is 50 and I have a tendency of making this as 100 because always 50 into 2 turns out to be 100, right? So that's why I tend to write it first even before calculating. Now in the capacitance is given 20 microfarad. Microfarad means 10 to the power of minus 6. So what I will be doing, I will write this 10 to the power of 6 in the numerator. Why? Because 10 to the power of minus 6 in the division, it will go up anyway and become 10 to the power of 6 in the numerator, right? So this is just a step jump. So what we got, 10 to the power of 6 divided by 2 into 50, 100, 100 into 20 is 2000 into 3.14. Okay, so what is 10 to the power of 6 divided by 2000? So 1, 2, 3 zeros, so 3 zeros we can less, so we get 1000 divided by 6.28. Okay, so 2 into 3.14 is 6.28, and 3 zeros cancelled, so we had 10 to the power of 3. 10 to the power of 3 means 1000. So this will be 6 ones are 6, 6 ones are 6, 40, so 46, 6, approximately 166 ohm. You can calculate exact value so this is the value of XC. Okay, exact value you can calculate using a calculator. As I mentioned, I don't like to use calculator. So what is the value of Z now? So the value of Z will be now equals to square root of R square. R square is, what is the value of R? 40. So 40 square plus, here we have 1570 minus 166 whole square. Okay, so the square is on the whole square of this thing. Okay, now let's calculate. So this will be 40 square plus 1396, 1390, sorry, not 13, 1406, 1404, 1404 whole square. Okay, so 1404 whole square. Okay, so if you calculate, it should come around approximately 1500 ohm. Okay, because this is the most dominating part, this is the lower value part, so it should be close to 1500. Exact value we will see in a while, but before going into that, we have to calculate the resonance frequency. What is resonance frequency? So resonance frequency is given by F equals to 1 upon 2 pi square root of LC. So this will be again 1 into, so see, one problem from this chapter is at times it is difficult to solve the question on your hand. So whenever you are solving it, try to use the calculator at the last step. Don't use the calculator at the beginning, but after you have figured out, okay, in this case and this case, you have to use the calculator at the last stage. Okay, once you have get this value, then here also you have to use the calculator. So calculator use is mandatory to solve question from this chapter. So 2 into 3.14 into square root, and you are only allowed to use simple calculator, not the scientific calculator. So you have to take pi's value as 3.14. Okay, what is L? L is 5, this is 20, and 10 to the power of minus 6 microfarad, so 10 to the power of minus 6. So now what you will get, 520 is 100, 100 into 10 to the power of minus 6, so you get this as 1 by 6.28 into square root of 10 to the power of minus 3. So 10 to the power of minus 3 is something tricky, okay, because 10 to the power of 4 or minus 4 could have been easier because you could take the square root, okay, but here you cannot. So it will be 10 to the power of 3 by 2 divided by 6.28. The exact answer will be 16, approximately 16 Hz. Okay, this turns out to be not 1500 but 1412. This turns out to be 1412. Okay, so 1412 ohm is the correct value here. Using calculator you can get that. Again, using calculator you can also calculate this one. Okay, now let's move on to the next question. An AC source of frequency 50 Hz is connected in series with an inductor of 1 Henry, a capacitor of 90 microfarad and a resistor of 100 ohm. Does the current lead or lags the voltage? Calculate the phase difference between the current and the voltage. So first of all, what is the steps? What are the steps? So you have to calculate XL. And XC. So we will do it step by step. What is XL? 2 pi, frequency is given 50 Hz, and L is given here as 1 Henry. So XL is 100 pi or 314 ohm. Okay, so 314 ohm is the inductive reactance. Now what is capacitive reactance? Capacitive reactance is 1 by 2 pi F into C. So problems may be sometimes you might feel boring, but if you practice few of these cases, then all problems you can solve. You can solve all questions that might come into your exam. Okay, that's why problems are very, very specific. You have to solve few questions from this chapter so that you get confidence and what to do if you see any of the questions. Okay, in future I will also be solving previous year questions, so don't worry about it. So once previous year questions are done, then you will be super confident about what are all the questions that you might face. So 1 by 2 pi FC. So 1 by 2 pi into F is 50. C is 90 microfarad. So 90 micro means what I said, just 10 to the power of 6. Follow the steps. All steps should be same. 2 into 50 is 100. 100 into 90 is 9000 into 3.14. Okay. So XC becomes so again 1, 2, 3 zeros are gone, and you get 10 to the power of 6 divided by 9 into 3.14, which will be 27.28 approximately. Okay, 28 approximately, and for simplification let me assume this is equals to 30, almost equals to 30. Okay, I don't even want to use calculator, so that's why I am using it. So it will be 10 to the power of 6, 1, 2, 3 zeros cancelled, so we get 10 to the power of 3 divided by 30, or 1000 divided by 30. So 0 0 cancels and you get 33.33. So 33.33 is XC. Now here the first question is current leads or lags. So current leads or lags depends upon who is greater. So from here we can see that value of XL is way greater than XC. So XL is greater than XC. So if XL is greater than XC, then we say that this is the majority. So current lags. If you find XC is more, then current would be leading. So current leads or lags depends upon the value of XL, okay, and XC. Mutual value of XL and XC. If they are exactly equal, we get the resonance condition. If XL is greater than XC, then we get current lags. If we get XC is greater, then current is leading. Okay, so here as clear as day, current is lagging. Now what is the phase difference? The formula for phase difference is tan inverse XL minus XC divided by R. Okay, XL minus XC divided by R. So XL value is 314 minus 33.33 divided by 100, if you calculate, it will be turning out to be close to 70 degrees. Now you may not be able to calculate 70 degrees without using a sine cos table, but if you keep it like this, 2.79, tan inverse 2.79, then also you should get the full marks, because 70 degrees is not a common angle, so you should not be able to calculate it without using a calculator. Okay, so if you leave the answer over here, so it will be tan inverse 2.79, then also you should get full marks. Okay, but this is a common problem, so 70 degree maybe you can answer, but without using a sine cos table, this exact value may not be able, you may not be able to calculate, and I don't recommend using sine cos table for just a simple problem. So you just leave it over here and get the angle properly. Okay, so this is the correct answer. You should get full marks. Next, a sinusoidal voltage of RMS value 200 volt and frequency 50 Hz is applied to a series RC circuit in which R is equals to 3 ohm and C equals to 800 microfarad. Calculate impedance of the circuit, the current through the circuit, phase difference between the current and the voltage. So R is given, C is given, and they mention this is only an RC circuit. So no L over here. Easy question, right? 50 Hz is the frequency. So what we will be doing first stage is to calculate XC. Okay, so XC is 1 by 2 pi F into C. So that is equals to 1 by 2 pi into 50, and the value of C is 800 picofarad. Microfarad, sorry. So 800 micro means 10 to the power of minus 6, which turns out to be 10 to the power of 6 in the numerator. Okay, so 10 to the power of 6 divided by 100 pi into 800. Okay, so how many zeros are here? 1, 2, 3, 4. Okay, so 1, 2, 3, 4 zeros are cancelled. So what we got? We got 10 square divided by 8 pi. So that is 100 divided by 8 into 3.14. Okay, so which will be approximately 100 divided by 25. If you multiply these two numbers, 3 8s are 24 and point something, which is very close to 25. So we can take this as 4 ohm. Okay, so the approximate value of the XC is 4 ohm. Okay, now R value is given as 3 ohm. So impedance of the circuit, the normal formula of impedance is equals to square root of R square plus XL minus XC whole square. But is there any XL over here? No, right? So XL is not there. So XL not there means we can simply put it equals to 0. So 0 means what? Minus X's whole square. So minus X's whole square is what? Minus X's whole square is simply X's square. Okay, so when only X, R and C or R and L are there, you can still use the same formula. Only thing, whatever is missing, you put 0 in that place and you will get the impedance. Okay, one formula to rule them all. Okay, one ring to rule them all. Right, so one formula to apply everywhere. R is 3 ohm. Okay, and XC is 4 ohm. So we calculated over here 4. So it is 5 ohm. 3 square plus 4 square is common value, 5 ohm. So impedance is calculated, the current through the circuit. So what is the current? Voltage is given 200 volt, Z is 5 ohm. So current must be equals to the voltage divided by the impedance, which is 200 divided by 5. Okay, so that is 40 ampere. So 40 ampere is the current in the circuit. Phase difference between current and voltage. So phase difference value again XL minus X tan inverse XL minus XC divided by R. Now here again XL is not there and we will not take the negative sign. We will simply take XC by R. Okay, or tan inverse 4 by 3. Now 4 by 3 is again another specific value which turns out to be 53 degrees. Okay, it is a specific angle, so you can check that. 4 by 3 is 53 degrees, 3 by 4 is 37 degrees. Okay, so these are the standard value, sine 53, sine 37, cos 53, cos 37, tan 53, tan 37. These are the values. They are not, even though they are not coming into the standard table, but this is also a very common value. Those who are preparing for JEE or KCET, they should know these values. Again, if you are not sure, you can skip it and leave it over here. You should get full marks, right? Next question. A resistor of 50 ohm, a pure inductor of 250 millihenry and a capacitor are in series in a circuit containing an AC source of 220 volt 50 Hz. In the circuit, current leads the voltage by 60 degrees. Find the capacitance of the capacitor. So capacitance of the capacitor you have to calculate. So what are the method? We know that the phase difference is given by tan inverse XL minus XC divided by R, right? Or tan phi equals to XL minus XC by R. Now tan phi value is given here 60 degrees, so you will put that. So tan 60 degrees equals to XL minus XC divided by R. Now what is the value of tan 60? Tan 60 is root 3. So that is equals to root 3. So XL minus XC equals to 1.71 into R is given here as 50 ohm. Okay, so that is equals to approximately 85. Okay, approximately 85. So now we are leaving it over here. We will come back to the same part once we calculated XL. Then we can calculate XC. Okay, so what is the value of XL? XL is 2 pi F into L. Okay, inductive reactance. So 2 pi 50 into L is 250 millihenry. 250 millihenry means 250 into 10 to the power of minus 3. Milli means minus. So 50 into 2 is 100. So 100 pi into 250 into 10 to the power of minus 3. So what we got? 1, 2, 3 zeros, 10 to the power of minus 3. So 1, 2, 3 zeros and minus 10 to the power of minus 3 cancels. So we get 25 pi or 25 into 3.14, which will be 2.378, approximately 78. So this will be approximately 78. So now we will use 78 minus XC equals to 85. Okay, so XC equals to 78 minus 85, which is equals to minus 13. So here what mistake we have made is that here current leads the voltage they have mentioned, but we have taken current lags the voltage. So only one small correction we need to do over here is by calculating, instead of XL minus XC, we do not want this negative sign. Okay, that is the major thing. What we will be doing? We will be doing XC minus XL. Okay, so if XL minus XC is positive, then obviously current is lagging, but here current is leading. Current leading means it will be XC minus XL. Okay, so XC minus XL. So this is one small correction is required, not much, but we will do that. So we get XC minus 78. Also one mistake I made. So XC equals to 85 plus 78. Okay, so what mistake you have to be careful about? If current is leading, then it will be XC minus XL. If current is lagging, it should be XL minus XC. Okay, sign should be, you should be careful about the sign. Now let's see, add them 150, 163. So 163 is approximate value of XC. So XC value we have calculated. Now we have to do the back calculation to calculate the value of C. So XC equals to 1 by 2 pi F into C. Okay, so C equals to 1 by 2 pi F into XC. So just cross multiplication, so XC and C changes the places. So now put the values. So what we got, C equals to 1 by 2 into 3.14 into F is 50 Hz and the value of XC is 163. So if you calculate, you will get that value as 20, approximately 20 into 10 to the power of minus 6 farad or 20 microfarad. Again, you can use a calculator to calculate this value. Okay, I am not going into the calculation part. Now next, a sinusoidal voltage of peak value 220 volt is applied to a resistor, a series LCR circuit with a resistor of series resistance 5 ohm, a pure inductor of inductance 32 millihenry and a capacitor of capacitance 800 microfarad are connected. Find the resonant frequency, calculate the impedance and power dissipated at resonance. Okay, so first of all, find the resonant frequency. Resonance frequency formula, F equals to 1 by 2 pi square root of L into C. So this formula we are going to use, 1 by 2 pi square root of, what is the value of inductance? Inductance is 32 millihenry. And what is the value of capacitance? 800 microfarad. Okay, so let's see. Into 8. So 32 is 4 into 30. So 32 is equals to 4 into 8. And we are multiplying with 8. Okay, and if you take the square root of this, what we get? Square root of 4 is 2 and 8 into 8 is 8. So this will be 16. Okay, so we get this and this as 16. And what we are left with? We are left with 10 to the power of minus 3, minus 6 and 2 zeros. Okay, so 10 to the power of minus 9 plus 2 minus 7. So this is the what we are left with. Okay, so resonance frequency will be 1 upon 32 pi, 16 into 2 is 32, 10 to the power of minus 7, which will be 10 to the power of minus 3, 0.5 or 7 by 2. 7 by 2. Or it will be 10 to the power of 7 by 2 by 32 pi. So what is 10 to the power of 7 by 2, which is 10 to the power of 3 root 10. Okay, so whenever you see that 10 to the power of value x by 2, okay, and x is an odd number, so first of all you divide it, divide the number, and you suppose you get y.5. okay, which is the odd number, you will always get y.5. so take that y value, put it in the 10 to the power of value. So this is equals to 10 to the power of y root 10. Okay, where x by 2 is equals to y.5. Okay, understood? If you have any doubt regarding this methodology, please mention in the comment below, but don't go anywhere. We have one more chapter coming next, right? So 32 pi, and you can calculate the value of the frequency in this case, but the problem is not done. I will show you the frequency in a while. Okay, again, if you have a calculator, calculate it and let me know the answer in the comment section. calculate the impedance and power dissipated at resonance. So second part, how to solve it. Do we have to calculate XL, XC and all these things? Actually no, because they mentioned impedance and power at resonance. So what is the meaning of that? At resonance, what happens is that XL and XC are equal. So XL equals to XC at resonance. Right? So that means impedance is just equals to the resistance. At resonance, impedance is equals to resistance, that is equals to 5 ohm. So impedance is 5 ohm. What about the power dissipated? Power dissipated is given by V square upon R, that is 220 square divided by 5. So that is 220 into 220 divided by 5. So we get 4 5s are 20 and 4 5s are another 20. Okay, so you get this is equals to 22 into 22 into 2. So the answer you will get as 4840. 4840. Sorry, I take some help from my answers. Okay, and the resonance frequency will come out to be 10 Hertz. You can take the answer, you can check the answer, it will turn out to be 10 Hertz. Now let's move into electromagnetic waves, the second chapter. So how many questions we can expect from this chapter? This is the smallest chapter, as I mentioned. We are expecting 1 MCQs as well as 1 2-marker question. So how many questions we are going to discuss? 15 MCQs and only 5 2-markers, so almost there. So just hold on for 10-15 minutes, this should be over. But before I continue, I request you, first of all, please share this video with your friends. Secondly, please join our WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. There you will get all the updates, all the information regarding your PU2, your KCET and all the counseling infos in future as well. So the ultraviolet region of the electromagnetic wave spectrum lies between X-ray and visible region, microwave and radio wave region, gamma ray and X-ray region, visible region and microwave region. So if you see that ultra wave, so this is our, suppose this is our spectrum. So it start with first gamma ray, next is X-ray, then is UV ray, then we have visible ray. Visible means the lights that we see, the lights that you are seeing right now, because I am recording in visible region of the wavelength, that's why you are able to see me. If I am recording in UV rays or in the infrared rays, you would not be able to see me, right? So visible after UV is visible, then we have infrared ray, then we have microwaves, and then we have radio waves. Okay, in the radio wave first comes FM and then comes AM. Okay, so now let's see the portion. What is the question? The ultraviolet region. So ultraviolet region is falling between X-ray and visible ray. So it is falling between X-ray and visible region. The expression for displacement current ID is ID equals to epsilon naught d phi E by dt. Remember, it is because of electric field, and electric field is given by epsilon naught, not mu naught. So be careful. ID equals to epsilon naught d phi E by dt. When you are writing the Ampere circuital law, modified Maxwell and Ampere circuital law, that time this term comes over there, because in Ampere's law we have mu naught I. Right, B dot dl equals to mu naught I, so that's why that mu naught comes over here. But in general, the normal expression for displacement current does not have any mu naught. Very common mistake, and this question has repeated multiple times in history, so please be careful about this. Next question, the electromagnetic waves with lowest frequency among the following. So if you remember, we are starting with gamma ray, then X-ray, then UV ray. So whoever starting first has smallest wavelength and highest frequency. Okay, so here they have stated lowest frequency. Lowest frequency means radio waves. Lowest frequency is radio waves. Okay, this has highest frequency, this has lowest frequency. Everything is in between. Next question, the electromagnetic waves suitable for radar system used in aircraft navigation are. So in radar system we generally use microwaves. Microwaves is very common, which is used in the radar system. So microwaves is the correct answer. Next, X-rays, microwaves and gamma rays traveling in vacuum have same velocity but different wavelength, same wavelength but different velocity, same velocity and same frequency, same frequency and different frequency. I think this should be different wavelength. Okay, so first of all let us understand, X-ray, microwaves and gamma rays, they are all electromagnetic waves. All electromagnetic waves travel with the speed of light, which is equals to 3 into 10 to the power of 8 meter per second. It does not matter whether it is a visible ray, whether it is a gamma ray, whether it is a X-ray, all rays travel with the speed of light. Okay, but X-ray, gamma ray, microwaves, all other rays, they have different frequencies and different wavelength. Frequencies and wavelengths are different, but speed is same. So same velocity but different wavelength. Same velocity but different wavelength. Same velocity, different frequency could be also correct answer. Okay, but here same velocity, same frequency is given, so that is not a correct answer. Next, the frequency of X-rays, gamma rays and UV rays are A, B, C respectively. Then, so frequency of X-ray, gamma ray and UV ray. So if you remember the spectrum that I have drawn, first is gamma, next is X-ray, then we have UV ray, then we have visible, then we have infrared. Okay, by heart this spectrum. Okay, infrared, then we have microwave, and lastly we have radio waves. Okay, this has smaller wavelength, higher wavelength. Here we have highest frequency, here we have smallest frequency. Frequency symbol is given by this symbol. If you are not aware, this is called nu. Okay, this is the symbol for frequency. So the frequency of gamma ray, X-ray and UV ray. So gamma ray has highest frequency, right? So we can say that gamma and nu symbols are almost appearing same. So let me write gamma ray in capital gamma. So this is the symbol for capital gamma. Okay, so gamma ray have highest frequency. Okay, so X-ray, this is A is X-ray, A is X-ray, B is gamma ray and C is UV ray. Okay, so B must be greater than A and then both of them should be greater than C. So B must be greater than A and they should be greater than C. Okay, so remember this order. In terms of wavelength, gamma ray has smallest and UV radio waves have highest. In terms of frequency, gamma ray have highest frequency and radio wave has smallest frequency. Next question, the speed of light according to Maxwell's equation is given by C equals to 1 by square root of mu naught epsilon naught. So this is the expression for speed of light. The angle between electric field and magnetic field in an electromagnetic wave is 90 degrees. No other angle is possible. Okay, always electric field and magnetic field should always be normal to each other, that is perpendicular to each other. No other angle is possible for an electromagnetic wave. According to the generalized Ampere-Maxwell law, so that's what I was talking about. According to generalized Ampere's-Maxwell law, B dot dl equals to mu naught IC plus epsilon naught mu naught d phi E by dt. Okay, this question and the displacement current question came multiple times, so be careful, keep an eye on this type of question. Electromagnetic wave used in the treatment of cancer is you can mention X-ray, you can mention gamma ray also. So here X-ray is given, so you will tick at X-ray. Either X-ray or gamma ray, both are used in chemotherapy, if you have heard the term. That is basically treatment of cancer. Next, which of the following ray is absorbed by the ozone layer? So ozone layer absorb X-ray, gamma ray, UV ray, everything is absorbed. Not only UV ray, they also absorb X-ray and gamma ray. All of the above is absorbed by the ozone layer. That's why it is very, very essential. Now, out of all the three rays, UV ray is most in terms of most amount, which is coming from the sun. Gamma ray and X-ray are less. Okay. Gamma ray and X-ray are less, but UV ray is one of the highest amount that is absorbed by the ozone layer. But X-ray and gamma ray, all high frequency lights are getting absorbed in our ozone layer. If there was no ozone layer, there would not be any life that could be possible on Earth. Okay, so ozone layer is the main protector, main shield that is protecting us from all the harmful rays. Which of the following ray is produced by hot objects? So hot objects produce infrared rays. Hot object produce infrared rays. So our body also emit infrared rays. So even if there is complete pitch dark, if you are wearing a infrared goggle, you will still be able to see me or anything, any object which is radiating heat. Our body is radiating heat, right? We are eating, we are digesting the food. Because of that, our body is radiating heat, producing heat, and that heat is being radiated by our body. So that's how the intelligence people, they monitor the terrorist activity, etc., the some unknown activity across the border. Okay, the armies and intelligence bureau, they monitor our border and any untoward incidents areas, they survey the area using infrared goggles. Okay. Which waves are used for mobile communication? So mobile communication use not X-ray, not UV ray, not microwave, but radio waves. Mobile communication happens mainly using radio waves. Which will produce electromagnetic wave? Accelerated charge, moving magnets, a static charge and a static magnet, a static charge. Only accelerated charge can produce electromagnetic waves. There is an alternative way, as charge in a circular motion. Charge in a uniform circular motion. This can also produce electromagnetic wave, because a charge in a circular motion basically means accelerated charge. So accelerated charge will always produce electromagnetic waves. A circular motion means centripetal acceleration is always present, right? Circular motion. So if the electron is orbiting in a circle, it should always emit electromagnetic waves. The experimental demonstration of electromagnetic waves was done by Maxwell, Hertz, Marconi or Bell. It was done by Hertz. Okay, Hertz first showed the existence of electromagnetic wave, how perpendicular electric and magnetic field can produce electromagnetic wave, and in honor of his name, the frequency unit of SI unit of frequency was named Hertz. Okay, so if you see 50 Hertz, we are solving alternating current problems. So that Hertz and this Hertz are same. Okay. Next, write any two uses of ultraviolet radiations. UV radiations can be focused to very narrow beams for high precision applications such as LASIK. LASIK is the operation of your eye, okay, where your refractive powers can be corrected. UV lamps are used to kill germs in water purifiers. or also in milk. Okay, so it is also used to sterilize milk. If you are using a UV at your home, we say RO UV. Okay, UV RO. What is the meaning of UV RO? RO means reverse osmosis, which basically takes away all the hard materials that is present inside the hard metals which are present inside the water, so that water can be potable, that is drinkable. And secondly, they are passed through UV lamps so that all the germs are killed. Okay, bacteria and microbes that present inside the water, they are died, then only that water is suitable for drinking. And same goes with milk. So milk is being sterilized by UV lamps. Similarly, the equipments used by a surgeon, okay, during a surgery, okay, all the instruments used by a surgeon during surgery are again sterilized by UV rays. So first, before the operation is conducted, the doctor uses UV sterilizer to sterilize all the instruments he is going to use or she is going to use during the operation. Next, name the electromagnetic waves used for the following applications: the radar system navigation used in aircraft navigation, the remote switches of household electronic system such as TV. So microwave is used for radar system, and infrared rays are used in your TV remote. So if you see your TV remote, normally you will not see anything. There is still a LED light fixed in top of your remote control, but when you press it, you do not see anything because it's an infrared. Next time, what you can do, when you are at home and you are using a mobile phone, switch on the camera of your mobile phone and switch on the video and turn on the your remote and you should see using the mobile camera. Then you will see that light is blinking because your mobile phone can detect infrared but our eyes cannot. Okay, very, very interesting. What is displacement current? Give expression for it. Displacement current is due to the changing electric field, is called current due to changing electric field is called displacement current, and its expression is given by ID equals to epsilon naught d phi E by dt. What are electromagnetic waves? How are they produced? Oscillating electric field in space which produces an oscillating magnetic field, which in turn is source of oscillating electric field, as so on. So this is how these are called electromagnetic wave. Electromagnetic waves are produced by accelerating charges or oscillating charges. Okay, this gives rise to electromagnetic waves. So what is the meaning of it? So when electric field is oscillating, okay, this electric field, changing electric field will produce a changing magnetic field. Okay, and this changing magnetic field will again produce a changing electric field. So electric and magnetic field, they carry on each other, and they start propagating. Okay, so that is why a changing electric field and changing magnetic field combined together can produce electromagnetic waves. Last question. Mention any two uses of infrared rays. Electromagnetic devices such as LEDs uses infrared are widely used in the remote switches of household electronic system such as TV sets. Infrared lamps are used in physical therapy. So physical therapy is where suppose you have a broken bone or dislocated bone and the doctor ordered you to go to a physical therapy, then the doctors uses infrared lamps to heat up the area. Is a very good heater, and that's how physical therapy is done, and infrared lamps are used over there. Infrared rays are also used in infrared goggles to detect human present or animal present when there is no light available. Marks distribution from this chapter: 1 mark question will be 2 from this chapter, so probably one of them will be MCQ, one of them will be fill in the blanks. But if you look into the model question paper trend, then we see that one question, both of the questions are MCQs, so probably both questions will be MCQ from this chapter. We don't know yet as they have not given proper breakup of the blueprint, so I assume that either there will be 2 MCQs or 1 MCQ, 1 fill in the blanks. there is no 2 marks question from this chapter. There will be one 3 mark question and one 5 mark question. Now because there is a 3 mark question coming from this chapter and from the trends that I have seen in your blueprint model papers, that the long answer type question will most likely to be a numerical from this chapter and not a theoretical question. But anyway, I will discuss a few important 5 marker theoretical in case that comes in your board exam. So worry not, everything will be prepared in this lecture from this chapter. So if you watch this video, then 10 marks will be assured for you. So you will be guaranteed to get 10 marks just from one video. So what all are going to discuss? 15 MCQs as we always discuss, and fill in the blanks will be 5. Then we'll also discuss 5 3 marker questions. We will also discuss 5 mark 2 question, which will be a descriptive question, and 3 very important numerical from this chapter. So without delay, let me start with the MCQs of this chapter. So a real and finite object is placed between the pole and principal focus of a concave mirror. So the image formed is, so let us understand the question. So here we have a concave mirror and we placed an object between pole and the focus, so it is less, that the object distance is less than focal length. So in that case we will observe a virtual enlarged image. So enlarged and virtual image is observed. So the image formed is virtual and enlarged, virtual and magnified. So whatever language they use, you should remember virtual and enlarged, virtual and magnified, same thing. Okay, so the correct answer is option C for this question. Next question, identify the statement which is true for a compound microscope from the following. So compound microscope, here we have 4 statements and we have to identify the true statement. That means 3 of them are false, only 1 is true. Its objective is a convex lens of greater aperture. Now we are talking about microscope, not telescope. This is true for telescope. For microscope, the objective is generally of smaller aperture. Let's see. Its eyepiece is a convex lens of smaller aperture. The image formed by its objective is real and inverted. This is the correct statement. Okay, so the image formed by a microscope, the objective image formed by the objective is real and inverted. That's why it is falling between the 2 lenses. Okay, its eyepiece produces final image which is virtual and diminished. It's produce the final image is virtual, but it is obviously not diminished, it is enlarged. That's why whenever we put something under the microscope, it appears big, because it is a magnified image, right? So eyepiece obviously produce a virtual image, but it is not a diminished image, it is a magnified image. But the correct statement over here, the image formed by its objective is real and inverted. Now let's move on to the next question. A ray of light is incident on a glass air interface at an angle greater than the critical angle for the pair of media. Then the ray undergoes total internal reflection. Okay, so whenever the angle is more than critical angle, then it will undergo always total internal reflection. With our discussion, the objective lens of a refracting telescope is a dash and magnifying power of the telescope for normal adjustment is dash. Okay, so let's see. The objective lens of a refracting telescope is a convex lens. Okay, it's a convex lens of and we are talking about telescope. So telescope's objective has a large aperture so that it can collect a lot of light. Telescope is generally used to observe very distant object. Okay, so that means we are observing something which is we generally say heavenly object. For example, stars, moon, sun, etc. They are all called heavenly objects because they are all located in the sky, right? So we need a large aperture so that a lot of light can come through the objective lens. And so it is a convex lens of large aperture and its magnification M is given by FO by FE. Okay, FO objective divided by FE is the magnifying power. So convex lens of large aperture and magnification is FO by FE. Correct answer option C. Okay, remember that because objective has large aperture, that's why focal length of objective is first and eyepiece is playing secondary role. That's why eyepiece is in the division. Okay, that is one way to remember it. Even if that is not true, you can remember it. Eyepiece is bigger in aperture, objective is bigger in aperture and eyepiece is smaller in aperture. So bigger by smaller is the magnification. That's how you can remember. Now next, a ray of light coming from an object which is incident parallel to the principal axis of a convex lens placed in air after refraction. Okay, so ray of light coming from an object which is incident parallel to the principal axis of a convex lens placed in air after refraction. Okay, it will converge at the point of principal focus. Okay, so appears to they passes through the second principal focus because they have given second principal focus. Generally, when parallel ray of light falls on a convex lens, they focus at principal focus. This is called secondary principal focus. This side it is called primary principal focus. Okay, primary focus means where light is, if the light passes from this point, then it become parallel. Okay, and secondary means parallel ray of light when incident, they get converged at this point. That's why convex lenses are called converging lenses. Okay, so it is passes through the second principal focus. Parallel light always, no matter whatever is the object, if the light is parallel, it will always pass through the principal focus. Now next, modern telescopes called reflecting telescopes use a concave mirror rather than a lens for the objective. So Cassegrain telescope is one of the telescopes which is a reflecting telescope. Now here we use concave mirror. Why we use concave mirror? Because there are mainly two reasons. No chromatic aberration in mirror. That means what? All lights, all colored light, they all reflects by same amount. Okay, so law of reflection, there is nothing to do with refractive index. So all lights reflect by same amount, all colors, and they merge at same point. So you don't need to worry about different color band. Okay, generally if you are observing something which is very far away using a convex lens, okay, then you will not get a clear image, you will get a blurred image. You have to use some software handling, using some software, you have to correct that image to get the accurate image, right? But in case of concave mirrors, that problem is not there, because mirrors generally do not have something called chromatic aberration. Chromatic aberration means different color of light have different refractive indices. Okay, that's why when light passes through, you have seen that in case of a simple prism, when white light passes through a simple prism, the light gets separated into 7 different colors, Vibgyor, right? So this is called because of this property, dispersion of white light. Okay, when we observe something which is very far using a lens, all the colors present in that spectrum or in that light, they get separated. Okay, and we get different colors for that object. Okay, now there are techniques to correct that. There are techniques to actually get the proper image. As I mentioned, software image handlers can do that. Okay, image processing is possible, but still if it is already, if you don't want to do any software in between, right? If it is already possible to get a clear image. So one of the reason is that concave mirror is used, because there is no chromatic aberration in a spherical mirror. Giving mechanical support to a mirror is easier. Now what is a mirror? Mirror is basically a curved surface where back side is silvered or front side is silvered, but you can provide support to the entire back side. Okay, the light does not go through this mirror to the other side. So that's why light, whatever is happening, that is happening only on the one side. Okay, light is falling on the mirror and they are getting focused at single point. If you put a sensor over here, you will get the image. That is the process. Now light is you don't need to pass the light to the other side, so you can support the entire back side to create a very large aperture mirror. But if you want to create a very large aperture lens, what happens is that lenses are completely different. Okay, lenses are completely different because in this case light is falling over here and they need to go to the other side. So you cannot block this side. So only way you can support the lens is through the rim. Okay, that's why whenever you see a spyglass, I hope most of you have a spyglass to look to become like a Sherlock Holmes, like, right? When we were kids, we used to play Sherlock Holmes games. Okay, we had a hidden object games, basically where you have a spyglass and you have to observe and find what is something wrong in that place, right? So that is one of the games we used to play, and the spyglass only had a circular rim. Okay, that is called rim. Okay, so that rim can support a lens up to a certain size. If it is going beyond that size, that rim is not sufficient to hold it and it will break apart. Okay, so you cannot create a very large lens telescope. In fact, the lens telescopes that we have, one of the largest is Hubble Space Telescope, which is located in space. Okay, that is not very huge. Okay, Hubble Space telescope is not very huge, but it has done wonders for mankind. It has taken numerous good pictures. Still on Earth we can still make a very large telescopes which is made up of mirrors and free of chromatic aberration, and also they can be supported by a large back side. So that's why nowadays whatever telescopes that we are making on Earth, and we are making it using mirrors. Okay, space telescopes are very rare nowadays. So it is both are true. So both 1 and 2 are true statement. Okay, so through this question we have learned a lot about difference between spherical telescopes and refracting telescopes. Now let's move on. Snell's law is invalid for angle of incidence I equals to 60 degrees, 30 degrees, 0 degrees, 90 degrees. Now Snell's law cannot be applied when angle of incidence is 0 degrees, because in case of 0 degree angle of incidence, light passes straight away, so there is no sin I. Sin I and sin R both are 0, so you cannot apply Snell's law. So Snell's law is not applicable for I equals to 0 degree. Next, a light wave of frequency nu and wavelength lambda enters to water from air. Okay, nu will remain constant, lambda changes, nu changes and lambda will remain constant. Both nu and lambda will change, both nu and lambda will remain constant. Now nu is called frequency of any electromagnetic wave, is a fundamental property and it does not change. No matter where you go, the frequency of light does not change. Only thing that changes, it is wavelength. Okay, wavelength changes but nu does not change. Okay, as long as it is on, if you are observing from Earth, the nu is fixed. So wavelength can change. Okay, wavelength can change but frequency does not change, and that's why we will mark option A as correct. Nu will remain constant, lambda will change. In refraction, light waves are bent on passing from one medium to second medium, because in the second medium the frequency is different, the speed is different, the coefficient of elasticity is different, the amplitude is smaller. So there are basically two main reasons you can answer this question. When light is entering from one medium to another, its direction changes. Basically you can explain this using the change in its wavelength and the change in its frequency. Change in its wavelength and change in its speed. So the speed is different, that's why it is changing its direction. Okay, in fact the definition of refractive index is given by refractive index, absolute refractive index, speed of light in vacuum divided by speed of light in medium. That is how we define refractive index. Okay, and refractive index is basically the reason why it is bending, right? So you can say that because speed is different in different mediums, so when light enters from one medium to another, its direction changes. Next, the relation between focal length and the radius of curvature of a mirror is F equals to 2R, F is equal to R by 2, F is equal to 2 by R, F is equal to R. So we know that focal length is half of the radius of curvature for a spherical mirror. So F is equal to R by 2 is the correct answer. The angle of minimum deviation of a prism depends on refractive index of the material of the prism, refractive index of the surrounding medium, refracting angle of the prism, that is angle of the prism basically. Okay, so we know that refractive index of a medium with respect to another is given by sine A plus delta by 2 divided by sine A by 2, right? So definitely delta depends on the refracting angle. It depends on the refracting index of both the medium as well as the surrounding. Okay, so in the formula that we derived in our lecture that we are going to derive here also, where we assume that surrounding is air, but if the surrounding is not air, then you have to divide that using the refractive index of the medium to get the correct value. Okay, so it will be N1 by N2. N2 is the surrounding medium. Okay, then only you will get this equation. Okay, so it depends on refractive index of the medium, material refractive index of the medium and angle of the prism. So both 1, 2 and 3 is correct. So option D is correct in this case. Total internal reflection is possible when light is traveling from air to water, water to air, air to glass, all of the above. So total internal reflection is possible only when light is traveling from denser medium to rarer medium. Okay, other way around it is not possible. So air is a rarer medium. Okay, so air to water and air to glass both are where you are seeing that a light is traveling from rarer to denser medium. So that means these two cases total internal reflection is not possible. Total internal reflection is only possible when light is traveling from water to air, because water is highly dense compared to air. So that's why optical density, obviously density means here optical density. So optical density of water is more compared to air. That's why we observe total internal reflection for water to air. Image of a real object formed by a simple microscope when the object is placed at a distance less than 1 focal length is. So image of a real object formed by a simple microscope. What is a simple microscope? Simple microscope is a simple convex lens, spyglass. Your spyglass is considered to be a simple microscope. Okay, so it consists of only one convex lens. Okay, so if the lens distance is less than 1 focal length, then you observe a virtual, erect and magnified image. So virtual, erect and magnified image. So option B is correct, right? We know that if the distance is less than the focal length, we observe a virtual, erect and virtual image. Sorry, it happens over here. Okay, virtual, erect and magnified image. Next question. The lens nearest to the object in a microscope is called objective lens. Obviously the name suggests nearest to the object is objective lens, nearest to the eye is eyepiece, right? One problem with the reflecting telescope is that the objective mirror focuses light inside the lens, outside the telescope tube, inside the telescope tube, all of the above. So reflecting telescope means it is basically based on mirror. So lens is not correct, and if this is not correct, then all of the above is also not correct. So either outside the telescope tube or inside the telescope tube. Now if it is if the ray of light, when parallel ray of light falling on a mirror, okay, they all get reflected over here. Okay, and telescope tube is like this. So the problem is not that the light is getting converged at outside the tube. If it is happening outside the tube, we could have placed a screen over there and we would be simply relieved. But that is not the case. What happens? All the rays that is falling on a reflecting telescope, they all converge inside the tube. That is one of the problem. So the light always focused inside the tube But we have overcome this. For example, Cassegrainian telescope, what we have done, instead of having a single mirror, the mirror is cut at the center, and when the ray of light is falling over here we have a convex mirror, okay, second mirror. So the light ray is now transferred like this, and you have a screen over here and you observe it from there. Okay, so this is a way of observing in case of Cassegrainian telescope, one of the oldest reflecting telescope that is being used till today. Okay, so this is one of the way to avoid that. So the light rays always converge at the inside the tube, normal general reflecting telescope. Next, fill in the blanks. A microscope is used to produce large dash of small objects. So microscope is used to produce large image of small objects. Optical fibers are based on the principle of dash. Optical fibers are based on the principle of total internal reflection. Okay. Reciprocal of focal length is called power. Reciprocal of focal length is called power. 1 by f is power. Dash mirrors are used as rear view mirrors in cars. So what type of mirrors are used in rear view mirrors? We have studied in class 10th. Convex mirrors. Convex mirrors are used as rear view mirrors. Okay. Next, the image formed by a simple microscope is virtual or real. Okay, both can be on answer for this question. The image formed by a simple microscope, when you are using it as a simple microscope, it will always be virtual, erect and magnified. Virtual, erect and magnified. So image formed by a simple microscope is always virtual. Now, question number 21. Give the Cartesian sign convention used to measure distance and heights in spherical mirrors. So first of all, you have to draw this diagram. This diagram is compulsory. This diagram is given in your textbook anywhere, or you can download from this lecture as well. Okay, so first you have to show a mirror. Okay, and then you have to show the x-axis. Okay, also show the y-axis over here as well. Okay, y-axis. Now you have to mention all. This diagram is compulsory. Everything that is shown over here is compulsory. All distances along positive x-axis is positive. All distances along negative x-axis is negative. Similarly, all distances along positive y-axis is positive, and negative y-axis is negative. Okay, so that means all distances you are measuring. And also you have to mention that the mirror is located at origin. The mirror is located at the origin. Is located at the origin. Okay, so this is origin, and all distances along positive x-axis is positive, all distances along the negative x-axis is negative, all distances in the positive y-axis is positive, all distances in the negative y-axis is negative. That is the basic Cartesian sign convention, and for writing this you will get 3 marks, not 1 mark, not 2 mark, but you will get 3 marks. But the diagram is compulsory. So if you want to answer such question, this question is given in your model question paper and it has come in the past in your previous year papers as well. So prepare the diagram. Diagram is very simple and technically correctness is not required because you are not drawing a ray diagram. Simple representative diagram with object, images, etc. Okay, so heights downward negative, height upward positive. Okay, the incident against the incident light is negative, distances along the incident light is positive. That is also one way to say, but I like to say any distances along the x-axis is positive, any distance in the opposite direction is negative. Okay, and distance along the positive y-axis is positive, distances along the negative y-axis is negative. This is basically Cartesian sign convention. Okay, Cartesian is the person who actually developed the coordinate geometry. Okay, Cartesian coordinate system. Okay, x, y, z, that was actually done by Cartesian, and that principle is used in physics, and that's why it is called Cartesian sign convention. Okay, nothing else. Now, draw the ray diagram for formation of an image by a compound microscope. Write the expression for linear magnification produced by the objective of compound microscope in terms of tube length. So, the diagram is this one, and tube length is the magnification of objective lens is given by L by FO. Now, this is a technical diagram. So, if this question comes in your exam, my opinion is skip this question because this can be a technical question, and if you make small mistake in the diagram, the marks will be deducted. So if you are completely practicing this diagram 2-3 times, and you can draw this diagram without observing that the original image, and if you mention what is U, FO, FE, okay, and everything is mentioned properly, then only practice this diagram. Otherwise, my recommendation is this diagram you should not practice. Okay, now next, show that the focal length of spherical mirror is equal to half of the radius of curvature. Now here we have taken a concave mirror. You can take a convex mirror as well. Concave mirror, in my opinion, is easier to analyze. So first of all, there is a ray of light which is falling on the mirror, and after reflection, it is passing through the focus. Parallel ray, parallel to the axis, always passes through the focus. Okay, now here we have joined center of curvature and the point of incidence. So that means this line is actually a tangent. This represents a tangent at this point. So that means this is the angle of incidence. This should be the angle of refraction. Okay, this should be the angle of incidence, and this should be angle of refraction. Now reflection, sorry. So we know that in law of reflection, angle of incidence is equal to angle of reflection. So I should be equals to R. So that both of them are assumed to be theta over here. Okay, now if you consider this as a parallel line, and this is also a parallel line, this is a bisector. Okay, then so basically this is a line, this is a line, and this is a bisector. Then this angle should be equals to this angle. Okay, alternate angles. So this total angle theta plus theta equals to 2 theta. That should be equals to this total angle, which is also 2 theta, right? So first we assume that obviously angle of incidence equals to angle of reflection, and both of them are theta, and by assuming that, we calculated this angle to be 2 theta. Okay, now for that we will use the triangle. Two triangles we will use. One triangle we will use this one, CMD triangle, CMD. Okay, CMD. So this angle is theta. This angle should also be theta because this is the radius of curvature. Okay, this is the radius of curvature. Okay, so this distance should be equals to this distance. This distance should be equals to this distance, and this is a isosceles triangle. So that is why this angle theta means this angle should also be theta. Okay, this angle theta, or you can use another alternate angle principle. Alternate angle means this is a line, this is a line. Okay, this is a bisector. That means this angle should be equals to this angle, alternate angle. Okay, so from there also you can say these two angles are equal. So this angle is also theta. Now first, obviously we are using the triangle CMD. Okay, CMD, the triangle, and what is the value of tan theta? From the triangle CMD, what is the value of tan theta? So tan theta is given by perpendicular by base. Perpendicular is MD, base is CD. So MD by CD. Okay, next we will be using triangle MFD, triangle MFD, and from here we say tan 2 theta, that is this angle tan 2 theta is perpendicular by base. Perpendicular is MD, base is FD, equals to MD by FD. Now we will use two approximations. First approximation is that this is a paraxial ray. The rays are paraxial. Paraxial. What is the meaning of paraxial? Paraxial means this point is very close to the point P. The point M is very close to the point P, that is the ray is very close to the principal axis. Those rays are called paraxial rays. Okay, every formula, every equation that we use is only applicable for paraxial rays, and because it's a paraxial ray, we can say that theta is very small. Theta and 2 theta are very small. Okay, and for small angles we know that sin theta is equals to theta, cos theta equals to 1, and tan theta is also equals to theta. So tan theta nearly theta and tan 2 theta nearly 2 theta. This is the first approximation. Second approximation, what we will be doing is that we will assume that this D point is very close to P. That means CD is actually equals to CP. D is very close to P. Therefore, CD equals to CP equals to R, and FD equals to FP equals to F. Okay, so CD equals to R and FP equals to F. So now we will go back to these equations again. So what we got? Theta equals to MD by R, and 2 theta equals to MD by F. Okay, so now we will divide these two equations. Okay, this equation is 1, this equation is 2, so we will divide them, and we get theta by 2 theta equals to MD by R into F by MD. Okay, this is division. The division means it will be reversed. So MD cancels, and we get theta cancels, and we get R equals to 2F. This is the required relation. R is equal to 2F or F is equal to R by 2. This is the required relationship between radius of curvature and focal length. The diagram is compulsory. The lines that I have written is compulsory to get full marks. Now next, write two conditions for total internal reflection of light and mention its one technological application. So conditions are: light must travel from denser to rarer medium. Number 2, the angle of incidence must be greater than the critical angle between the medium. Application: optical fibers are cables used to transfer data using total internal reflection. So optical fibers are based on the principle of total internal reflection. Okay, so that is a technological application. Okay, now next, name the two types of telescope based on the objective used. Also mention any one factor on which the magnifying power of the telescope depends. This question is taken from one of your sample papers. Okay, sample papers, board released 2 sample papers which is available along with the question bank. You can check that out. So two types of telescopes based on objective used are: refracting telescopes uses convex lens as objective, and reflecting telescopes uses concave mirror as objective. Okay, one factor on which the magnifying power of a telescope depends: focal length of the objective. So focal length of the objective, maybe its lens, maybe its mirror. So the factor on which the magnification depends is obviously the focal length of the objective. Other possible correct factors are focal length of eyepiece, length of the telescope as well. Okay, So these are the three factors on which the focal length, magnification of a telescope depends. Now, derive the expression for refractive index of a material of prism in terms of angle of minimum deviation and angle of the prism. Now this is the only one derivation given in your model paper. Okay, there is one more very important derivation that also we are going to do. So first, this derivation, this came two times in the past. So first of all, what you have to do is this. In this case, if you see this derivation, these two diagrams are compulsory to draw. Okay, these two diagrams you have to draw, there is no other option. Okay, so this is the prism and this is the minimum deviation graph. Okay, so prism diagram is compulsory, where you have to mark I, E, R1, R2, delta and angle of the prism A. These are the compulsory things that you have to draw. In case of minimum deviation, these values are not important, but the pattern of the graph should be important, and this is the angle of deviation, this is angle of incidence. This is also very important. Okay, so you have to mention that from geometry means you are applying geometry, normal geometry. In this prism, you will get delta equals to I plus E minus A. This is the minimum write-up that you have to do. Delta equals to I plus E minus A. So from this geometry, it can be shown that this value of delta, this is a triangle. Okay, geometry can be proven. I am not doing it in this class. So delta equals to I plus E minus A. And the angle of prism can be represented as R1 plus R2. So these two things you have to remember. So delta equals to I plus E minus A, I plus E minus A, and A equals to this R1 plus R2. Now, by observing the I versus delta graph, okay, or delta versus I graph, it should be delta versus I graph, I will correct it. Delta versus I graph, we can see that the angle of minimum angle of minimum deviation occurs when the angle of incidence I is equal to emergent angle E. Okay, that is I is equals to E. So the minimum deviation occurs when, so this is the minimum point. Okay, the graph is given, so this should be the minimum point. So when the minimum point is given, if you see that for any other point, there are two cross sections. Okay, one, if this is I, then this should be E. If this is I, this should be E. So I and E are always appearing as pairs, except for this point. At this point, what is happening is that you are getting only one value of I and one value of E as well. So I and E are merging. Okay, so at this point what happens is that I is equals to E, and if I is equals to E, if I and E are equal, then corresponding inner angle should also be equal. So R1 is equals to R as well. Okay, and say that is equals to R. Okay, that is equals to R. Now delta M equals to 2I minus A. From this equation, minimum delta I plus I minus A, that is 2I minus A. So you get I equals to A plus delta M by 2. Also A equals to 2R. So R equals to A by 2. Okay, so from this equation we know that from Snell's equation, the refractive index of the material of the prism with respect to the surrounding is given by sin I by sin R. So that is sin, instead of I we will just write this value, instead of R we will just write this value, and this is the final expression. Okay, clear? So basically we are using Snell's law, and while using some geometrical proof is there. It's slightly tricky, but you can, if you are someone who is who cannot do derivation mathematically but has a good memorizing power, you can memorize this derivation. In case this derivation comes, you can write it. Next derivation is mathematical, but simple mathematical, and most asked question from this chapter in terms of derivation. Deduce the lens maker's formula. This one you cannot skip, you have to practice. Okay, here we have two diagrams. One object is placed over here. So say this is the first surface of refraction. So this is has a radius of curvature R1. This one has a radius of curvature R2. Okay, as you can see, R1 is positive, R2 is negative. What we are trying to find? We are trying to find the focal length. Okay, that is our objective. What else? When the ray of light is falling on this surface, suppose the image is formed somewhere, okay, inside the second medium, and that distance is given by V1. And when this V1 acts as an object for the final object, and you get the final image. So what relation we will use? We will use the relations for reflection through a spherical surface. So reflection through spherical surface, surface N1. Okay, for surface N1 and N2, there are two surfaces, N1 and N2. For N1, we can write N2 by V1. Now, refractive index of this medium is N1, refractive index of this medium is N2. Okay, so N2 by N1 V1 minus N1 by U equals to N2 minus N1 by R. Okay, so this is a very easy relation to remember. Where is V1 is forming? V1 is forming assuming that there is completely glass material, nothing else is there. Okay, complete glass material is there. So light ray is traveling from U, it is falling over here, and this is V1. Okay, the refractive index of this entire medium is 2, refractive index of entire medium is 1, this is U. Okay, so what is the normal lens formula? Normal lens formula is 1 upon V minus 1 upon U is equal to 1 upon F. That formula is very, very handy to remember in this particular situation. So we will use the same thing, but along with the refractive indexes. So N2 by V, because N2 is inside, V1 is inside N2, so it is N2 by V1 equals to N1 by U. So U is inside U1, so that's why N1 by U, and N2 minus N1 by R1. N2 minus N1 by R1. R1 is the radii of curvature of this particular surface. Now this is not the only surface. There is one more surface which is again stopping the light from going into the completely into N2, and it is again coming back to N1 again. So this is also N1, right? This medium is also N1. So now again we will use the same relation. This is equation number 1. And what relation we will use? N1 by V. Now again the same relation. V is the final image. Okay, for this final image, the intermediate distance is V1. So you will use minus N2 by V1 equals to, now light is traveling from N2 to N1. So it will be N1 minus N2 by R2. Okay, sign, we do not use any sign of object distance, image distance, or R1, R2. That is not required over here. That sign should come automatically. Okay, now N1 minus N2, if you take the negative sign common, you will get minus N2 minus N1 by R2. No need to use any extra sign over here. Okay, now this is equation number 2. And what we are doing, we just need to add them. Okay, add them. So when you are adding it, so you see that N2 V1 cancels, and we get N1 V minus N1 U equals to N2 minus N1 is common, and we get 1 upon R1 minus 1 upon R2. Okay. Now what? So now take this 1 upon V minus 1 upon U equals to N2 minus N1 whole divided by N1. So we have taken this N1 common and divided it, 1 upon R1 minus 1 upon R2. So do not put 1 by F right now, okay, even though this is lens equation, but we assume the lens equation is still not known. What we know is that if U is infinity, that is the ray of light is coming from very, very far away. If U is infinity, then V is equals to F. So final image is formed at F. So parallel ray of light when falls on a lens, okay, the image is always formed at the focus, right? So that is what we know. We will use that. So 1 by F minus 1 by infinity equals to N2 by N1 minus 1 upon R1 minus 1 upon R2. Okay, so 1 upon infinity is 0. So from there we can write 1 by F, so this is the final step, equals to N12, okay, refractive index of 2 with respect to 1, or let me write it N21. Refractive index of 2 with respect to 1 minus 1 upon R1 minus 1 upon R2. Generally the first medium is air, so in that case we get to use absolute refractive index. So this is the simple derivation. If you remember the steps, you can simplify it and answer it, but the diagram is compulsory. Diagram in your textbook is slightly incomplete. You have to add R1 and R2 in this diagram, also V1, and add the refractive indexes of the all mediums. Okay, this is also N1, right? Now let's move on to some numerical questions. Okay, an object of height 1 millimeter is kept perpendicular to the axis of a thin convex lens of power plus 10 diopter. The distance between the object and the lens is 15 centimeter. Find the position and height of the image formed. This is the question from your 2025 final paper. Okay, here the power of the lens is given as 10 diopter. So power is given by 1 upon F, but here F is expressed in meters. Remember that. Okay, F is expressed in meters, then power is given by 1 upon F. So from here we can say that focus in meters is given by 1 by P, which is equals to 1 by 10, that is 0.1 meters. So focus now in centimeter will be 0.1 into 100, right? Centimeter, meter to centimeter is multiplied by 100. This is one place where we like to use centimeter and not meter. In electrostatics we always use meters, but this is the chapter where centimeter is more preferred over meters. Okay, so focal length is 10 centimeter. Now the distance between the object and the lens is 15 centimeter. That means U is minus 15. Okay, U for any numerical question, U is always negative. Any numerical question, U is always negative. Now from lens equation we know that 1 upon V minus 1 upon U equals to 1 upon F. This is common for all types of lenses, lens equation. Okay, or 1 upon V equals to 1 upon F plus 1 upon U, or UF U plus F. Okay, or V equals to UF by U plus F. So this formula you can use directly, or if you forget you can do it. This will save some time for you. So V equals to U is 15 minus 15, F is 10. For a convex lens, focal length is positive. Convex lens and convex mirror, focal length is positive. Okay, U is minus 15 plus 10. Okay, so minus 150 divided by minus 5. Minus 15 plus 10 is minus 5. Minus minus cancels and you get 30. So V is 30 centimeter. So V we have calculated 30 centimeter. Now we have to calculate the height of the final image. So height of the object was given 1 millimeter. So height of the object is given by, height of the image is given by magnification times height of the object. Height of the object 1 millimeter already given in this case. So what is the magnification? So magnification by a convex lens is given by V upon U. Okay, what is V? V was 30 centimeter and U was minus 15. So it is minus 2. Okay, so the magnification is minus 2. Minus represents the final image will be inverted. Minus represents final image will be inverted, not upright. Okay, so the height of the image is equals to m into h naught, that is minus 2 into 1 millimeter, that is minus 2 millimeter. Here negative represents the image will be inverted. Okay, so 30 centimeter 2 millimeter, magnitude is 2 millimeter. If you want, you can keep minus. If you don't want, you can avoid the minus, but if you keep it, then it will make a good impression on the teacher. And if you write this line here, the negative sign represents image is inverted, that will make a good impression on the teacher. Now next question, double convex lenses are to be manufactured from a glass of refractive index 1.55 with both faces of the same radius of curvature. Find the radius of curvature required if the focal length is to be 20 centimeter. Also find the new focal length of the lens if it is immersed in a water of refractive index 1.33. So this question is from your model paper 1. So here refractive index is given as 1.55, surrounding medium is air. Okay, the focal length is given by 20 centimeter, and because it's a biconvex lens, R1 is equals to minus R2 equals to RC. Okay, so biconvex lens means this is a biconvex lens, so this is R1. Okay, R1 is positive and this is R2. So R2 will be negative. Now also not only that, both, because biconvex, both sides are equally convex, so R1 magnitude wise R1 and R2 should be same. So we can say that R1 equals to minus R2 equals to R. So R1 equals to R, R2 equals to minus R. So our background work is done. Now we will take the lens maker's equation, 1 upon F equals to n minus 1, 1 upon R1 minus 1 upon R2, or 1 upon 20 equals to 1.55 minus 1, 1 upon R minus R, okay, or 1 upon 20 equals to 0.55 into 2 by R. Okay, minus minus plus, 1 upon R plus 1 upon R, that will be 2 by R. So we get R equals to 20 into 1.1. 0.55 into 2 is 1.1. R goes here, 20 goes over here. So we get 22 centimeter. So 22 centimeter is the radius of curvature for each surfaces. Now when you immerse it into water, okay, only thing that changes, the focal length is changed. Okay, but why it is changed? Because this n is no longer n. Okay, you have to use the general formula, that is n divided by n of water. Okay, you have to use the general formula, which is n divided by n of water, n divided by n of water. Okay, n divided by n of water minus 1. Okay, and obviously 1 by R1 minus 1 by R2, the remaining part will remain same, that is 2 by R should be there as well. So 2 by R we are directly writing that this part will remain same. Okay, R value we already know, 21. Now we have to calculate the 1 by F1 value. So 1 by F dash equals to 1.55 minus divided by 1.33 minus 1, okay, into 2 by 22, or 1.55 minus 1.33 divided by 1.33 into 1 upon 11. So 1 by F. okay, or 1 by f equals to 0.22 divided by 1.33 into 1 by 11, or f dash equals to 1.33 into 11 by 0.22. So if you cancel it, you will get 133 into 11 by 22. So the decimals we have removed, and we get 11 is 11 to the 22. So it will be 133 divided by 2, that is 66.5 centimeter. So correct answer is 66.5 centimeter. Now next question. So now the last question, find the effective focal length and effective power of combination of convex lens of focal length 25 centimeter in contact with the concave lens of focal length 20 centimeter. Is the system a converging or a diverging lens? Ignore the thickness of the lenses. So we know that the focal length, equivalent focal length of two lenses is given by 1 by f equivalent equals to 1 by f1 plus 1 by f2. This is same as parallel combination. So we can write f equivalent equals to f1 f2 by f1 plus f2. This is the formula for two lenses in contact. Okay, here it mentioned that one is a convex lens of focal length 25 centimeter. So assume that f1 is a convex lens. F1 is a convex lens, that means its focal length is 25 centimeter. First one is convex lens. Okay, second one is a concave lens. Both are lens, obviously, then only this formula will be applicable. So F2 will be minus 20 centimeter. Okay, so for concave everything is negative, for convex everything is positive, no matter lens or mirrors. Okay, so now we will use these values in the equation. So see, if you observe me over here, I have not used any sign over here. I will directly use the sign in the formula. Okay, so equivalent focal length will be 25 into minus 20 divided by 25 minus 20. Okay, so it will be minus 25 into 20 divided by 5. 25 minus 20 is 5. So 5 5s are 25. 5 20 is 100. So minus 100 centimeter. So minus 100 centimeter is the equivalent focal length. And what is the sign? Sign is negative. Sign is negative means it's a concave mirror, concave lens. So final lens is a diverging lens. Why it's a diverging lens? Because final lens is a concave lens. So concave lens, because of the negative sign, it's a concave lens, and because it's negative, that means it will be a diverging lens. Concave lenses are called diverging lenses and convex lenses are called converging lenses. So correct answer is, in this case, 100 centimeter diverging lens. Okay, negative sign represents diverging and the magnitude is 100. So as you can see from this chapter, we are expecting two questions. And two questions are mostly two one marker question. That means one should be MCQ and another one should be your fill in the blanks. Also we are going to, there are no 2 marker and 3 marker questions that might come in your board exam. So no 2 marker and 3 marker in your FA2. If any 2 marker or 3 marker is going to come, those questions we will cover in the long answer type. Okay, don't worry, we will cover that. So in long answer type there is one question that is guaranteed to come from this chapter. So if you are struggling with the earlier chapters where the concept is difficult, then this chapter should help you to get 7 marks. So if you watch this video, 7 marks will be guaranteed for you. Now what are all the questions that we are going to discuss? So as usual, we are going to discuss 15 very important MCQs, also 5 fill in the blanks from this chapter, and in long answer type we are going to discuss 3 very important long answer type question. as well as two important numerical questions, because if you go through your blueprints, you will see that out of the 3 blueprints, 1 blueprint has a numerical question from this chapter and not a theoretical question. So if you see any numerical question coming from this chapter, that is going to be also very, very important. Now let us start with the MCQs. First, a beam of unpolarized light of intensity I0 is passed through a pair of polaroids with their pass axis inclined at an angle of theta. The intensity of emergent light is equal to. So this is a question based on Malus law. So what is the first polaroid? There are so you have to understand that there are 2 polaroids. First is say P1 and second one say P2. Okay, and their pass axis has an angle between them. So if you take the pass axis, the angle between the pass axis is theta. The light which is falling on this is I0. So I0 is the intensity of the light which is falling on the first polaroid. So what will happen when an unpolarized light is allowed to fall on a polaroid? The intensity of the light which is coming out will directly be I0 by 2. It is always, whenever an unpolarized light is falling on a polaroid, the light after it getting polarized, the intensity becomes half, so it will be I0 by 2, and this is a polarized light. This one is a polarized light. Now when it is falling on the next polaroid, now it is a polarized light, so we can use Malus law, which states that the output intensity, say I, will be given by the incident light, which is I0 by 2 over here, times cos square theta. What is theta? Theta is the angle between the pass axis, so cos square theta, but here you have to take I0 by 2 as your reference point and not I0. Okay, so correct answer will be I0 by 2 cos square theta. So option D is correct for this question. Very interesting, very important question. Now let's move on to the next question. To observe sustained interference pattern on a screen placed at a suitable distance in Young's double slit experiment, which of the following condition or S in plural E/R are necessary? Sources of light should be coherent. That is compulsory, that sources should be coherent for observing Young's double slit experiment. Sources of light should be narrow. Yes, if they are narrow, you are getting a very well observed interference, so this is also very, very mandatory. Sources of light should be very close. If they are not close, interference pattern will not be visible, so this is also compulsory. So all 3 A, B and C are compulsory to observe sustained Young's double slit. Very important, sustained Young double slit pattern. So if they are not close, you might see interference, but the screen size etc. will be very large, so that is not possible, and you will not get a sustained interference. It will be almost average intensity, so this is not possible. So only when they are close you will get a very clear sharp interference pattern. So now let's move on. So here the answer will be all A, B and C. Diffraction effect is exhibited by only sound wave, only light wave, only matter waves, all types of waves. So diffraction is a property of all types of waves. It is observed in case of sound, it is observed in case of even matter wave. Okay, so electron wave that we will discuss in another chapter, dual nature of radiation and matter. So diffraction is basically observed by all types of wave. So option D, all types of wave, is the correct answer for this question. If unpolarized light of intensity I0 is passed through a single polaroid, the intensity of emergent light. So here we have only one polaroid. So you already know that when unpolarized light of intensity I0 passes through a polaroid, the intensity drops by 2. So it will be I0 by 2. Correct answer is again option D, I0 by 2. So put that in your head always. Okay, this is a very important concept for PU as well as KCET. Now next question, the phenomena of bending of light at the corners of an obstacle is called diffraction. Bending of light on the obstruction on an obstacle is called diffraction. So when a sharp edge is presented to a narrow beam of light, it bends near the edge. Okay, so ideally according to the rectilinear propagation of light, if light is propagating like this, we should get a light here if you put a screen over here and complete darkness over here. But in reality you will see that some spot is bright, and that is happening because of the diffraction of light. Light does not travel in a curved path, but it is getting bent and at a sharp edge. It is only happens when the sharp edge is there, and this phenomena is called diffraction. This is the definition of diffraction. So this is diffraction. Now next, according to Huygens principle, the speed of secondary wavelet is twice the size of wave, 0, same as the wave, infinite. So according to Huygens principle, the speed of the secondary wavelet is same as the wave. It is the it is a PYQ. It came in 2024, your PU board exam. Now next, when a point source of light is placed at the principal focus of a thin convex lens, the shape of the emergent wavefront is. So when a point source of light, so here we have a lens and a point source of light is placed at the principal focus. So this is a point source, convex lens. So light after passing through the convex lens, it becomes parallel, okay, because it's a focus. So at focus if you keep anything, then it will become parallel to the principal axis. So initially the wave pattern was like this. This was the initial incident wavefront, and after it passes through the lens, it becomes parallel. So that means the wavefront will also be plane wave and it will be parallel to each other. So it will be plane wave front. Correct answer is plane wave front. Okay. So in case you see any such questions, try to draw the ray diagram, basic ray diagram, and then try to analyze what is happening, and based on that information try to find out what wavefront it is. Now next, the shape of the wavefront for light coming from a distant star is. So the shape of the wavefront from a light traveling from a distant star, again from a distant star we can assume that the ray of lights are parallel to each other. Okay, that is what we say, that if light object is located at infinity, the light rays becomes parallel. For a distant star you can assume that the rays are parallel to each other, and based on that fact you can actually say that it's again a plane wave front. Okay, this is a plane wave front. Next, the principle of superposition of waves applies whenever one source of light falls on a screen, one source of light moves across a screen, two or more sources of light illuminate the same point, two or more sources of light illuminate two different points. So principle of superposition means when two waves, obviously two or more waves, when they fall at the same point, what happens at this point, their intensities actually gets added up. That is called principle of superposition based on their phase. It's not a simple addition. Okay, we will see that in through one derivation, but mathematically they get added up. We say vectorially they get added up. So basically when two or more sources of light illuminate the same point, the point has to be same. It cannot be two different points, and we need more than one source. Okay, so two and or more sources of light illuminate the same point. Now let's move on. We will have constructive interference if the path difference is delta x equals to n lambda, delta x equals to n plus 1 lambda by 2, delta x equals to n plus half lambda, delta x equals to n minus half lambda. So we will get constructive interference when path difference is the multiple of n lambda. So n equals to 0, plus minus 1, plus minus 2, plus minus 3. So this is the condition for this constructive interference. So definitely delta x should be n lambda. Now next, to observe diffraction, the size of the obstacle should be of the wavelength. If it should be either lambda or 2 lambda or 3 lambda, slightly more than lambda is preferred. Okay, so it should be of the order of the wavelength. Okay, to observe diffraction, in fact observe interference as well, the slit width. Slit width, that we say slit width or the size of the obstacle should be of the order of wavelength. If it is too large, the light will not be able to pass. If it is too small, light will easily pass and you will not observe any diffraction. So to observe diffraction, the size of the obstacle should be of the order of the wavelength. Remember this term, of the order of the wavelength, right? Now next question. Two lights each of intensity I0 are used in Young's double slit experiment. The intensity of the interference maxima. If the intensity of the light, both of them are same, the intensity of the light gets multiplied, so it becomes 4I0. The intensity becomes 4I0. For dark pattern it becomes 0. Okay, for dark pattern it becomes 0. Okay, for constructive interference the intensity is becomes 4 times. For destructive interference it becomes 0. Okay, now next, when a compact disc CD is illuminated by small source of light, colored bands are observed. This is due to diffraction. This is due to diffraction. When you illuminate a CD, if you have seen a CD, it was very popular when I was the student like you, but nowadays CDs are almost obsolete. You do not see a lot of CDs. Okay, when we were smaller than you, younger than you, we used to have cassettes. Then cassettes were replaced by CDs when I went to a college. Now then came pen drives. Now it is almost everything is stored in clouds, so we do not no longer use CDs or pen drives, or pen drives are still used a little bit, but CDs and cassettes are obsolete long back. CDs are very rarely used. Okay, so it is diffraction because on surface of a CD there are some grooves, okay, small grooves, and on that grooves light gets diffracted, and that's why we see color. Okay, nowadays you might see a CD in front of a bicycle. Okay, they mount it for the colorful effect that produced by that CD. Okay, if you have seen a CD, please mention that in the comment below. Yes, I have. Yes, I have seen a CD. Please mention that in the comment below. This is a nostalgic moment for me because this was one of the most popular way to collect songs, to watch movies, etc. Right? Now let's move on. While both light and sound show wave character, diffraction is much harder to observe in light. This is because, okay, so one example of diffraction in sound, let me tell you one example. Suppose you are standing behind a wall. Okay, you are standing, there is a wall, you are standing behind, and one of your friend is on the other side of the wall. Okay, so ideally if light, if you are talking in the sense of light, you will not able to talk anything and that will reach to your friend. Okay, but if you talk in sound wave, then definitely the sound wave will reach to your friend who is standing on the other side of the wall. Right? Now why does that happen? This is because sound wave can travel through the barrier. So this is suppose this is the wall, this is where you are standing, and this is where your friend is standing. Okay, now if you talk something, the sound wave will easily travel because it can bend, and the main reason is that the wavelength of sound is much higher. Okay, wavelength of sound is much higher in the order of meter, centimeter or meter. That's why sound wave can easily bend even if the obstacle is little bigger. Okay, but to observe diffraction, in case this is an example of sound waves diffracting. Okay, so if you are wondering, this is an example of sound wave getting diffracted, and you can communicate even if you are not looking at the person. Okay, now for light wave that is not possible because the frequency and the wavelength of light is very small. Okay, wavelength of light is very small, so you need a very sharp and very small object which can actually diffract the light. Okay, one example you can try is razor blades. This is very popular. One experiment is mentioned in your textbook, so you can try that out. Okay, so because light, the wavelength of light is far smaller, it is very difficult to observe diffraction in case of light. Now last MCQ, which of the statements are correct with reference to single slit diffraction pattern? Fringes are of unequal width. So which of the following statements are correct? Okay, actually is correct, it should be is correct. Okay, one of them should be correct. Fringes are of unequal width, fringes are of equal width, light energy is not conserved, intensities of all bright fringes are equal. So if you see the pattern of diffraction of light, you will see that there is a clear spike, very high spike, which is called central maximum, and then the intensity of light gradually decreases and it becomes zero very quick. So these are all secondary maximums. So intensity of light is different for different maximums. Also fringes are of unequal width. The central maximum is most bright and most wide, whereas secondary maximums are not that bright and not that wide as well. So fringes are of unequal width is the only correct statement over here. Okay, so fringe width is this one. So as you can see, the fringe of the bright fringe is maximum, and central bright fringe is maximum. Secondary fringes decreases very quickly. Okay, if you study physics in future, then you will know how to derive these equations, how to use that equation. That will be there in your upcoming journey if some of you chooses to study physics. Now before I continue, I just like to tell you that if you want to get well score in your PUC exam as well as in your KCET exam, then definitely you have to subscribe to our channel. The link, obviously the subscription button is there, and also you have to join our WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. Now let me continue with the fill in the blanks from this chapter. A wavefront is a surface of constant, let's see the options, transverse, wave, particle, maximum, phase, diffraction. So only one object which is making a sense, one word which is making a sense. A wavefront is a surface of constant phase. Okay, constant phase. So correct answer will be phase. The light waves, so phase is done. So whenever you are answering, fill in the blanks, try to mark them, and if possible also mark which question you are answering for. So this is already done. This is for 16. This is a way to remember the correct choice. The light waves are dash in nature. Let's see again. Light waves are transverse in nature. Light waves are transverse in nature. Okay. The phenomena of bending of light around the edges of obstacle is called diffraction. It is called diffraction. So these two are also done. Okay. Transverse and diffraction, these two are done. If two waves are coming from two coherent sources superposed in phase, then the intensity of the light at that point is maximum. So when two waves interfere with same phase, the interference becomes the intensity becomes maximum. So it becomes maximum. Phenomena of polarization proves that dash nature of the light waves. Okay, so the phenomena of polarization proves that wave nature of light waves. It proves wave nature of light waves. Okay, in more correct, EM wave. Okay, electromagnetic wave nature of light waves, that should be more accurate. Okay, because only electromagnetic waves can undergo polarization. Okay, sound wave, which is a mechanical wave, cannot undergo polarization. So more accurate should be EM waves. Okay, so more accurate for this option will be EM wave. Okay, so electromagnetic wave nature of light is proved by polarization. Diffraction and interference can occur all types of waves. Okay, all types of waves can undergo interference and diffraction, but only electromagnetic waves can undergo polarization. So that's why it proves the electromagnetic wave nature of light. Now let's move on to the 5-marker question. So first question, two coherent sources of a constant phase difference undergo interference. Obtain the expression for resultant displacement. This is question number 1. Mention the two uses of Polaroids. Give the condition for constructive and destructive interference of light in terms of path difference. Now these two questions can come as a 2-marker question in your FA2. So prepare these two questions as well. Don't ignore that. But this is a a 3 marker question, and any one of them will come as a substitute as a add-on question with them. Okay, so this is a 3 marker. Any one of them will be coming as a 2 marker question, but I have added both questions so that you also get help for your FA2 exam. Okay, so now let's see. 2 coherent waves of constant phase difference undergo interference. So let's see 2 waves. What are the 2 waves? Say Y1 equals to A1 sine omega t. This is a standard equation of light wave. And another wave, say Y2 equals to A2 sine omega t plus phi. Okay, so this is the, what is phi? Phi is phase difference, and it is constant, obviously. Okay, now they undergo interference. So if they undergo interference, what happens that you have to add their respective displacements. Okay, so net displacement y should be equals to y1 plus y2. This is the net displacement. Okay, net displacement is y1 plus y2. This is the superposition principle. Okay, or we can say this is a1 sine omega t, and this is a2 sine omega t plus phi. Okay, their amplitudes are different in this given case. Now what you have to do, you have to add these two. Now how you can add these two equations? So for that, what we will be doing, we will, for time being, we will keep the first term as it is, and we will break apart the second term using sine A plus B formula. Okay, so it will be sine omega t cos phi plus cos omega t sin phi, right? This is the formula for sine A plus B. Now what we will be doing, we will try to take common of sine omega t term and whatever else is left with cos omega t term. Okay, so we will try to take the things which are common. So A1 plus A2 cos phi. Now I am jumping one step. I hope you can understand why I have done that. Okay, so A2 cos phi, multiply, when you multiply A2 with each of the terms, okay, so A2 sin omega t cos phi, A2 cos omega t sin phi. Okay, so what we have done, we have taken sin omega t common and we got A1 plus A2 cos phi. Okay, plus A2 sin phi cos omega t. Okay, so this is the two terms that we have received. Now if you substitute this term as r cos alpha and this term as r sin alpha, okay, this is a very common substitution that you do in your integration or differentiation substitution method problems, right? So here what we can write is that obviously r will be common and we will get cos alpha sin omega t plus sin alpha cos omega t. So definitely again we can apply sin A plus B formula and we can write r sin omega t plus alpha. This is the equation of resultant wave, but don't get overboarded. You have to show the value of r as well as alpha. You have to show the value of r as well as alpha. Now what is r over here? So if you take r cos alpha, r sin alpha, if you take the squares of both and add them, you can find the value of r, which will be coming out to be r equals to square root of a1 square plus a2 square plus 2a1 a2 cos phi. Simple, right? So if you add square of these two, if you take the whole square plus whole square of this, that is what we have done, r square sin square alpha plus r square cos square alpha equals to what we got, a1 plus a2 cos phi whole square plus a2 sin phi whole square. you don't need to show this, okay, this is just for your understanding. Now r square can be common, so sine square alpha plus cos square alpha, what is that? Sine square theta plus cos square theta, obviously that becomes 1, so definitely that is 1. So on your left hand side, right hand side, what you got? a1 square plus 2a1 a2 cos theta cos phi plus a2 cos square a2 square cos square phi plus a2 square sin square phi. So if you add them, you will get a2 square is common, cos square phi sin square phi becomes 1, so you get a1 square plus a2 square plus 2a1 a2 cos phi. This is same as vector addition. This is same as vector addition, right? So this one you can remember, or you can do it on the exam hall, but doing this will not give you any extra marks. But if you remember, this is same as your vector addition, that should be sufficient, okay? You do not need to show this derivation, okay, but if you forget it how to do it, you can remember that, right? So r value is calculated. Now next is alpha. So what is alpha? Sin alpha by cos alpha, that is tan alpha. So r sin alpha divided by r cos alpha, r gets cancelled, you get sin alpha by cos alpha, that is equals to tan alpha, and that is equals to a2 sin phi divided by a1 plus a2 cos phi, same as vector addition. So these two terms are same as vector addition. So if you write this, you will get all 3 marks, okay? First of all, you have to write the equations of the given waves, and then using superposition principle, you have to write using superposition principle y equals to y1 plus y2, and then you have to simplify this, okay? Right, now let's move on to the next part. Mention 2 uses of Polaroids. Polaroids are used in sunglasses, car windshields to reduce the glare from reflected light, that is from roads, water surfaces, etc. Now in camera and photographic filters are also Polaroids are used to reduce the unwanted reflection and improve contrast, okay? So it is used in a camera and photographic filters. If you are someone who is photographic enthusiast, you might have seen that the photographic enthusiasts use a Polaroid filter in front of the camera, okay, especially when they take a light in the bright condition, okay, that prevents that safeguards the sensor of the camera, okay? So that is why Polaroids are used as filters. It is also used in 3D movies. You can mention that 3D movie glasses are also made up of Polaroids, okay? That is also one of the modern uses. Now condition for constructive and destructive interference. Now based on that, objective questions, numerical questions, both can come. So these formulas are also important. So path difference is given by a delta x equals to n lambda, which is given by n equals to 0, 1, 2, 3, and in terms of path difference, the dark fringes are given by delta x equals to 2n plus 1 lambda by 2, where n is same value. And if you are interested in phase difference, so phase difference is given by 2 pi by lambda into delta x. This is the condition for, this is the path difference. Now if you add respective constructive condition and destructive condition, you will get the respective condition for phase difference as well. This is the phase difference general formula for both cases. You just need to put respective delta x's over here and calculate the actual condition, right? Now let's move on. State Huygens principle. Using Huygens principle, arrive at the law of reflection for a plane wave. This also has come in the past. Let's see. Huygens principle, every point on a wavefront acts as a source of secondary wavelets which spread out in all directions with the same speed as the wave. The new position of the wavefront is the forward envelope, that is the tangent of the surface of this secondary wavelets. Now you can I can explain this later in a separate video, but this is the statement that you have to memorize anyway. Do not make any changes or any mistakes in the statement. Huygens principle and one theory question is very expected from this chapter. If the other question does not come, which is given in your model paper, by the way, this question and obviously the model paper question, which is Snell's law, both are important. So we will do the both derivation, okay? So first we will start with the reflection. So reflection, what is the main thing? We need to have a mirror, okay? In case of reflection, we need to have a mirror, and we assume that two brothers, one and 2, they started from some point at the same time, okay, and they reached their destination. So when the brother 1 reached over here, the brother 2 reached somewhere here. So this will be our incident wave front, and by the time the light ray gets reflected and reaches somewhere here, the second light reached over here. So this will be our reflected wavefront. This is called reflected wavefront. Okay, so here we will mark all the incident and reflected wavefronts. Okay, the diagram you have to draw it using scale so that you don't make any mistake, and also put arrows so that it is the light rays that you have to indicate, and these lines are the wavefronts. Okay, so A and B are the incident wavefront. AB incident wavefront, and say this is CD. This is CD is reflected wavefront. Right, so this is how the things goes. Now what you have to show that the angle of incidence is equals to angle of reflection. Okay, so if you draw a normal over here, this will be angle of incidence I, this will be angle of reflection R. Now from geometry it can be shown that if this is angle of incidence, then this angle that it makes with the plane of reflection is also I, and this angle is also R. Okay, so this can be shown. Let me use a different color. So this angle is I and this angle is R. Okay, so this can be shown. We do not need to show that, you just need to mention it that the angle made by AB with the reflecting plane is I, the angle made by the reflected wavefront with the reflecting plane is R. Now you have to show that I is equals to R. For that, what you have to do that, you have to assume that speed of light in the medium is V. Speed of light is V. Okay, one single medium is there, so speed of light is simple only V. Now, so what we said, by the time light reaches from A to D, okay, from A to D, same time light reaches from B to C. So A to D must be equals to B to C, and that should be equals to VT. Okay, because both ray of light take same time. So two brothers started at the same time, but in the path there are some path difference created, and one reaches first and B is yet to reach. B is light 2 is stuck at B. Okay, so this is the incident wavefront, and by the time the light B reaches to C, it already reflected back to point D. So D is our so that's why we said CD is our reflected wavefront. Okay, and so that means the distances should be same because both are equals to VT. Right, now what we will be doing, we have to show that these two triangles are congruent. Okay, ABC and ADC, these two triangles we have to show congruent. Okay, now the order of the sides is important in case of congruent triangles. Okay, so we will use ACB and ACD. So from triangle ACB and triangle ACD, these two are the triangles. What we know that AC is common, BC is equals to CD. Okay, so BC equals to AD. Okay, so BC equals to not AD, sorry, here also it will be wrong, it is CD. Okay, BC equals to CD, right? So CD, this will be also CD. Okay, so BC is equals to CD and AC is common. AC is common. What else? So AC is common because both triangles have this side AC. What else? If you see that this is a wave front, right? So this makes an angle 90 degrees. This will also make an angle 90 degrees, right? So angle ABC, so wavefront, remember that wavefront, if there is a wavefront, okay, that is intersecting a ray of light, okay, wavefront will always make angle 90 degree with the ray of light, no matter whatever is the shape of the wavefront, okay, ray of light, even if it is a spherical, it will always make an angle 90 degree with the ray of light. It is a property of wavefront, okay, that property we are using over here. Okay, so this angle will also be 90 degrees. So ABC equals to angle ADC. So side angle side, okay, side angle or side angle side. From that we can say that triangle ACB must be congruent to triangle ACD. Okay, these two triangles are congruent. So what we can say is that therefore angle BAC must be equals to angle DCA. Okay, DCA. Okay, so this is the derivation that we wanted to do. So we can say that I equals to R. This is the reflection of light. So this is hence proved. Hence proved. So this is the derivation of reflection of light. Now next derivation is same, state Huygens principle. Using Huygens principle, arrive at the Snell's law. Snell's law is law of refraction. It is slightly complicated than the reflection one. So here we have a medium which is separating the two media. So this is one medium, this is two medium. Again, two brothers started at the same point, say X and Y. Okay, they started at the same point. During their travel time they got separated, and by the time X reaches the point A, Y reaches say point say B. Okay, so what is the incident wavefront? Incident wavefront will be this one. Obviously this angle is 90 degrees. Okay, and by the time, now here one important thing, light does not stay in the same medium, light travels to the second medium, right? So by the time B reaches to this point, okay, the light A already reached the second medium and it bends and it reached say at a point B, say C. Okay, B is already taken, so let's say at point C, and this point is say D. So what is the reflected wavefront? Reflected wavefront is same. What is wavefront? By the way, wavefront is the points of same phase. Points of same phase. That means when they started, initially they are at same phase. They had same phase. Now whenever they have started traveling, one is traveling light slightly before the other, and the phase path difference is there, but path difference is there means these two has to have the same phase. Okay, these 2 points has to have the same phase. No matter which medium they travel, phase relation should continue between them. Now, so this is the points of same phase. Now we can say that this angle is angle of incident and this angle is angle of refraction. Okay, this is 90 degrees angle. Okay, this is a 90 degree angle. Now speed of light in this medium say v1, speed of light in this medium say v2. The time taken by light to reach from B to D is t, time to reach from A to C is again t. Okay, so what we can say is that the distance BD and AC are not same, but the time taken by both of them are same. So what is BD? BD will be V1 into T, right? BD is V1 into T. S is equal to VT. S equals to VT. Similarly, AC will be V2 into T. So BD and AC are both calculated. Now we will use the law of triangles to calculate the angle. Okay, we know that in Snell's law the formula starts with sin theta and sin I and sin R. So we will directly calculate sin I. What is sin I over here? So this is a right angle triangle. This triangle is a right angle triangle, right? Now we will apply that and try to calculate what is this sin I. Sin I is perpendicular by hypotenuse. Now if this is the right angle, so this must be the hypotenuse, so AD must be the hypotenuse. And what is the perpendicular? Perpendicular is the side which is opposite to that of the angle, so hypotenuse in this case will be BD. So sin I is BD divided by AD. BD divided by AD. So what is BD? BD is V1T divided by AD. Similarly sin R is AC divided by AD. You can check that out. So here this is the angle R. So opposite side is AC. So AC divided by hypotenuse is AD. So AC divided by AD. So that will be V2T by AD. Now what we will be doing, Snell's law states that we have to show the relationship between sin I by sin R. So we will simply divide them. We will simply divide them and we'll see that AD will come in division. So they will cancel. So we get V1T divided by V2T. Again TT cancels. So we get V1 by V2. Now we will cleverly write this as C by V2 divided by C by V1. What is C? C is speed of light in vacuum. C is speed of light in free space. Okay? Or vacuum. Whatever you are comfortable with, you can write that. You can even write it in air, but here we do not know which medium is air, so that's why we have written it like this. So what is C by V? C by V is the refractive index for that particular medium. This is called absolute refractive index, right? N2 by N1. So N1 is the refractive index of the incident medium and N2 is the refractive index of the reflected medium. Now do the cross multiplication, you will get N1 sin I equals to N2 sin R. This is the general form of Snell's law. So this is the law that we are trying to prove. So this is also being proved. Easy derivation, no rocket science, only Huygens principle that is mentioned in the previous question. You can write that out. Right? Now let's move on to two numericals. In Young's double slit experiment, the slits are separated by a distance of 0.5 millimeter and the screen at a distance of 1.5 meter from the slits. If the distance of the 9th bright fringe from the central maximum is 1.3 centimeter, calculate the wavelength of the light used. Also calculate the distance of the 5th dark fringe from the central maximum. Now let's see. So here few symbols you have to remember. Small d is the distance between the slits. Small d represents the distance between the slits, which is given by 0.5 millimeter. Millimeter means, again, all the units must be converted into meters because there are a lot of different units. So this will be 0.5 into 10 to the power of minus 3 meters. The distance between the screen and the slits is called capital D. The distance between the screen and the slit is called capital D. Here it is given as 1.5 meter itself, so no need to change that. Okay. Now, if the distance of the 9th bright fringe from the central maximum is 1.3 centimeter. So, bright fringe from the central maximum is given by Yn equals to n lambda capital D by small d. This is for bright fringe. This is for bright fringe. Okay, for bright fringe, any nth order of bright fringe can be written by this formula. From here you can say that lambda is equals to Yn into d divided by n into capital D. Okay, so using this formula you can calculate the wavelength. So distance here mentioned, Yn here is given as, also Yn is given, okay, 1.3 centimeter, 1.3 centimeter. that is 1.3 into 10 to the power of minus 2 meters. Now put all these values over here. 1.3 into 10 to the power of minus 2 into 0.5 into 10 to the power of minus 3 divided by n is 9th bright fringe and d is 1.5. Okay, so you can cancel this. You will get 3 5s are 15, and you get this as 1.3 divided by 27 into 10 to the power of minus 5. So if you divide it, you will get approximately 0.048 into 10 to the power of minus 5, or you can write this exactly as 480 into 10 to the power of minus 9 meter. The unit is meter, all the units are converted, so that means it will be equals to 480 nanometers. So wavelength is calculated. Now next part is still not done. This is not still done. You will still have to answer the second question, where it is mentioned also calculate the distance of the 5th dark fringe. So for dark fringe, okay, the distance of the nth dark fringe is given by 2n minus 1 lambda d by 2d. Remember this dark fringe, this one is easy. This one you have practiced maybe somewhere in competitive exams, but this one is slightly tricky, so be careful. You have to remember for dark fringe as well. Now let's put the values. 5th dark fringe means 2 into 5 is 10 minus 1. Lambda here is given as 480 into 10 to the power of minus 9. D is 1.5, and 2 into small d is 0.5 into 10 to the power of minus 2. So if you simplify everything, you should get about 0.65 into 10 to the power of minus 2 meters, or 0.65 centimeter. Okay, you can use the calculator because in PU board exam simple calculators are used. 10 to the power values you tackle separately, and then you try to use the other values to calculate the decimal values. Okay, so you will get this as 480 nanometers and 0.65 centimeter as the answer. Now let's move on the last question of the day. In Young's double slit experiment, the slits are separated by 0.6 millimeter and the screen is placed at a distance of 1 meter from the slits. The distance between the first dark fringe and the fourth bright fringe is found to be 0.6 centimeter. Calculate the wavelength of the light used. Very interesting. So first of all, what are all the values given? Small d is given as 0.6 millimeter. Now I already explained, so millimeter means 10 to the power of minus 3 meters. Capital D is given as 1 meter. The distance between the first dark and the fourth bright, actually fourth bright will come first. Fourth bright and first dark is given by 0.6 centimeter. 0.6 centimeter means 0.6 into 10 to the power of minus 2. So this is generally represented by a symbol of delta y. So delta y is 0.6 into 10 to the power of minus 2 meters. Okay, now what you have to calculate? You have to calculate the wavelength lambda. We will use the almost same formulas but in a different way. So first we will see what is the position of the first dark fringe. Position is important. Position formula is same, which is 2n minus 1 lambda d by 2d. Okay, now for first bright fringe you have to put n equals to 1 over here. So n equals to 1 means 2 minus 1. So 2 minus 1 means it will be simply 1. 2 minus 1 is 1. 2 into 1 minus 1, right? Instead of n you have to put 1. So that means it will be lambda d by 2d. Okay, this is the first bright fringe. What about the fourth dark fringe? Fourth bright fringe. Fourth bright fringe is easy, which is n lambda d by simple d. Okay, that is 4 lambda d divided by small d. So what is delta y? delta y, as you can see, this one is bigger, so lambda d by small d is common, and you get 4 minus half. 4 minus half. If you find the difference between them, distance between them, you have to take this one first minus the other one. Lambda d by small d is common, so you get this as so 4 minus half is 8 minus 1, 7 by 2, so 7 by 2 lambda d by d. Now what we are trying to find? We are trying to find the wavelength. So lambda equals to 2 delta y into small d divided by 7 capital D. Okay, this is the simple formula. So you put that 2 into delta y is given here as 0.6 into 10 to the power of minus 2. Small d is given as 0.6 into 10 to the power of minus 3, and 7 capital D is given as 1 meter. So if you simplify everything, you should get around 1020 into 10 to the power of minus 9. I am not doing the calculation. Approximately it will be this much meter, or it will be 1020 nanometer. Okay, so this is the correct answer for this question. Okay, 1020 nanometer is the wavelength. Again, as you can see, one of the question is taken from your model question paper, one of them is taken from your question bank. So these kind of questions are very common from this chapter. So if you look into the blueprint of this chapter, there will be two 1 marker question. That means 1 marker questions, one of them will be MCQ and one will be fill in the blanks according to the 3 model paper shared. So that is the expected question. Also, there is no 5 marker, no 2 marker question, only one 3 marker question is going to come from this chapter. So total 5 marks will be allotted for this chapter. This is an easy chapter. If you study a few questions and practice a few MCQs, then definitely you should be able to answer all the questions from this chapter. So what we are going to discuss in today's session, we are going to discuss MCQs 15, we will also discuss fill in the blanks 5, also we will be discussing 7 3 marker questions, including your latest model question paper questions. So let us start. First question: in a photoelectric experiment, the graph related to 2 quantities is a straight line with the slope equals to h by e, then it is a graph of. Very interesting. So how do we know this is a graph? Which quantities graph, and how to determine the slope? If we can write the equation like this, then we know that this represents the slope and C represents the intersection, right? That is the equation of a straight line. So equation of a straight line, if we can write it like this, then we can find the slope as well as the intersection. So here they are asking about the slope. So first, obviously, one equation that comes to our mind from this chapter is the Einstein's equation, which says that K max actually equals to the energy of the photon that is supplied minus the work function. This is the standard equation. Now this K max can be related to in terms of stopping potential. It can be written as EV0, where V0 is the stopping potential. K max, or the maximum kinetic energy of the electron that is coming out during a photoelectric emission, is given by EV0, right? So from there we can write EV0 equals to h nu minus phi naught, or V0 equals to h upon E into nu minus phi by E. Okay, so if you see that if this quantity is represented by y, if this quantity is represented by x, then we can say that this is our slope and this is our intercept along with the sign. Okay, so this is y equals to mx plus c, minus c equals to minus phi by e. Okay, so from here we can say that the slope is basically stopping potential versus frequency of the radiation. Okay, stopping potential versus frequency of incident light. So correct answer is option C. Very careful, in case you forget, start from here and try to configure the equation so that you don't miss out on the correct answer. This is very, very important. Okay, and this question is there in your model question paper as well as in your question bank that is shared by the board. So this question can be very important, not only during your pre-board but also for your final board exam. In photoelectric effect experiment, if only the frequency of incident radiation is increased, then the maximum kinetic energy of the photoelectron decreases, the stopping potential increases, the photoelectric current increases, the photoelectric current decreases. Now here you have to remember one thing, is that if you increase the frequency of the incident radiation, the maximum kinetic energy will increase, right? Again, the same equation, K max or maximum kinetic energy is given by h nu minus phi. Now phi is a constant, so if you increase the frequency, then K max should also increase, right? But here they are saying that maximum kinetic energy decreases, so definitely this is not correct. Decreases is not correct, it should increase. Secondly, stopping potential increases. So if K max is increasing, we know that K max is given by E V naught. So if K max increases, V naught should increase, E is a constant, right? So if frequency increases, K max increases. If K max increases, stopping potential increases. So this is the correct statement, because it is a stopping potential is getting increased, so that is the correct statement from this statement. Now photoelectric current is independent of the frequency, it depends only on the intensity. Saturation current or maximum photoelectric current, it is independent of the frequency. It only depends that the frequency has to be more than the threshold frequency. If that condition is satisfied, then definitely photoelectric current is independent of the frequency. It only depends on the intensity. Okay, clear? Now let's move on. The de Broglie wavelength of a moving particle is independent of dash of the particle: charge, mass, speed, momentum. Now de Broglie wavelength is given by what? Lambda equals to h upon p, where p is momentum, or h by mv. So definitely lambda depends on momentum, lambda depends on mass, lambda depends on velocity as well, but there is no mention of charge, so definitely it is independent of charge. De Broglie wavelength is independent of charge. Next, the process of emission of electrons from a metal surface by applying high electric field. By applying high electric field is called field emission, as the name suggests. So remember, high electric field or electric field emission due to electric field is called field emission. By heat is called thermoionic emission, okay, and by light is called photoelectric emission. Okay, secondary emission is not important. So these three emissions are there in your textbook, so you should remember: due to heat, thermoionic; due to field emission; and due to light, it will be photoelectric emission. In photoelectric effect experiment, the graph of a physical quantity y versus a physical quantity x is a straight line passing through the origin. So in photoelectric effect, this is a graph that they are talking about, y versus x. Okay, so what is this graph represents? Definitely this represents the photoelectric current, and this represents the intensity of the light. Okay, so it is a photoelectric current and x is intensity of incidence. So y is photoelectric current, x is intensity of incident radiation. In only this case, the graph will be a straight line passing through the origin. Okay, now let's move on. Macroscopic particle in our daily life do not show wave-like properties because they are not associated with waves. Their wave is extremely high, their wavelength is 0, their wavelength is negligibly small. So in this case, the correct answer is the wavelength is negligibly small. Okay, so we know that wavelength is given by h by lambda, h by p. So for us, even if you can increase the velocity or mass or whatever it is, the problem is this h. H's order is of the order of 10 to the power of minus 34. Right, that is the Planck's constant. So that's why what happens, no matter whatever you do, okay, you cannot have a very high wavelength. Wavelength high is possible only when the mass is very, very small, so that they can cancel, right? So that's why you cannot have a very high wavelength, and wavelength is not 0, by the way. Even though it's small, it is not 0, it has a physical value. So that's why you have to write negligibly small. Next question, wavelength of matter wave is known as Einstein's wavelength, threshold wavelength, de Broglie wavelength. We all know that the wavelength of matter wave is called de Broglie wavelength. Photoelectric emission, emitting electrons, applying heat, electric field, magnetic field, light. So photoelectric emission happens due to the emission of light. Next, according to de Broglie, the material particle exhibits wave nature only at rest, only in motion, only when kept at a rest in magnetic field, only when kept at a rest in electric field. So electric field and magnetic field has nothing to do with de Broglie wavelength. Again, the same formula, lambda equals to h by mv, that is, it has to be in motion. If it is not in motion, then we will not get any wavelength. So that means it only in motion we observe de Broglie wavelength. Photoelectric effect was discovered first or observed by Einstein, Hallwach, Leonard or Hertz. It was Heinrich Hertz. Heinrich Hertz, the same person on which the unit of frequency is named. Okay, Heinrich Hertz is the person who first observed the photoelectric effect. Minimum frequency required for photoelectric effect is minima, threshold frequency, Einstein's frequency, de Broglie frequency. Interesting question. It is called threshold frequency. The minimum frequency required for photoelectric effect to take place is called threshold frequency. Einstein's photoelectric equation is in accordance with conservation of mass only, conservation of charge only, conservation of energy, conservation of momentum. So Einstein's photoelectric effect is only based on conservation of energy. Okay, conservation of energy, Kmax equals to h nu minus phi naught. That is, Kmax is the energy, h nu is the energy of photon, and phi is the minimum energy required to liberate one electron, right? So from there it's an energy equation, and we can say this is based on conservation of energy. In photoelectric experiment, if both the intensity and frequency of the incident light are doubled, then the saturation photoelectric current is doubled, remains constant, becomes 4 times, is halved. So photoelectric experiment, intensity and frequency both are doubled. Now we know that the saturation current is directly proportional. So saturation current is directly proportional to the intensity, right? Directly proportional. So, and there is no relationship with frequency. So if it is doubled, if intensity is doubled, then saturation current will also be doubled. It will not be 4 times because both of them are increasing. Saturation current is independent of the frequency, so that means only it will be doubled and not quadrupled or not remain same. If only frequency is doubled, intensity remains same, then it will remain same. Okay, because the intensity is getting doubled and they are direct proportional relationship, that means current will also be doubled. Very interesting question. The maximum kinetic energy of the photoelectrons depends only on incident angle, potential, pressure, frequency. So maximum kinetic energy depends only on frequency. It does not depend on anything else. Okay, Kmax equals to h nu minus phi. So Kmax depends on frequency of incident wave, that is nu. That's why it depends only on frequency. Light of certain frequency and intensity incident on a photosensitive material causes photoelectric effect. The incident radiation made exceedingly dim. Okay, so we have a photosensitive material. Some incident light is falling on this. Suppose initially we had a lot of bright light falling on this, and we are getting some electrons out of this surface. Okay, that is called photoelectric effect. In photoelectric effect, light is falling on a surface, and in return we are getting some electrons out of the surface. Now what happens is that suppose you make the source exceedingly dim. That means you decrease the intensity of the light. Then what will happen? Photoemission will cease to exist. Will the photoemission will cease to exist? It does not depend on the intensity of light. Photoemission will still take place. Saturation current might change, but photoelectric effect will not cease. Even if the light is very dim, it will still continue. Photo emission will continue but saturation current will decrease. Yes, this is the correct statement. Photo emission will continue but saturation current, which is proportional to intensity. That's why intensity decreasing means saturation current will decrease, but the photoelectric effect will not cease to exist. Cease to exist means it stops, but it is not happening. Okay, so be careful about certain language. Other options, photo emission will continue but saturation current will increase. Saturation current cannot increase because you are decreasing the intensity. None of the above is obviously not the answer. Now let's move on to the fill in the blanks question. In interaction with matter, light behaves as if it is made up of packet of energy. Okay, in interaction with matter, light behaves as if it is made up of packet of energy called. So what is the name for packet of energy? It is called frequency, wave, intensity, particle, photon, zero. So it is known as photon. From the given option, this must be the term photon. The charge of a photon is, photon is a uncharged particle. It can be considered as an uncharged particle in motion. So charge of a photon is 0. Next, maximum kinetic energy of a photoelectron depends only on the dash of the incident radiation. So the maximum kinetic energy depends on frequency. 0 is also done. So maximum kinetic energy depends only on frequency. Again, the same equation, K max equals to h nu minus phi. So from here we can say that maximum kinetic energy depends on, in some cases we write phi naught. Okay, so this is called the incident radiation. That means this is the frequency. The answer will be frequency in this case. The saturation current in photo emission depends on the dash of the incident radiation. Saturation current depends on the intensity. Saturation current depends on the intensity of the incident radiation. So correct answer is intensity. A fast moving electron will behave as a wave. A fast moving electron will behave as a wave. Okay, so correct answer is wave. Now let's move on to the 3 marker section. There is no 2 marker question going to come from this chapter, only 3 marker question, no 5 marker numerical. Like last year there was a chance from this chapter, there was a small possibility of 5 marker numerical, but that did not came. But this year according to the blueprint, there will be no 5 marker question, only 3 marker 1 question will come, and we will practice all the questions that is going to come from this chapter. Give Einstein's explanation of photoelectric effect and write Einstein's photoelectric equation. Okay, Einstein suggested that each photon of light has energy proportional to frequency nu given by E equals to h nu, where h is Planck's constant. When light shines on a metal surface, photons transfer their energy to electrons in the metal. Okay, any energy from the photoelectron exceeding the work function becomes the kinetic energy of the ejected electron. So now this is first part. Write Einstein's photoelectric emission. We will see in another question, don't worry. Okay, give any 3 results of experimental study by photoelectric effect, or same question might come, write the experimental observation by Hallwach and Leonard. Okay, Hallwach and Leonard's observation, same question, only thing is the name is different. Okay, Hallwach Leonard's observation or any observation of photoelectric effect, same question. For a given metal, no electrons are emitted if the frequency of the incident light is below a certain minimum value called threshold frequency. Very important. Okay, regardless of the intensity of light. Photoelectric emission occurs without any noticeable delay. So it basically happens in the time 10 to the power of minus 9 second delay. There is a delay, but delay is 10 to the power of minus 9 second, which is almost negligible. Okay, after the light strikes the surface, even for a very low intensity. Okay, so when as soon as the light strikes the surface, we get one electron out of the surface. That is basically photoelectric effect. The maximum kinetic energy of the emitted electrons increases linearly with the frequency, the incident light above the threshold frequency. Okay, so the maximum kinetic energy of the emitted electron is increasing linearly. Okay, the maximum kinetic energy increases linearly with the frequency. Okay, this is K max and this is the frequency. This is the cutoff frequency nu naught. Okay, the intersect, otherwise this is a straight line, right? Now let's move on. What is meant by photoelectric effect? Defined work function, defined threshold frequency. This is also very popular question. The photoelectric effect refers to the phenomenon where electrons are emitted from the surface of a metal when light of a certain frequency or higher shines on it. These emitted electrons are called photoelectrons. Next, the work function. The work function phi is the minimum energy required to eject an electron from the surface of a metal. It is property of the metal and is typically measured in electron volt. Okay, work function also depends on temperature. Next, the threshold frequency nu naught is the minimum frequency of the incident light required to cause the emission of electrons from the surface of the metal. For light with frequency below nu naught, no electrons are emitted regardless of the light intensity. Okay, so this is called threshold frequency. Threshold frequency is the minimum frequency and work function is the minimum energy required. Okay, so they are related to each other but not exactly, there is a small conversion that work function is actually given by h nu naught. Okay, that's how they are related. In case you want to remember it, that is how they are related. Now mention Einstein's photoelectric emission and explain the symbols. The same question was asked in that part, so I skipped it because I have covered it in a separate equation. This is the Einstein's photoelectric emission where h nu is the energy of the emitted light. Okay, this is the energy of light. This is the energy of light. And phi is the work function, and half mv squared is the kinetic energy of electron. Okay, h is Planck's constant, 6.626 into 10 to the power of minus 34. You can assume this 6.63, that is also fine. Nu is the frequency of incident light, phi is the work function of the metal, m is the mass of electron, 9.11 into 10 to the power of minus 31. V is the velocity of ejected electron. Okay, if you don't want to write half mv square, you can write k max as well. Okay, or the equation that I was writing, that also fine. K max equals to h nu minus phi naught, that is also fine, but you have to explain the terms very clearly. Now next, the work function of cesium is 2.14 electron volt. Calculate the threshold frequency for cesium. How to calculate? So work function of cesium is given by, so work function means phi or phi naught, that is given by 2.14, and they ask you calculate the threshold frequency. So what is the relationship between threshold frequency and work function? This is basically simply h nu naught equals to 2.14 EV. Now EV to joule, you have to convert EV to joules first. So 1 EV is basically 1.6 into 10 to the power of minus 19 joules. Anything familiar with this? What is this? This is the charge of an electron. Okay, only thing, if you multiply with 1 volt and 1 charge of an electron, you get 1 electron volt. Okay, and because it saves us some space for smaller energy, we use EV. Okay, so here in this particular case we have to convert it into joules, so we have to multiply with 10 to the power of minus 1.6 into 10 to the power minus 9. So what is the threshold frequency? Threshold frequency is 2.14 into 1.6 into 10 to the power of minus 19 divided by 6.63 into 10 to the power of minus 34. Okay, if you calculate this approximately using a calculator, you will get 0.52 into 10 to the power of plus 15. Okay, plus 15. And what is this? This is a frequency. So what will be the unit of frequency? Unit of frequency will be hertz. Same person hertz. So you can write this as 5.2. You can leave the answer over here, or if you don't want to keep it as a decimal number, 5.2 into 10 to the power of 14 hertz. Anyway, it is correct. Okay. Easy question. Only thing you need to know is how to convert from electron volt to joules, and then the Planck's constant value, which are very, very standard values. Now let's move on. Write any three properties of photon. These questions are last question, this question and next question are from your model paper. Any three properties of photon are: photon has zero rest mass and always travels with the speed of light in vacuum. Okay, so this is photon. Even though it is a photon, it is traveling at a very high speed, the same speed of light. A photon carries an energy E equals to h nu and momentum P equals to h by lambda. Okay, a photon is electrically neutral and is not deflected by any electric or magnetic fields. Okay, so these are the three properties of photon. All of them are very, very important. Don't forget them. It also came one time in a previous year paper as well. So you have to prepare this question as well. What are matter waves? Explain the de Broglie hypothesis of matter waves. So matter waves are the waves associated with the moving material particles such as electrons, photons, atoms, etc. De Broglie hypothesis. Now de Broglie hypothesis, Louis de Broglie proposed that every moving particle behaves like a wave. So matter wave means wave associated with moving particles, and de Broglie suggested every moving particle will have their own wavelength. Okay, just as light shows particle nature. Because why he assumed it? Because he thought nature likes symmetry. Okay, most of the natural things are symmetrical. For example, we have right hand, we have left hand. So even if you look it from like this, we are symmetrical on both sides. So that is one thing to consider. Okay, if you consider our brain also, it is symmetrical on left and right lobe. There are two lobes. So most of us are symmetrical in nature, and that's why de Broglie proposed that when this entire photoelectric saga was going on, Einstein's explanation etc. was going on, he suggested that nature likes symmetry, and that's why if light can behave like a particle, then particles will also behave like a wave. That was his point. That's why it is called hypothesis. Later on, Davison and Germer did an experiment and proved this hypothesis. It is no longer a hypothesis, this is a theory now. But anyway, when he gave this is called hypothesis, because like Avogadro number, okay, Avogadro's hypothesis. Now it is Avogadro's theory, right? When Avogadro gave it the exact number 6.623 into 10 to the power of 23, people thought, okay, this cannot ever be proven, but it was later proved. Similarly, here de Broglie hypothesis initially was given as a hypothesis, later on it was also proven. Okay, so his idea was, because light is behaving like a particle will also behave like a wave. Okay, according to him, any particle of momentum P has an associated wavelength lambda called the de Broglie wavelength. Because he gave the theory, the wavelength is called de Broglie wavelength, and the value is very simple, lambda equals to h by P, where lambda is the de Broglie wavelength, h is Planck's constant, P equals to mv equals to momentum of the particle. Clear? So this is it. So atoms is the first chapter. Now let us look into the blueprint of the chapter atoms. So here we are going to discuss one marker question. We are going to get one marker question and one 2 marker question. So there will be no fill in the blanks coming from this chapter, and the weightage of this chapter is only 3, but we will try to finish it as quickly as possible. How many questions we are going to discuss? We are going to discuss 15 questions of 1 marker and 5 questions of 2 marker. So let us start with the MCQs. The total energy of an electron revolving in nth orbit of hydrogen atom is least for So total energy of total energy is least means it maximum negative, so it will be negative. So total energy for ground state, total energy of any state, actually let us start with total energy of any state is minus 13.6 divided by n square. So if the n value is smaller, then we will get the least value, because this is a negative sign. There is a negative sign, means higher the negative value, smaller is actual value. That means it is least for n equals to 1. That's why it is the most stable orbit. Lower the energy, it is more stable. Right? Next question, the minimum energy required to free the electron from the ground state of hydrogen atom is. Obviously the total energy is minus 13.6 electron volt, so you will need at least that much energy to free up an electron. Okay, so 13.6 electron volt energy you will need to free up one electron from hydrogen's ground state. Next, let K be the kinetic energy, U be the potential energy, and E be the total energy of the electron revolving around the nucleus in hydrogen atom. Then which of the following is correct? K greater than 0, U greater than 0, E greater than 0. Let us understand about the energies. So total energy, you already realized total energy is negative. What about kinetic energy? Kinetic energy is given by, kinetic energy for any object is given by half mv squared. This is true for electrons as well. Now mass cannot be negative. Even if velocity is negative, square of velocity cannot be negative. That means half mv square is always positive. So that's why we say that kinetic energy is always positive. Right? Now in case of atomic physics, kinetic energy will still be positive. Okay, total energy is negative, potential energy will also be negative. That's why electron is orbiting around the nucleus. So potential energy and total energy are negative, whereas kinetic energy will be positive. So if you read the options, kinetic energy positive, potential energy is negative, total energy is also negative. Right? So option B is correct. The impact parameter is minimum in alpha particle scattering experiment for the scattering angle of. Interesting question. What is impact parameter? Impact parameter is the perpendicular distance between the trajectory and the center of the nuclei. So if the trajectory is along this, then this is called impact parameter. This distance is called impact parameter B. Okay, now if it is said that the for alpha particle scattering, the impact parameter is minimum. Impact parameter is minimum means it is going straight towards the nucleus. It is going straight towards the nucleus. Then impact parameter is 0, and it will come back straight along the path it went. It will hit the nucleus, or it will try to hit the nucleus. Okay, it will go to the distance of minimum closest approach, distance of closest approach, and then it will come back. Right? So that means the deflection will be 180 degrees. So when the deflection is 180 degrees, the impact parameter is minimum. Okay, don't fall into the prey. Minimum means 0 degree. No. Next, Bohr's atomic model cannot explain spectral lines, stability of atoms, fine structure of spectral line, all of the above. So Bohr's atomic model can explain spectral lines. It can also explain the stability of atoms. Only thing it cannot explain is the fine structure. Okay, fine structure means the splitting of electric spectrum under the effect of external fields. So that's why Bohr model is not complete. It is the first correct step towards finding the correct model, but it was not complete because it was not able to explain the spectral lines, fine spectral lines. The ratio of radii of first 3 Bohr orbit. So ratio of radii of first 3 Bohr orbit, R1 is to R2 is to R3. Okay, so this will be equals to R1 is to 2 square R1 is to 3 square R1. Okay, Bohr's orbit, for nth orbit it is given by n square R1. Okay, so this is the first ground state orbit. So from here you can say that this must be 1:4:9. So correct answer is 1:4:9. Option C is correct. Now let's move on. At the distance of closest approach for alpha particle with gold nucleus, both kinetic and potential energy are equal. Okay, so distance of closest approach of alpha particle with gold nucleus, both kinetic energy and potential energy are equal. Entire kinetic energy is converted into potential energy. That is the correct answer. Kinetic energy is not equal to potential energy. The initial kinetic energy is exactly equals to the potential energy. So entire kinetic energy is converted into potential energy. They are not balanced by each other. Okay, so entire kinetic energy is converted into potential energy and it momentarily stops at the distance of closest approach. So that's why option B is correct, not option A. Don't fall for the trap. Don't answer option A. Rutherford's nuclear model of atom fails to explain large angle scattering of alpha particle, charge distribution of an atom, energy of electrons revolving around the nucleus, origin of line spectra of hydrogen atom. Actually it is many of the points, but main is origin of the line spectrum of hydrogen. It cannot explain. Okay, energy of electrons can be explained. Charge distribution partly can be explained. Large angle scattering of alpha particle, obviously it was assumed that the center is obviously at the center, it is located at the center. That's how it was came to be. So large angle scattering, based on large angle alpha ray scattering, Rutherford gave its nuclear model. So definitely these three can be explained. But spectral line, why we observe spectral line, that was not clear. So that's why spectral line of hydrogen was not been able to explain using Rutherford's nuclear model. The scientist who is credited with the discovery of nucleus, it's Rutherford. Okay, Rutherford is the person who was credited with the discovery of nucleus. When white light passes through a gas and we analyze the transmitted light using a spectrometer, we find some dark lines in the spectrum. These dark lines are called emission spectrum, absorption spectrum, missing line, dark band. They are called absorption spectrum. So you have a gas, okay, and a light is passing through this gas, and when you observe this gas, suppose there are 4 lines, but when you observe it, you find only 2 lines and 2 of them are missing. Okay, so this is called absorption spectrum. Like emission spectrum, same thing is possible for absorption spectrum as well. So what is the meaning of absorption spectrum? For example, the light which is coming from sun, okay, when it is passing through our atmosphere, some of the emitted lines are absorbed, some of the emitted frequencies are absorbed, right? For example, all the UV rays are absorbed by our ozone layer. So that's why we do not have that ozone UV rays present in our light, right? Similarly, some other dangerous rays, some other infrared rays can also be absorbed during our atmospheric gases, that is transit through the atmospheric gases. So those are called the absorption spectrum. That means the gases absorb those radiations and then they give you the output. That's why it is called absorption spectrum. What is the meaning of emission spectrum? When you excite a gas, okay, you heating up a gas, or you are sending some electrical energy through a gas, then that gas automatically emits some radiation. That is called emission spectrum. So emission happens when the gas is excited, absorption happens when the gas is at neutral state and some ray of light is passing through this. Next, the lowest state of the atom called lower orbit, ground state, earth state, none of the above. What about call it Empire State Building, right? No, it is called ground state, not Empire State from where King Kong jumped. If you remember the movie, King Kong jumped from the top of a building. Empire State, but not Empire State, it is ground state. The radius of nth Bohr orbit is proportional to n square. the total energy of the electron orbiting a hydrogen nucleus is negative. This implies the fact that the electron is free to move, electron repels the nucleus, electron is bound to the nucleus, all of the above. So when we say that the energy of electron is negative, that means electron has to pay back the money, okay, then only it can leave. So electron is not free to leave, it can move only in its orbit. So basically you have taken loan from some person, some of your friend, and you cannot leave him. If you leave, then he will kill you, something like that, some imaginary situation. So that's what is happening over here. Electron has taken some loan from the nucleus, and that is minus 13.6 electron volt. So if he wants to leave the nucleus, it has to pay back that energy, and then only it can leave. So if someone else gives him that minus 13.6 EV, that is positive 13.6 EV, then it will repay its debt, and it can move to the it can move freely, right? So electron is bound to the nucleus. Electron is bound to the nucleus. The total energy of electron orbiting hydrogen is negative. That means electron is bound to the nucleus. So it has some money to pay back. So once he is paying back that money, he can leave. Otherwise, throughout his lifetime, it will keep on orbiting the nucleus. Next, in a Bohr atom, an electron emits energy only when it moves from ground state to excited state. Okay, in Bohr atom, an electron emits energy when it is moving from excited state to ground state. So electron emits energy when it is moving from excited state to ground state. From ground state to excited state, it will absorb energy, okay, and it will give out energy when it is jumping from excited state to ground state. Okay, so option B is correct. The energy of an electron at the ground state of hydrogen atom is minus 13.6 eV. Okay, the energy means total energy. Okay, total energy of electron at the ground state of the hydrogen atom is minus 13.6 eV. Write any two postulates of Bohr's atomic model. Now, Bohr's atomic model, postulates of Bohr's atomic model, one of the most important questions. Previously, it can come as a 3 marker, but from this chapter, this year, we are only expecting 2 marker questions. So, they will change the question like that. So, there are 3 postulates. So, they will say write any 2 postulates, okay. So, an electron cannot move round the nucleus in all orbits. It can only move in certain discrete, discontinuous orbits, okay. So, there is no link between 2 orbits. They are discontinuous and obviously discrete. Discrete means they are separated from each other. The permitted orbits are those in which the angular momentum of the electron is an integral multiple of h by 2 pi, that is mvr equals to mvnRn equals to nh by 2 pi. When the electron moves in these orbits, energy is not given out. Energy is given out only when an electron from a higher energy state jumps to a lower energy state. The difference in the energies is permitted in the form of E1 minus E2 equals to h nu. Okay, clear? So any 2 you can write for this question. So this year there will be you don't need to remember all 3. You can study any 2 and you should still get the marks. Write 2 limitations of Bohr's atom model. Now we have to write down the limitations. Previously was postulates, now it is the limitations. Bohr's model is applicable to hydrogenic atoms. It cannot be extended even to mere 2 electron atoms such as helium. While the Bohr's model correctly predicts the frequencies of the light emitted by the hydrogenic atoms, the model is unable to explain the relative intensities of the frequencies of the spectrum. The model does not explain the fine structure and splitting of spectral lines observed under the magnetic field Zeeman effect or electric field Stark effect. Okay, so Bohr's atomic model cannot explain Zeeman effect and Stark effect. Okay, also it cannot be extended to more than 1 electron system, for example helium, lithium, and also it is unable to explain the relative intensities. According to Bohr's model, all lines should be equally bright, but when we observe the spectrum, we see some of them are more bright than some other one may be slightly little bright. So that's why relative intensities cannot be explained using Bohr's model. Define impact parameter. What is the angle of scattering for minimum impact parameter? So impact parameter B is defined as it is the perpendicular distance between the initial direction line of motion of an incident particle and the center of the target nucleus when the particle is far away from the nucleus. Suppose we have a nucleus and an alpha particle which is moving along this line. This is the center of the nucleus. So the impact parameter is defined as the, if you continue on this path, okay, the distance between the line of the path and the center of the nucleus is called impact parameter, and that is denoted by symbol B. Okay, angle of scattering for minimum impact parameter. So minimum impact parameter corresponds to a head-on collision, that is impact parameter is 0. In this case, the particle is scattered through an angle of 180 degrees. So we have seen one MCQ as well as long answer question from this concept, and this question is taken from your latest model paper. The radius of the innermost electron orbit of a hydrogen atom is 5.3 into 10 to the power of minus 11 meter. Determine the radius of the n equals to 2 orbit. This is again your model question paper problem. So we know that Rn equals to n square R1. Okay, so n square is 2 square into R1 is this value 5.3 into 10 to the power of minus 11. So 4 into 5.3 into 10 to the power of minus 11. So it will be 21.2 into 10 to the power of minus 11 meter. Very simple, easy question. Okay, Rn equals to n square R1. R1 is given in this problem, so you just need to put that value and calculate. Okay, 2 marker question. If you just add it, do it, you can get the 2 marks. Mention 2 drawbacks of Rutherford's atomic model. So Rutherford's atomic model fails to explain stability of atom, no explanation for atomic spectra, does not address the electron arrangement. Okay, so these are the main 3 drawbacks. Any 2 you can remember and answer. Now next chapter is nuclei. So nuclei, again we will be checking the blueprint. So in the blueprint there will be one 1 marker question and 1 3 marker question. So total marks allotted for this chapter is 4. Okay, and in this lecture we are going to discuss 15 very important MCQs and 5 as usual 3 marker question. So let us continue. Among the following, which set of nuclei are isotopes? Isotope means they have same element and a different number of atomic mass. So same element means their neutron number should be same, symbol should be same. So U 23592, U 23592. I think there should be some mistake. This should be 238. Okay, so these 2 should be your isotopes. Okay, now next, the radioactive decay in which very high energy photons are emitted is called. So radioactive decay in which a very high energy photons are emitted is called gamma decay. Alpha decay, beta decay are not high energy photons, they are basically particles. That's why they are fast moving particles but not high energy photons. Photon means only gamma decay where gamma rays are emitted. Next, the ratio of nuclear densities of aluminium 22713 and 64 copper 29 is. So nuclear densities of elements are constant, okay, except some very few lighter and very high atomic mass objects. Ratio of nuclear densities is constant, so it will be 1:1. Ratio is 1:1. You do not need to take square root or anything. Radius okay, you can calculate radius, but they ask you about nuclear densities. Nuclear densities means it must be constant. So whatever is the nuclear density for aluminium, same should be for copper as well. The nuclear force is attractive for distance equals to 0.5 fermion. Attractive for distances less than 0.8 fermion, repulsive for distance 0.8 fermion, repulsive for distance less than 0.8 fermion. So here remember that nuclear force is repulsive up to 0.8 fermions, and it becomes attractive from 0.8 towards higher values. Okay, 0.8 to 2.2 actually is the range where nuclear force is active. Beyond to 2.2 nuclear force becomes 0. So attractive for distance r equals to 0.5, definitely not correct, because this distance is less than 0.8 fermion. So definitely at this range it is repulsive. Attractive for less than 8, again in this range it is repulsive. Repulsive for r greater than 0.8, again this is wrong, because in this range it is attractive. So repulsive for distance less than 0.8 is only correct answer. So this is the correct answer. This is one of the previous year questions came from this chapter. The nuclear radius of the order of, the nuclear radius is of the order of 10 to the power of around, nuclear radius is 10 to the power of 14 times more than that of the atomic radius. So you can take consider this to be of the order of 10 to the power of minus 10 meters. Minus 15 is too small. Okay, it is of the order of 10 to the power of minus 10 meters, slightly few hundred Fermis. Okay, so here you can see this is few hundred Fermis. This distance is much smaller than 1 Fermi. In that case nuclear cannot exist, because smaller than 1 Fermi means the force will always be repulsive. Okay, Fermi means 1 Fermi means 10 to the power of minus 12 meter. Okay, nuclear radius is greater than this value, and that is here only one greater than this value is 10 to the power of minus 10. So it is approximately 10 to the power of minus 10 meter. Chadwick discovered photon, proton, electron or neutron. Chadwick discovered neutron. Okay, remember that photon is mostly associated with Albert Einstein, proton is associated with Rutherford, electron is associated with J.J. Thomson. Okay, so remember that this is Einstein, this is proton is Rutherford, and electron is J.J. Thomson. Okay, and neutron is discovered by Chadwick. Okay, so in one table all the discoverers are mentioned. Next, the ratio of nuclear mass to the nuclear volume is called nuclear mass, nuclear volume, nuclear charge, nuclear density. Easy question. Mass by density, mass by volume is always density. In case of nuclear mass by nuclear volume, it will be nuclear density, and normally it is a constant quantity. 1/12 mass of carbon 12 atom is 1 atomic mass unit, or 1 U or 1 AMU. Okay, neutron was discovered by, okay, same question, James Chadwick. Okay, repeated question, but they have changed the order. So neutron was discovered by James Chadwick. Nuclei with same atomic number are called, same atomic number means they have the same number of protons, that means they are called isotopes. Okay, same mass number are called isobars. Okay, isobar means same mass number, and isotones are same neutron number. Isomar is from organic chemistry. Chemistry ma'am will teach you more about isomers. Okay, not me. Next, the equivalent energy of the mass defect is atomic energy, nuclear binding energy, nuclear fission, nuclear fusion. So the equivalent energy of the mass defect is called nuclear binding energy. So the equivalent energy of mass defect is nuclear binding energy, not fission, not atomic energy, okay, not fusion, it is the nuclear binding energy. Next, nuclear fission is a process where two light nuclei combine to produce a heavy nucleus, two heavy nuclei combine to produce even heavier nucleus. The options are making me laugh. One heavy nucleus breaks into one or more stable nuclei, so that is the correct answer. Fission is process where it breaks down, okay, one heavy nucleus when it breaks down into more stable and lighter nuclei, that is called fission. Fusion is when two are fusing together. An alpha particle is hydrogen nucleus, helium nucleus, hydrogen atom, helium atom. Alpha particle is doubly positive helium, that is basically the nucleus of helium. The nuclear force between neutron-neutron is more than between proton-neutron. Proton-neutron is more than that between neutron-neutron. Neutron-neutron and proton-neutron are same. So option C is correct. Okay, this will be proton. So nuclear force between neutron-neutron and proton-neutron are same. The energy equivalent to a substance of mass 1 gram is. So let's do this calculation. So energy equivalence means we have to use our age old formula, E equals to mc square, and mass here given as 1 grams. 1 gram means 1 into 10 to the power of minus 3 kilograms, and C is 3 into 10 to the power of 8 whole square. So it will be 10 to the power of minus 3 into 9 into 10 to the power of 16. So it will be 9 into 10 to the power of 13 joules. So the corresponding energy is 9 into 10 to the power of 13 joules. Now let us move on to 3 marker question. First question, differentiate between nuclear fission and nuclear fusion. Again, this is a new question, came in your model paper. And so nuclear fission is a heavy nucleus splits into two lighter nuclei. Nuclear fusion is when two light nuclei. So in fusion you need to have minimum 2 atoms, okay. So two light nuclei combine to form a heavier nucleus. Occurs in heavy elements like uranium-235, plutonium-239. Occurs in lighter elements like hydrogen isotopes H2H3. Releases moderate amount of energy, releases very large amount of energy, much greater than fission, okay. Reaction can be controlled in a nuclear reactor, and reaction is extremely volatile, and it is very difficult to control in our environment, okay. That's why cold fusion or fusion which can be controlled, if you can determine a machine or you can design a machine which can withstand nuclear fusion, then definitely you will get a Nobel Prize, okay. This is not achieved by any human till date, because the initial temperature required to start nuclear fusion is equivalent to the temperature of sun. You can create that using atomic energy. So you have to conduct a fission, okay, that is you have to blast a nuclear bomb to generate enough energy to blast a hydrogen bomb, okay. Hydrogen bomb, that is one of the form of bombs where nuclear fusion takes place, okay. So nuclear fission has to be done first to do a nuclear fusion. So that's why it is very, very tricky and difficult to achieve, and the energy that will be released obviously will be enormous. Next is define binding energy and mass defect. Write the relationship between them. The difference in mass of nucleus and its constituents delta M is called the mass defect. So delta M equals to ZMP plus A minus ZMN minus M. The energy required to separate a nucleus into its nucleons is called nuclear binding energy, EB. That is EB equals to delta M C square. Right. So if you calculate delta M, you can calculate the binding energy as well. Next, write three properties or three characteristics, three types or three characteristics of nuclear force. So the nuclear force is much stronger than the Coulomb force acting between charges or the gravitational forces between the masses. You can write that nuclear force is the strongest force. The nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers, or nuclear force is a short range force. Okay, and if you can mention, if you are writing short range, you have to explain it. Okay, the nuclear force between neutron proton and proton is approximately same. That is, the nuclear force is independent of electrical charge. Next, calculate. So from this chapter sometimes we can get some binding energy related small numerical problems. So we will be solving two numerical problems. That's it. Calculate the binding energy of an alpha particle in mega electron volt from the following data. Mass of alpha particle is 4.00260 U. Mass of one neutron is 1.008662. Mass of proton is 1.007825. Now to exactly calculate the value, you have to use a calculator. Okay, I will not do the exact mathematics. I will just tell you how to calculate it. You have to do the mathematics yourself and tell me the answer in the comment section below. Okay, so what is the calculation? Calculation is simple, that mass of alpha particle is 4.00260. So we have to calculate the mass defect. Delta M equals to mass of neutron. Mass of neutron is Mn into number of neutron plus mass of proton into number of protons minus the actual mass of the alpha particle. Okay, now how many neutrons are there in an alpha particle? In an alpha particle, total nucleons are 4. Out of that, 2 are protons and remaining 2 are neutrons. So it will be 1.00866 into 2 plus 1.00785 into 2. This is the rest mass of alpha particle, but when they form the alpha particle itself, the mass reduced to this value, which is 4.00260. Okay, so you have to calculate the binding energy in terms of MeV. So this way you will get the binding energy in U. Okay, and it will be 2.086 into 2 is 17.86 means 160, 172 plus 12, 173. So this should be the somewhat closer to the value. Okay, this calculation you have to do on your own. I am doing some approximation method. So 2.015, approximately 2.15. Okay, 2.17 and 2.15. Again, as I mentioned, I am not doing exact calculation. You have to calculate it exactly using a simple calculator. 4.00260. If you add it, you will get 4.032 minus 4.0026. So it will be approximately 0.0294. Approximately, this will be the change in binding energy. This is the this mass is called the mass defect. So corresponding binding energy is given by delta M C square, but we will not use this method. What we will be using, we will convert this directly by delta M into 931.5 MeV by C square. So this will be 0.0294 into 931.5 MeV. Okay, so this is the way to convert directly, right, from mass defect to binding energy. Mass defect to binding energy you have to multiply with 931.5. okay, this is an easy conversion. So this will be coming out to be, I think, 1.8 about. Okay, you can calculate this exact value. As I mentioned, I will be not solving that. 1 2 3 2.9 into 9. Okay, I think it will be coming out around 18. You can check that out and you can calculate, tell me the exact value. Okay, mention it. I will not be solving this value. This is up to you. Find the binding energy of an alpha particle from the following data. Almost same data problem, only thing is that the values are different. So this is a homework for all of you. Okay, this is a homework for all of you. Solve it. Same question, the data is slightly different, so mass of the nucleus is different, rest mass of the proton is also slightly different, rest mass of neutron is slightly different. Okay, there are few problems on from which the questions can come. So this is a homework. So every problem will be similar. Okay, so either it will be asked as a nitrogen or an oxygen or alpha particle. Okay, only you have to remember the only formula that you need to use is mass defect is number of neutrons into mass of neutron plus number of protons into mass of protons minus the total mass, and at the end the binding energy is given by delta M into 931.5. and if they ask you binding energy per nucleon, then what you have to do, you have to divide it with the total number of nucleons. For example, for alpha particle the nucleon number is 4. Okay, for nitrogen 14 the number of nucleon is 14. Okay, so remember that total atomic mass or atomic number you have to divide it, then you will get the binding energy per nucleon. Okay, so this is a homework. Solve it and let me know the answer. So in the blueprint you can see that there will be 1 marker question 1, there will be short 2 marker question 1, and there will be no 3 marker question coming from this chapter. So 3 marker portion is blanked, and 1 guaranteed 5 marker question will come from this chapter. Total marks allotted for this chapter is 8. Now in the MCQ section, what we are going to discuss in today's session, we are going to discuss 15 MCQs. We will also be discussing 2 marker question 5 and 5 marker questions 3, that is sufficient to score the marks, 8 marks that is allotted in this chapter. So let us start. First, we will, as usual, we will start with MCQs. MCQs are the part where you struggle the most, so don't skip the video, watch till the end so that you are confident with all different types of MCQs. In the figure, EV and EC are the valence band and conduction band corresponding to an extrinsic semiconductor. Capital E is the energy state corresponding to the impurity present in it. The input, the impurity present it can be. So here if you see that the level of impurity shown over here are like this. So this is a donor level. This is called acceptor level. This accepts electron from the valence band. It accepts electron in the valence band and creates more number of holes in the valence band. That is, it is a p-type semiconductor. So this is a p-type semiconductor. Now p-type semiconductor requires what is the valency that we need to dope into an intrinsic semiconductor to make it a p-type? We need a 3 valence. Valency should be 3. Okay, 3-valent or trivalent substance. Now if you see all the options, arsenic is a pentavalent substance, phosphorus is also pentavalent, antimony is also pentavalent, only indium is a trivalent element. Okay, so we will dope it with the trivalent element, that is indium. Okay, now let's move on to the next question. The column 1 is the list of materials and column 2 the list of energy band gaps E. Identify the correct match. Conductors Eg less than 3 electron volt, insulator Eg equals to 0 volt, semiconductor Eg greater than 3 electron volt. Now we know the match over here that conductors have 0 band gap, that means Eg equals to 0. Insulators have very high band gap, so their band gap should be greater than 3 electron volt, and semiconductors have band gap between 0 to 3 eV, so it will be less than 3 eV. So let's see the matching. So 1 is matching with B, 2 is matching with C, and 3 is matching with A. So if you see that 3 is matching with A is given only once, we will match the first one also. So this is the correct matching. Obviously option D is correct. Clear? Next question. When a forward bias is applied to a PN junction, it raises the potential barrier, reduces the majority current to 0, lowers the potential barrier, raises the width of the depletion region. So forward bias means what? When you apply forward bias to a diode, what happens is its depletion region, which was wider, slowly starts to become 0. It will start to go towards 0 and slowly disappear when the forward voltage is sufficient enough. Okay, so it is basically reduces the potential barrier or lowers the potential barrier, not the majority carrier. It does not change majority or minority carriers. Okay, it only lowers the potential barrier. Potential barriers lowers and it becomes 0 as you keep on increasing the forward bias voltage. Energy band gap in conductors, insulators and semiconductors are respectively E1, E2 and E3. The relationship between them is, so for conductor E1 is equals to 0. For insulators E2 it is greater than 3 electron volt, whereas for semiconductors E3 it is less than 3 electron volt. Okay, so what we can say is that E1 is the smallest, E3 is in the middle, E2 is more than all the other options. So as you can see, correct answer is E1 is smallest, E3 is next, and E2 is the largest. So correct answer is option D. Clear? So 4, option D is correct answer. Next, P-type semiconductor is electrically positive, negative, neutral. As temperature increases, it becomes negative. So no matter whether it is a P-type, whether it is a N-type, whether it is a intrinsic, whether it is extrinsic, it is always electrically neutral. Does not matter what. Semiconductors normally are always electrically neutral. So P-type, N-type does not matter, because total number of positive charge, total number of negative charges are always equal. So it is electrically neutral. Next question. In intrinsic semiconductor at room temperature, the number of electrons and holes are equal, 0, unequal, infinite. So in intrinsic semiconductor, what is intrinsic semiconductor? Intrinsic semiconductor are those which are pure semiconductors. So normally the total number of electrons are equal to total number of holes, and again it is electrically neutral. So it is equal. In intrinsic it is equal, unequality comes from the doping, and if it is not doped it will always be equal. When a PN junction diode is in forward bias, which type of charge carriers flow in the connecting wire? Ions, protons, holes, free electrons. So when a PN junction diode is forward biased, always in the carrier wire, connecting wires, free electrons flows in the in case of whether it is a PN junction, whether it is a P type, whether it is N type. Okay, it will always be free electron in the connecting wires. Connecting wires will always have free electrons. Inside the diode there may be holes or maybe electrons, but outside in the connecting wires only free electrons will pass, because it is mentioned in the connecting wire. Wire always have free electrons, and that's how they conduct the current. Holes cannot escape the diode and come to the connecting wire. So only free electrons is the correct answer. This is a very tricky question, by the way. Be very, very careful. Next, a positive hole in a semiconductor is absence of free electrons, an artificially created particle, an antiparticle of electron, a vacancy created when an electron leaves a covalent bond. So a positive hole is a vacancy created when an electron leaves a covalent bond. Okay, it is not absence of free electrons. Remember, absence of free electrons is there in the insulators, but hole is not something which is due to absence of free electrons. It is when an electron is moved out of a covalent bond, the vacancy that is left behind, that vacancy actually behaves as a covalent bond, as a hole. Next, the energy gap in case of which of the following is less than 3 electron volt, greater than 0, less than 3 electron volt? It is basically germanium. Germanium is a quantity which is a semiconductor. So semiconductors have energy gap less than 3 electron volt. Aluminium, iron and copper, they are all conductors. So for them the band gap is equals to 0, not less than 3 electron volt. Okay, less than 3 electron volt criteria is only applicable to germanium. Even though aluminium, iron, copper are 0, you cannot say they are always less than 3 electron volt. Germanium on the other hand is always less than 3 electron volt. 0, so it should be mentioned that but not 0. It should have been mentioned that here, but not 0. Okay, not equals to 0. Next question, in the depletion region of an unbiased PN junction, the majority charge carriers are only electrons, only holes, both electrons and holes, neither electrons nor holes. So in the depletion region, it is completely depleted of all the charges, all the possible charge carriers. So neither electrons nor holes are correct answer. In unbiased PN junction, in the depletion region, no charge carriers present. That means neither electrons nor holes. Okay, nobody is there, everyone is dead. So that's why it is called a depletion region, depleted of all the free charge carriers. Now question number 11, the donor energy level ED is slightly below the bottom EC of the conduction band. In case of, so donor energy level, that means the band diagram, if you draw, you will observe like this. This is valence band, this is conduction band, and donor level is here, which donates electron to the conduction band, so that conduction band has more number of free electrons. Donor level appears only in case of N-type of semiconductor. N-type semiconductors have donor level, P-type semiconductors have acceptor level to create more number of holes. Okay, so remember this small trick, that N-type has donor level. Donor means it donates electron, donates means it will have more number of extra free electron. Acceptor means it accepts electron, that means more number of holes are created. Okay, that is the meaning of donor level and acceptor level. This is because of the impurity. This comes into the picture due to the impurity that is present inside the semiconductor, right? In an N-type silicon, which of the following statement is true? Electrons are majority carriers and trivalent atoms are dopants. So N-type semiconductor means, what is the N-type? N-type's majority carriers are electrons, and what is the dopant? Dopant is a pentavalent material. Okay, pentavalent, for example, phosphorus, arsenic, antimony, they are pentavalent. So in case of N-type silicon, even though first part is correct, electrons are majority, trivalent is not correct, so this is not correct statement. Electrons are minority carriers, so definitely electrons are not minority, so this is incorrect. Holes are minority carriers and pentavalent atoms are the dopants. So holes are minority for N-type. Obviously if electrons are majority, then minority has to be there, so holes are minority, and pentavalent is also correct, so both this condition is satisfied, so option C is correct. So be careful, again be careful, don't just see okay electrons are majority and you mark it. You have to read the complete statement to answer this type of questions properly. Next, in an unbiased PN junction, holes diffuse from P region to N region. Okay, so in unbiased junction, holes diffuse from the P region to the N region because free electrons in the N region attract them. They move across the junction by the potential difference. Holes concentration in the P region is more as compared to the N region. All of the above. Here it is actually all of the above. Okay, free electrons in the N region attract them. Okay, holes getting attracted by opposite charge. They move across the junction by the potential difference. There is already a potential difference developed. Okay, electrons started diffusing, so electrons are also started coming towards the hole, so there is a potential difference developed, and that's why electrons started to move. Holes concentration in the p region is more as compared to n region, that is also one of the region. Okay, so all of the above is the correct answer, even though I have some reservation about this. Okay, potential difference is actually developed in the opposite sense, but free electrons n region attract them, so that is one region, so that's why I have answered all of the above. But otherwise, I think all of the above is a incorrect statement. More correct will be hole concentration in p region is more compared to the n region. Okay, this actually not true. The potential difference is actually developed in the opposite direction once what should I say, once the hole starts to move from p region to n region, the potential difference originates in the opposite direction, that gives rise to depletion region. Free electrons do attract them, but the attraction force can be ignored, very small. Okay, and even holes are not actually something which is a real particle, so that in that sense you can ignore this statement as well. So main region is concentration of holes in the p region is more than in n region, so that's why electron starts to shift. Okay, if you are living somewhere where a lot of people are there inside a room, what you want to do, you want to move towards another room which is empty or vacant, right? So that's what holes are doing. Next, when a forward bias is applied to a PN junction, it raises the potential barrier, reduces the majority charge carrier to 0, lowers the potential barrier, none of the above. So when a forward bias is applied to a PN junction, it lowers the potential barrier. It lowers the potential barrier. Which of the following is used to convert AC to DC? P-type semiconductor, N-type semiconductor, diodes, all of the above. Only diodes are used to convert AC to DC. P and N-type individually they cannot convert AC to DC. That means rectification. Rectification process, AC to DC is the rectification process. We will see that. So rectification is possible only by diodes. So PN diodes or normal diodes that are used to convert AC to DC. So all the MCQs are over. Now let's buckle up for the longer version of the question. Name the majority and minority charge carriers in N-type semiconductors. Okay, so what is the majority charge carrier? What is the type? N-type, so majority must be electrons. N-type comes from negative type, P-type comes from positive type. Okay, so remember that. So majority is electron, negative type means electron has to be majority, and minority are those who are present in small quantities, small numbers, so that is holes. Okay, next, what are intrinsic and extrinsic semiconductors? So intrinsic semiconductor are those pure semiconductors are called intrinsic semiconductors. The presence of charge carriers, electrons and holes in an intrinsic semiconductor are intrinsic property of the material, and these are obtained as a result of thermal excitation. Okay, so intrinsic semiconductors are basically pure semiconductors, and charge carriers are intrinsic property of the material, and its conductivity increases with temperature. Okay, the number of charge carriers can be changed by doping of a suitable impurity in pure semiconductors. Such semiconductors are known as extrinsic semiconductors. These are of two types, N-type and P-type. Clear? Easy question. How can a semiconductor diode be forward biased? What happens to the width of the depletion region when forward bias voltage is increased? So a semiconductor diode is forward biased when you connect the positive terminal of a power source like a battery to the P side of the diode and negative terminal to the N side of the battery. This setup helps to overcome the potential barrier created in the depletion region and allows the current to flow through the diode. Okay, as you increase the forward voltage, the depletion region becomes narrower and slowly disappear. Very important, as you increase the forward potential, depletion region depletes and it goes to 0. Differentiate conductors from insulators on the basis of band theory of solids. Very important. So differentiation means obviously you have to write the difference table. Band structure, overlapping partially filled bands. Okay, in case of conductors, both valence band and conduction band, they overlap. Now large separation between the bands in case of insulators. You can write the same question might come in case of semiconductors also, so you have to prepare that as well. Okay, so they separation is small but still distinct. Energy gap 0 or very small, very large, greater than 3 to 5 electron volt. Okay, 3 to 5 electron volt, better to write 3 electron volt. Charge carriers, abundant free electrons in the conduction band, very few or no free electrons in case of insulators. Conductivity is very high and its conductivity is very low. Distinguish between p-type and n-type semiconductors. So property, doping element, trivalent. Okay, in case of p-type, that is boron, gallium, indium. N-type semiconductor, for n-type semiconductor, pentavalent, for example phosphorus, arsenic, antimony, etc. Majority carriers for p-type are holes, for n-type they are electrons. Minority carriers are electrons, and for n-type they are holes. Charge movement due to holes, charge movement due to free electron. Clear? Now these two questions, 5 marker questions, are very very important. Full wave and half wave. Out of that, full wave is most important, okay, because it has came more number of times than half wave, but half wave has also came 1 or 2 times, so don't ignore half wave as well. So what type of questions we can expect from this part? So what is a rectifier? Explain the working of a full wave rectifier using a circuit diagram. Draw its input output waveform. Now what is a rectifier? This is a common portion, and after that they will ask half wave or full wave. Now in your pre-board, both can come. In your final exam only most important is full wave, but half wave may also come. So prepare, please prepare both of them. The diagrams are also slightly different. So remember, when you start the diagram, on our left hand side there is a transformer present, okay, and you are tapping at the middle center tap. It is called center tap. Okay, from the middle it is the reference point. It is grounded over here. So when this side is positive, what happens is, when this side is positive, this becomes negative, and when this side is negative, the other side becomes positive. Okay, so the polarity of the both sides are changing with respect to the center tap, and that's why the diode will be forward bias in one case and reverse bias in the other case. So there are 2 diodes in full wave rectifier. Minimum 2 diodes should be there. Okay, there are other types of rectifiers where more than 2 diodes are used, but simplified number of diodes should be 2. Okay, now what you have to write? A rectifier is an electronic device that converts alternating current to direct current. One such example, do you know what is the example of rectifier? You are using it every day. Even watching this video, you are using that. So one of the most common rectifier is a charger, mobile charger, laptop charger, or some charger that is being used in your TV. Okay, televisions generally have the rectification happening inside them. Otherwise, for all other devices, laptops, mobiles, the charger itself is the rectifier. It not only rectifies, it is also transform the voltage. So it is actually combined device. Okay, it changes the voltage as well as it also rectifies from AC to DC. If you read the label on a charger, you will realize that it is mentioned that some 220 volt AC input and some 2.1 ampere 5 volt DC. So that's what the voltage is being reduced, and also the current is also changing, right? Now an AC have 2 cycles. And AC have 2 cycles. One is this is called positive, this is called negative. This cycle is called positive, this cycle is called negative cycle. Okay, so during positive half cycle means this cycle. Okay, this is the positive cycle. During the positive half cycle of the AC input voltage, the upper half of the transformer secondary windings becomes positive. So this one becomes positive. Okay, diode D1 becomes forward biased and conducts, allowing the current to flow through the load resistor. So if you see that the P side is positive and the other side is 0, so voltage current will pass from positive to 0. So this diode conducts, whereas the diode D2, this is negative, P side is negative, so that means this does not conduct, so only this diode is conducting. Okay, so allowing the current to flow through the load resistor, diode D2 is reverse biased and does not conduct because the P side of the diode is negative. So negative voltage means the diode is not conducting, so we are only getting a current through diode D1, and that is also along only one direction. Now if you draw the input output waveform, you will see that this is waveform for A, this is the waveform for B. So when this is the positive cycle for A, for B it will be negative cycle. When it is negative cycle for A, it will be positive for diode B. Okay, so D1 conducts during the first cycle, D2 conducts for the second cycle. Clear? Any doubts? You can ask me later on. During the negative half cycle of the AC input voltage, the lower half of the transformer secondary winding becomes positive, diode D2 becomes forward biased and conducts, while diode D1 is reverse biased and does not conduct. Current again flows through the load resistor in the same direction as during the positive half cycle. So this is the minimum writing, and everything is written perfectly. Okay, so you do not change it or do not reduce this much. Okay, 5 marks you are going to get, so at least have to put some effort, right? So put some extra effort and write exactly as it is showing in here. Okay, next is what is a half wave rectifier. Explain the working of an half wave rectifier using a neat circuit diagram. Also draw the input output waveform corresponding to it. Now if you see the half wave diagram, there is only one diode present, no center tap, so only one diode, one load resistance, and it is a very simple diagram. Okay, diagram is very simple, but do not confuse half wave and full wave. Okay, half wave is slightly different than full wave, so do not confuse with half wave and full wave. Now a half wave rectifier is an electronic circuit that converts alternating current AC into direct current DC by allowing current to flow only during one half cycle of the AC input signal. The other half cycle is blocked, so only half of the AC waveform is used. Okay, now so this is the circuit diagram. So during what happens is that the positive half cycle diode conducts, during the negative half cycle diode does not conduct, so you get a flat line over here. During the positive half cycle of the AC input, the P side of the diode is positive with respect to the N side. The diode becomes forward biased and conducts the current. Current flows through the load resistor RL in one direction and voltage across the load is positive. Negative half cycle of the AC. During the negative half cycle of the AC input, the P side of the diode becomes negative with respect to the N side. The diode is reverse biased and does not conduct. No current flows through the load resistor RL and the output voltage is 0 during this half cycle. Very important. Okay, so the output voltage is 0 for the second half cycle. Now let's move on. Now this is the last question of this chapter. This question you can skip, but I recommend you should also practice this question. No harm done. You are going to get 5 marks anyway, but if you do not have time, you can skip this question. This question might be asked as a 2 marker question, or can become as a 5 marker question along with all the parts. So that's why I recommend to study this question as well. Write 3 differences between intrinsic semiconductor and extrinsic semiconductor. So it can come as write 2 difference between intrinsic and extrinsic, and can be asked as a 2 marker question. So definition: a pure semiconductor with no impurities. Extrinsic semiconductor doped with a small amount of impurity to improve conductivity. Charge carriers, equal number of electrons and holes. Unequal number of charge carriers, majority carriers electron in N type and holes in P type, and minority carriers. Okay, so extrinsic semiconductor has 2 types of carriers, minority as well as majority, but in intrinsic there is no majority minority, everyone is equal. Conductivity: low conductivity at room temperature, high conductivity due to doping, which increases the charge carriers. Okay, so extrinsic semiconductors, these properties, intrinsic semiconductor, these properties you have to remember. Next, draw the energy band diagrams of N type and P type semiconductors for temperature T greater than 0. Easy diagram, easy to remember, nothing difficult, no rocket science. Here if you see that, first of all, in case of P type and N type, you have to show the corresponding impurity level. Okay, so this is an N type. So in N type semiconductor, this is the This is called donor level. Donor level. Okay, and as you see, this is the valence band, this is valence band, this is conduction band. Okay, so electrons are here in the valence band as well as in the conduction band. More number of electrons are in the conduction band. That means this is an N-type semiconductor. In case of P-type semiconductor, what happens is that this is a P-type semiconductor. Now in P-type semiconductor, this is acceptor level. Okay, this accepts electron. Acceptor level accepts electron from the valence band, so that more number of holes are present in the valence band. Now if there is a objective question which says that in case of P-type semiconductor, holes are located at, so holes are located at valence band, not in conduction band. Remember, this is valence band. Okay, conduction band is almost empty. Some few minority electrons are present. Okay, in majority of the holes are actually present in valence band. Okay, conduction band is consisting of only electrons, whereas holes are present only in valence band. Why so? Because you are breaking a covalent bond, right? Bond happens only because of the electrons taking part in valence band, right? Valence band determines the valency of an atom. So because you are breaking those bonds, that means holes are created only in valence band. Okay, so this is very interesting point for an MCQ objective type of question as well. Okay, so holes are located in the valence band and electrons are located in the conduction band. Okay, so this is the acceptor level P-type semiconductor, and you can show this energy gap 0.1 electron volt, and here it is 0.01 to 0.505 electron volt. Okay, so this is 0.01, this is 0.01 to 0.05. This is optional, but the band diagram should be drawn like this. Holes and electrons should be shown properly. Okay, so this is the end of this lecture.